morphisms which are not yet in C, which are in this category. And I want to prove that this family of morphisms can be factored in a unique way through a dotted morphism into X. And now I have to make explicit what it means. So first let's prove that we can factor it through X, and then we will prove uniqueness. Alright, what is a dotted arrow from Y into one of the xi's? It can be defined in terms of an arrow yi goes to Y, which is in sigma. So how would you denote the arrows that are in sigma? Perhaps by putting little bars throughout it. In sigma prime, I'm sorry. And by giving a homomorphism of yi into xi. All right? Call perhaps rather zi is instead of yi. Now let's look at the finite product of all the zi's over y. This is an object that lies over y, and because of axiom number 4 here, and of the property number 4, z goes to y is also in sigma prime. All right. Now we can view that these morphisms, instead of being defined by zi goes to xi, we can view it as being defined by z going to xi by the compositor, because z is mapped to zi. So what we have done here is to find a single z over y with an arrow here which is in sigma prime, in such a way that all the added morphisms that we have here for every I comes from a morphism of this same z into xi, or ui. Why I'm true, because I know that I can find a morphism of z into x such that these triangles here commute, because x is a product in C. Now, this morphism from z into x can be interpreted as a dotted morphism from 1 to x, and it does what we want. So that's about the existence of the factorization. Now, what about unicity? Assume that we have two dotted morphisms from y into x, such that the compositions of these dotted morphisms between each of the projections are the same. All right. So, provided we want to prove that they are the same, these two dotted morphisms. Now, provided I replace y by some y prime lying over it with an arrow here which is in sigma prime, I can assume that the two dotted morphisms are already defined by morphisms, actual morphisms y prime into x. Because I have the calculus of fractions. Y primes form an inverse system. So, as this here becomes an isomorphism, this is an isomorphism within c sigma prime minus 1, I can just as well assume that y equals y prime. That is, I can assume that I have actual arrows from y into x, such that the compositions of these arrows with the projections not are equal, but that they are equal when you view them as being dotted, that they're equal in here. That means also that if you look at the kernel of the composite of this and this arrow with the projection here, so this pi, called the kernel ki, that means that the inclusion of the kernel ki into y is in sigma prime for every I. All right, now if you look at the intersection of these kernels, that's just a finite product. Call this k if you want. And because the ki over y lie in sigma prime, k over y lies in sigma prime. And now we see that the composition of these two arrows with k goes to y are the same, and k goes to y is in sigma prime, therefore the corresponding dotted arrows are the same. And at the same time we have proved that this function commutes with products. So there's a third point to prove. Should we do it or will we leave it? I guess it's the same kind of game. So what is remarkable here is that when we localize within the category delta, we get a surjective morphisms on the objects. We don't have to add any more objects. That is, if you have an algebraic, it implies that if you have an algebraic theory, and if we add more axioms to it, we don't have more constructions, but we have more arrows between constructions. That's all. But I think that's pretty special to this case, and there's just one type of limits, either inverse limits or of course there's a dual thing, and direct limits. On the other hand, there's a common feature to these problem number 1 and problem number 2. Namely, we start here with a category. We take the enveloping category I tilde by adding inverse limits. And we see that I within I tilde, turns out that the functor here is fully faithful, but never mind, that's not what I have in mind. That the objects of I form a set of cogenerators in I tilde. This came from the fact that in the dual situation, when we look G and J tilde, and G and J hat, G and J quite well known that they form a set of generators in J hat. Now, in fact, J and J hat is a set of generators in the strongest sense that has been so far studied. Namely, every object of J hat is a direct limit of object of J. That's called, we say in this case, that J is a strictly generating subcategory. There are about 5 or 6 variants of generating subcategories for topoi or categories which satisfy some mild exactness properties. They are all the same. But for total categories, they need not. So here we have the strongest possible property of being generating. We call this strictly generating. And when we go to the dual categories, we say that I is strictly cogenerating in IT. Every object of IT is an inverse limit of objects of I. That means can be reconstructed from objects of I through the limits that are inside D. So that sounds good. Now what about the problem 2? We start with the category C, with, in terms of it making invertible some arrows, we construct another category, C sigma minus 1. It's pretty clear that they have even the same underlying set here, underlying objects you see. So certainly, they are also, it's cogenerating. Now, what about now passing to the limit? It's pretty easy to see that if you look at categories R alpha in delta, which form a, let's say, for instance, a transfinite Dirac system or just a filtering Dirac system, transfinite or not. And if you look at the 2 Dirac limits of the R alpha within the category delta, and assume now that for all of the R alphas, I have a category I, let's say, which is mapped into each of the R alphas, and therefore which is in a compatible way, so it's mapped into the limit. And assume that for each of the R alphas, I is strictly cogenerating. Every object of R alpha is an inverse limit of object of I within R alpha. Then it's pretty easy to check. I won't check everything here. By the way, I don't exclude that I have made mistakes because I have written up things pretty quickly. I had just the day of yesterday. So I'm saying a certain number of things, I'm telling a nice story, but there may be mistakes in it. So because I couldn't do things too carefully. But I think that essentially these things are correct. All right, so modulo mistakes. I think I checked this one. It then turns out that also every object of R is an inverse limit of objects of I, and the I is decogenerating in R. I didn't check, I'm afraid, did I? Let's see. It's the same with adding arrows. Well, that's what I state here. I think I checked it. Yes, because adding arrows, you see you first add, remember, arrows in the set-theoretic sense, and then you have to reverse, then you have to take an envelope, and you have to then to reverse some, to make some arrows invertible. But each of these operations you see that you perform, it's pretty clear that, yes, let's do it. So you have a category C and delta, or R we will call it. And then you add a bunch of arrows between various objects of R, but you want to do it in the sense of delta. So let's call it RH underline delta. And you have a functor from R into this, and assume you have also a functor from I into R, and assume that every object of R, that I in R is strictly cogenerating. I claim that I is also strictly cogenerating here. So, in fact, strictly cogenerating is something that is transitive. So all we have to show is that R is strictly cogenerating in here. So let's prove this. And therefore, let's recall how we did this business. We first added these arrows to R in the category of categories. This was a random universal construction, and in doing so, the objects have not changed. One has just added arrows and formal composite of these arrows with themselves and with the arrows which existed already in R. So certainly, R is cogenerating in here. No problem. In fact, they have the same objects. And then, one had, however, to make certain arrows invertible, because we want to express that a certain functor from R into this. No, now I have to first to take the envelope with respect to delta. But we know that the objects we started with are cogenerating in the envelope. That's what Mark that we have already said. And after this, we have to make some arrows invertible in order to express that the functor, which goes now from R to here, should commute with inverse limits. But when we make some arrows invertible, let's say we take a sigma minus 1 in the sense of delta, we know also that they have the same objects. So altogether, R remains cogenerating throughout. That means that in each of the 4 types of steps that we have in constructing algebraic theories from an indexing set I, this indexing set I is always cogenerating in the strict sense. And now we have enough in order to prove the theorem which solves. How does Lawvere call it? The semantics of algebraic theories of delta. Sum is the following. The algebraic theories are those which are two representable by category C in data, which admit, that means categories with arbitrary inverse limits, which admit a small cogenerating, which admit a small strictly cogenerating family. So we can call also it delta generating, namely, or degenerating, namely every object of the category can be expressed as an inverse limit of objects of this small subcategory. Moreover, the functor I, where I is discrete, goes to R is basic. If and only if this the image of I and R is strictly cogenerating. That is that what I collect as a conjecture in the general case turns out to be a theorem here. So algebraic theories are just corresponding to delta that can be expressible by arbitrary inverse limits, just are classified by categories in which arbitrary inverse limits exist and which have a cogenerating set, small cogenerating set of objects, or dually speaking, and the dual category will be very interesting for us in a minute, or so. they correspond to categories in which arbitrary diagonals exist, and which have a strictly generating set, which is small. Set of objects which is small. So this is kind of. Now I haven't given quite the proof. What I have kind of proved is that if you have an algebraic theory, then it has a property stated. And if I goes to R as basics, then I is cogenerating in R. Because I kind of analyzed what happens in the 4 steps that we had in building up algebraic theories. So we have to prove the converse, namely if we have such a thing, then it corresponds to an algebraic theory. And I being basic. And how does this go? Yeah, and in fact it's been in 5 number of steps, 3 steps I think, for to start with, and then 2 can be constructed. So that's also interesting here. We don't need to make a transfinite construction. So let I prime be the full subcategory of R generated by I. So what I take as underlying set of I prime, set of objects just I. But the arrows are so that, the morphem are so that we have an R. So I prime to R is now a fully faithful functor. And the functor that we are given is a compositum. And I goes to I prime and uses an isomorphism between objects, bijection between objects of I. Isomorphism of I prime. And now, as a first step, let's already condense some of these. Let's look at the theory. Let's call it T lower I prime tilde, which transforms every C into hom underlined within cut of I prime C, which is also hom underlined within delta of I prime tilde and C. Now we have seen several times, I think, that this is an algebraic theory, because we get it by 2 steps. First, starting with this set of objects and taking the empty structure, that's step number A. Then we add all the arrows that we have in A prime, that's step B. That's step C rather, we did it in this order, so that's step C. And then writing axioms which express that we have a functor from E prime into C, namely that we have associativity. So in 3 steps we construct Ti prime tilde. And of course we have a canonical functor which goes from Tr to Ti prime tilde. And now what I claim is, because I prime tilde is mapped into R by a delta functor. Now what I claim is that R can be described in terms of I prime tilde by just passing two categories of fractions. Because we have just now to add some other axioms, some more axioms to our theory. I think that some errors become invertible. And that's it. Now why is this? We know already that I prime cogenerates R strictly. So every element of R is the inverse image, is the inverse limit of a diagram inside I prime. Now this diagram can be viewed because I prime is a full subcategory of R. That this functor is full. It's a diagram in I prime if you want. You take its limits in R, but it can be viewed as a diagram in I prime. And it has a limit, of course, in I prime tilde. And the image of this in R is, of course, the element we started with. That means that this functor is essentially surjective on objects. Alright. Now, in the same way, one can show that it's essentially surjective on arrows. Because let's assume that we have an arrow from x to y within R. Then this defined as an arrow from I prime, how would we call this, the categories? Of objects lying under x, call it, of objects of I prime that lie under x, together with an arrow of x into it. Call it like this. We get a functor from x goes to I prime into y over I prime. That is more accustomed to the situation, in the dual situation. Whenever I have an object of I prime and together with a morphism from x into hey, it goes in the opposite direction, like this, of y into it, then by composing with x goes to y, I get an object of I prime with a morphism of x into it. All right? And now x is just the inverse limit of this diagram, viewed as being a diagram in I prime. And y is the inverse limit of this diagram, viewed as being a diagram in I prime. On the other hand, the arrow which I have and here I have already, on the one hand we have the categories which we have here, and on the other hand we have the functors from these categories into I prime. And the functor which I have from this into I prime is just a compositor. This functor I have from this into I prime. And therefore we know that there's a corresponding map which goes from the inverse limit of this into the inverse limit of this. And that's precisely the map we started with, of course. I mean, we can reconstruct the map through a morphism between the canonical inverse systems, of which x and y respectively are the inverse limits. But now, you see, these inverse systems are I prime, they define inverse system in I prime tilde, and therefore, and a morphism between them, and therefore a morphism between the inverse limits. And the corresponding morphism in R is this morphism here. Therefore, it's surjective on objects, essentially, and surjective on arrows. And therefore, R is a quotient category of I prime tilde obtained by collapsing certain arrows, by making certain arrows equal. But because we have a functor here which is left exact, that just means that other arrows should be made into isomorphisms. That means that R is a quotient category of I prime tilde. So in fact, I got this thing in 4 steps. Taking the vague structure on I. Second, adding a bunch of arrows. Third, then adding axioms which say that some compositor become equal to others. And fourth, other axioms stating that certain other arrows become equal. But now, the 2 last steps can be condensed, because when you pass to a quotient category entry, when you pass to a quotient again, it's the same thing as if you pass to a quotient category in one single time. So in fact, we have an arbitrary algebraic structure in 3 steps. So here we don't need any transfinite construction. Should we stop or go on a little more? What is the feeling? Or just relax and discuss a little bit without dragging the whole. Slightly lengthy, you see, to explain that. These things come out pretty simply here.
Yeah, it's remarkable, isn't it?
They will be just as simple with topo, I think. Yeah, what should we do? Should we go on in the law or leave it for some other time? But in my notes here, what do I have more? I have a number of extra comments on the situation, which is kind of a nice, rich situation. And then the next step would be to consider what happens if D second is empty and D prime is anything, and to solve problems 1 and 2. And slightly more intricate, but pretty simple. And then to look at the very beautiful situation when D prime is just the set of all finite diagrams. And then the relation between, call this delta now, and that's delta naught, that's delta 1, the kind of categories which have arbitrary inverse limits. So every delta structure defines delta 3 defines delta 1 3. But one can show that we can also pass in the other direction. There's a nice correspondence here. So that's the kind of thing that we have to be said. And in the process, I thought that maybe the knowledgeable people here could clear up what happens when we take for D prime. That's the thing which I'm not so familiar with. I don't really feel so well. If I take for D prime all finite discrete diagrams, I look at classical finite products and tie it up somehow with the Jones theory. There are these things which I think they managed to be discussed a little. So apparently it's perhaps a little late because it might take us an hour or two more. So this is one thing. And then, which I thought we would do in our next time we meet, to look what happens with topos. So what we could eventually do, so there's two choices. Maybe it's reasonable not to go on for an hour more, so it might be a little long.
Next month.
Maybe we could take
On the other hand,
maybe we could take
next week is the last we are functioning. So if we want to meet still for the seminar still 2 times, so that on one time we finish speaking about this case when the second is empty, and then another time to say what say what we know about topos, then we should try to find some dates.
How about next Monday and Wednesday?
Monday and Wednesday.
It's fine.
For me it's alright.
I'd rather know Mondays. This one's okay for me because it's a holding calendar, but Mondays are bad for me.
What do you mean, Tuesday and Wednesday, you mean?
That's better for me, yeah.
Monday, next Monday?
No,
Today.
today was okay, but normally Monday's bad.
Well,
So let's say Tuesday and Wednesday next week. So Tuesday we finish with the stuff of inverse limits, and on Wednesday we try to clean up what is known and not known about topos. And now today, what are we doing? Should we stop, or is there any discussion? Just to cut, to discuss it all? Any comments? What has been going on? To me, still after when one gets used to the setup, it seems to me that it becomes very concrete as soon as one starts looking at the example. I mean, I consider these things which I've done right now. I mean, with explicit construction, I consider it as being very concrete. Everything comes out kind of nice. So this gives some perhaps this illusion perhaps that there should be nice solutions always to these problems. To these universal problems, which is the main matter.
We're just wondering.
But it's over now.
You have any questions?
No questions, I'm afraid.
I think most of the stuff in the past has been with the intermediate step that you talked about before, where you put, what's corresponds, let's see. Can we go on and actually represent one? I think you're going just a little bit further and actually talk about the classifying category of the representative.
I mean, for particular examples?
Yes, yes.
Well, I mean,
Just
it's
carry on through.
It's very easy. Let me then go one step further. If we have the algebraic theory T, which is represented by R, you see, and I claim that on the other hand, let's look at S, the representative of the theory in the category of sets. For instance, if the theory is a set of groups, we have all usual groups. R turns out to be just the opposite category of the category S. Right? That's really very simple.
Yeah.
If our structure is a structure of rings, the classifying category for it is the opposite category of the category of rings. And the same for modulus, Lie algebras. I mean, everything that can be expressed in terms of inverse limits only.
And let's see, how do we start? No, let's see. That's.
I will give the
that's
proof
how
if you
to-
want,
quick,
because it's easy enough. So our theory, therefore, is just a theory from delta. C goes to home delta of R C, where home delta means the functors that commute with arbitrary inverse limits. Now what if I take sets T of sets, I'm sorry because I'm accustomed to the French notations. T of sets.
I think
That's-
McLean even uses R notation. McLean uses R.
Yeah.
Yes.
So we have to take all functors covariant from R to sets that commute with arbitrary inverse limits. Now R is a category where arbitrary inverse limits exist and which has a small cogenerating family, and therefore we know that these functors are exactly the representative ones,
Yeah, exactly. That's
and
it.
therefore this is equal to R naught.
No, that's precisely it.
And therefore R is equivalent to S naught, if this is S here. That is, we find here once again, I mean, in a particularly striking way, that the knowledge of the realizations of our type of structure in the category of sets implies the knowledge of the whole theory, because it implies the knowledge of the category S implies the knowledge of the representing category R, which is just the opposite. So if we look at the opposite category of the category of groups, let's say, there's a canonical group sitting in there. So in the category of groups, there's a canonical co-group sitting. In the category of rings, there's a canonical co-ring sitting.
What other kind of ring? What other kind of ring? Like if there is some direct limit,
If who?
there is some direct limit,
Ah.
instead of D double prime Q of and void, that is the case where there is only two parameters. Yeah, right.
If the second is not void, empty, you mean?
Not empty, right? Yeah, right.
It's not empty. Completely different affair. You see, I have kind of studied the case when we are looking at topoi, you see, which is something very specific. I mean, there are 100 other cases one could look up. See, for topoi, it's very, very, very explicit solution to universal problems. But already, if we take the case of additive categories, I would think it shouldn't be too hard to construct the solutions. But take abelian categories with exact functors. it's more difficult. Maybe that you won't find the solution to this unless you have the general process doing it in the general case. Other than if you take, I had no of examples which perhaps I will have time to speak about it, but we speak about topoi. And d prime and d second are both big, not small. When the solutions don't exist, you see. Because the solutions that turn up, you see, you find solutions of different problems, quite canonical, but they are not in the universe. I mean, they are not eligible, you see, they are not eukaryotes, for instance, or such things. They're just too big. It's very funny because, I mean, the computations, you see, they go quite through, but you wind up with things that are too big. So I have said here for the last hour or so, and what we're going to say next time, it's really very much special to the case when there are only inverse limits considered. Of course, you can dualize and look at the situation and there are only light limits. But I mean, there are essentially new things occurring, and there are two types of limits. We have repeated this all over and over again, in fact, in the course about topoi, and I think even in the course about algebraic geometry. That when there's only one type of limits, inverse limits, then there's a yoga which reduces everything to set theory by identifying an object whose function it represents. Whereas when we have both types of limits, then we start being ill at ease, and the way out is to replace categories of functors with in sets by categories of sheaves on some. And then again, things become smooth. And therefore, next thing you like to do is therefore to try to look at these problems for topoi, which seems to be an important, interesting case. You see, topoi really kind of nice. But nevertheless, of course, there are thousands of other setups which can be reduced to different topoi.
What's going to be I here?
In which case, groups?
So, yeah.
Finely presented groups, for instance. Or in the case of, in fact, you have just one object, you see. That is the universal representative. Let's say, what is it? Let's try to remember. So let's take the structure of groups. So S equals usual groups. So S naught is just opposite category. An object of F, of R or of S is the same thing. So what is the universal object in it? The co-group. I think it's Z.
It's Z.
Yeah. Because let's see. Yeah. What about I? You have to be explicit about the generators. Let's say. What's about I goes to R? You see.
So you've got to fill out all. You've got to fill out. I has to.
So we are identifying S.
Oh yeah.
You see?
I see what the
S.
response.
We are identifying it with. If S goes to ounce to the I, that's it. We have to define this. That's
right.
Capital I constructions. We have to see what is the effect on S. All right. So to have an object of S, we have to associate a sequence of sets. And what we do, of course, is the following. S can be viewed as being a functor from R to ounce, and then we take the values of this functor on I. But if we want to view S as being objects of R, you see, they're representable functors. So let's call R over I, you see, these elements. Then we should take hom of S. So there's an RI, these are the sets underlying. That's the underlying. And this is the hom in R, which should correspond to hom in S of Ri and S. Now that's it. Therefore, how do we get, these are Ri's, if we interpret R as being up to arrow reversing the category S itself, the functor which associates to every object of S to every group, the underlying set, should be represented by Ri. But we know it's represented by Z. We know that a group G can be identified with the group homomorphisms of Z into G by associated with every G in capital G, the homomorphism of Z into capital G, which transforms one into this element. So, in a natural way, Z is a co-group in this category. And what does this mean? This means that we have a canonical morphism of Z into Z times Z. I guess it can't be anything different from the. Oh no, I'm sorry. Into the sum of within the category. That's the free group on two generators. And I guess what you do is the following. This here is a free group on one generator X, call it f of X. This is a free group on two generators X and Y. And Fx goes to, we call them rather perhaps X1 and X2. And this reason here should be, I think, the one that maps X into X1, X2. Can't be anything else.
Yeah.
Yeah, and then everything should come out in anyhow completely trivial as a mere translation of what we have said so far.
And part of the problem too is the part of the changing the basic data is you're requiring here you're requiring to be actually sitting in delta. So the way that if you set up the problem back where D has fewer limits, and exactly as you were talking about, where D just says finite diagrams as they've been getting on flow down to finite discrete diagrams, then the requirements are less stringent. And I sitting inside here gets smaller and smaller, or at least it is not required to be so large.
Well, I is always one element in this example.
Yes.
I is just, I mean, you see, we have one base set for groups, usually. I mean, we can, of course, define the several base sets, but that's kind of handy taking one.
Wait a minute.
But taking smaller and smaller
No, wait.
sets of limits to consider, namely larger and larger deltas, you see. That's it. Will lead, but we will analyze this, I think, with some care, to smaller and smaller r's. You see, there will be some submatrix sitting in there, stable under limits of type D prime. But I think.
Oh, that's right. You didn't. That's right. You didn't make that requirement on I that it's sitting.
For the time
that
being,
I didn't have to sit in delta.
In delta? No.
No,
I just do this
no,
discrete.
no, just can be discrete.
Yeah,
Discrete,
that's the base
that's
set.
right. That's right.
The
It's
base
the
of
basic
sets.
base. Yeah. That's right.
So what I did, I think, it's really clearer. Not to mix everything up. You see, first to look at the case when D is equal to all inverse limits, no Dirac limits, and first understand this situation quite well. I mean, we have about said everything, not quite everything that can be said, but I mean, at least as far as mathematical, what requires mathematical proofs, I mean, I think the main technical things have been done. The rest is just, guess the consequences of what has been done so far. And then second step, I think using what we have said so far, looking at what happens for an arbitrary D prime here, D second still being empty. And the way I solve problem 1 and 2 at least, you see, I quite essentially reduce, I use the solution in the case of where D prime is everything, and I kind of reduce to this case by an ad hoc construction. See, I can say it at once, but it's for problem number 1. You have a category C, we want to add not arbitrary inverse limits, but only inverse limits of type D prime. What I do, I begin to add arbitrary inverse limits, I get C bar. We had a very nice explicit solution. And C sits as a full subcategory in C bar. And now I take the subcategory of C bar, stable under limits of type D prime, generated by C. And I'm talking about that it does it. And so I add to C in C bar all, for instance, finite inverse limits if that's what I want, or finite products if I want finite products, etc. And it turns out, of course, one may have to iterate it. It's not clear that doing it once, what we get is already stable under these types of limits. So we keep iterating it. If we have only finite inverse limits, it's enough to have a countable induction. I mean, in fact, it turns out that if we have all finite inverse limits, then 2 steps is enough.
But obviously, for example, groups is describable in these, groups again is describable in these terms with far less fewer, let's say, finite or even less finite products.
Yeah.
Then delta is different in this case. And R, the R certainly exists in that case too.
Yes.
And
But it's contained in the big R, you see.
Yeah,
They all
precisely.
sit in the same
precisely.
thing.
That's right, it's sitting in the big R.
Yeah. So, I think...
But for example, R is small, R is even a set in that case.
Yeah.
I mean, R is tiny, it's small, R is
That's not by
small.
the same letter. I call it by a different letter, you see. Because I like to look at this 2 series, you see, all inverse limits and just a bunch of inverse limits simultaneously, and have then different notations for the all-encompassing R,
All right.
which is just the opposite of the category of realizations of our structure in sets, and then the subcategories which are stable under D prime limits only, you see, which sits there as something like an extra data.
Right.
So it's something to give an algebraic still, you see, in D prime is something in a way, well, I mean, more precise than to give it in D prime 1, taking all diagrams for inverse limits, because we have a theory in the first setup, it defines the theory in the second setup, but not conversely. So we can restrict this theory to categories with arbitrary inverse limits, but there's no operation in the opposite direction. However, that's something remarkable when D prime consists of all finite diagrams, and then it goes kind of 2 ways.
Yeah.
But I think these things we should explain with some care next time. You see here, we have kind of hand waving. We should be more specific. And it's really, I think it deserves to be done with care. But so maybe we stop for today. In these particular cases, it doesn't seem to be so hard.
No, but it gives a lot of insight into how long things have already been done, fit into a larger scheme. That's what I'm finding out.
By the way, in my notes I don't state anything such. I state that this condition is satisfied if and only if f maps e pi into e prime pi and is pi accessible, which is kind of clear. But however, I have to prove that if pi is big enough, for some pi's, for at least one pi, f maps e pi into e prime pi. So there's something. Prime C. There's an argument in SGA notes, but it kind of escapes my mind how it was obtained. So maybe we leave this question open. In fact, what was proved in the SGA note was that if E and F have both a couple filtration, and if the objects of E and F are accessible. So this is true in the case we have here. In fact, the categories are accessible in our sense, and it's much stronger than this. Then, for every, and let's call these filtrations phi pi and phi pi prime, if you want. Phi prime pi, the ones in E and the one in E prime. Then what is proved is that provided we take pi big enough and we take C of the type 2 to the pi, then the functor f, the accessible functor f, maps field C into field C into phi prime C. That's what was proved there. But I just can't remember now what came out. So apparently here, this implication, there's a proof to be given that escapes me. So the essential part is to prove this here. Once we have this, of course, then it's practically done. Because once we know that the functor f maps some e pi into f pi for some pi and is moreover pi accessible, then it's clear that it's the unique functor deduced from this functor small f here, or small f over pi, by passing over to end pi. Because f commutes with direct limits that are dominating pi, you see. It's known that we know it on e pi, because every object of E is expressed in terms of objects of e pi as such a direct limit. So here we have, I mean, there's just this technical point which I get mixed up with. I don't see how it comes out. It's kind of simple. What we did prove, and what was proved in SGA was that for pi big enough, the direct image by f of field pi was contained in field pi to the pi naught, where pi naught was some fixed cardinal, see, which is not so pretty. But now once we have, and therefore, however, if pi is big enough and of the form 2 to the psi, then 2 to the c, then pi to the pi naught is equal to pi. It may be true that for every cardinal pi and pi naught, pi is strictly greater than pi naught, that pi to the pi naught is equal to pi. That's essentially the generalized continuum hypothesis. But, well, we don't know, but for some pi's, I mean, for those which are of the type 2 to some power, 2 to the lambda, let's say, lambda is some other kernel, it is true. And therefore, we know that for at least one pi, we have this inclusion. But once it's true for one pi, it's true for all the following ones. This wasn't done in the SGA notes. I didn't just see it. Because as we have our functor, you see, which is the end pi functor of a functor from e pi to f pi, it's pretty clear that it maps e pi prime into f pi prime. Because if we have an object in e pi prime, this means that the object is of the type limit of xi's, the xi's being all of them in e pi, and the indexing set I here being dominating pi and having a cardinality at most pi prime. And now, of course, capital F of x is the direct limit of capital F of xi, and these F of xi, they lie by assumption in e prime pi. I'm sorry, it's e prime. They lie in e prime pi, and the direct system here has cardinality at most pi prime, and therefore the direct limit must be in e prime pi prime. Therefore, in fact, what we have proved at the same time is the following: that if we look at the canonical cardinal filtration of the accessible categories E and E prime, and canonical, it's canonical at least for the cardinal big enough, you see. It doesn't depend on the choice of any choice, it's just the filtration by pi accessibles. You see? Alright, then any accessible functor from E into E prime for big enough cardinals respects the filtration. That's kind of nice, you see. We have this filtration that's practically up to neglecting what happens for the first few cardinals. this filtration is respected by any accessible function. I wonder what time it is, maybe we should.
7:20, 6, yes, no, 7:20.
Maybe we would be reasonable to stop. Because I have not completely finished the story, but almost. Should we finish the story? Maybe it takes 50 minutes more, it's all right. Right with you? Fine. So I will try tomorrow to perhaps to give the indication of the proof, which I kind of mixed up. Various other ways of expressing this accessibility business. If you don't want to use these canonical filtrations, here we give some statement which was in the SGA notes. So the idea is that the functor, accessible functor from E to E prime is a functor that can be already described when we know its restriction to sufficiently large, small subcategory of E. And we can express it also in the following way. Let's see here a small subcategory of E. And look at the category of functors from C to E prime. Of course, we have also the category of functors from E to E prime, and we are really interested in these. And we have a restriction functor. When we have a functor from E to E prime, we get its restriction to C, which is a functor from C to E prime. But this restriction functor has a left adjoint. If the inclusion here is called I, then the restriction functor called A upper star, and the left adjoint called it I lower schräg. Kind of transitional. This adjoint functor exists because in E prime direct limits exist. We are restricted to this case. All right? And now what we see is, as a consequence of this, that the functor is accessible if and only if there exists a small subcategory C and E, so that the functor belongs to the image of I lower schräg. And in fact, these functors I lower schräg, they are fully faithful. You see, so we can say that the category of functors from E to E prime has these full subcategories in here sitting there, which for C larger and larger become larger and larger. And the union of all these full subcategories is just the accessible functor from E to E prime. So, yeah. Now, some I should also perhaps, as we are interested in categories in which arbitrary limits exist, I should say the following. When do arbitrary limits exist in the category n lower pi of C? I claim that arbitrary limits exist, direct limits, in E, if and only if for every set I, ordered set, no, not ordered, every category I, category with, well, ordered set would do, I think, with cardinality of I at most equal to pi. I limits exists. I limits exist in that in C Dirac limits of cardinal at most C exist. So you see the Dirac limits are, they're kind of, arbitrary Dirac limits are kind of cut into two pieces. Taking Dirac limits for cardinality at most pi, and then taking Dirac limits with respect to indexing sets that are filtered dominating pi. It's pretty, let's show, for instance, let's try to show how this works. Let's show, for instance, that if you have an arbitrary Dirac system, xi, in C for simplicity, you see, that then the Dirac limit exists. The case of an arbitrary Dirac system in E would be reduced to the previous one, because every limit of this Dirac system is itself the limit of a Dirac system of objects of C. So let's prove that the Dirac limit of the xi's exists, provided we assume that in C Dirac limits of cardinality at most pi exist. Well, I mean, we do always the same. We do the same business as several times before. We take first for every subset, subcategory I prime of I with cardinality of the set of arrows of I prime at most equal to pi. We take the Dirac limit of the xi's for I just in I prime. Now this is something that exists in C. And I take the Dirac limit of all these, or in n pi c, then I take the Dirac system of all these, which is an limit of n pi c. And then you just have to check that this Dirac system is a Dirac limit of these xi's, which I think will be trivial checking. It comes from the fact that the Dirac limits large with respect to pi commute to inverse limits that are of cardinal smaller than at most equal to pi. You see, I mean, there's something one has to be a little careful with. There's something to be checked, and it comes from this fact. You see that they kind of match together. One has to write it down, and we can in fact express the situation in the following way. Look at the category delta in cut, where arbitrary Dirac limits exist, and then we take functors which commute with arbitrary Dirac limits. And let's look at the larger delta lower pi, where we assume that Dirac limits of cardinality at most pi exist, and where we take functors which commute with those. And if we have an object in this category here, which is small, and then we can look at n lower pi of c and to the canonical functor from c into n lower pi of c, which turns out to be a functor into a category in here. And in this way, n lower pi of c becomes the delta pi delta envelope of c. In other words, if you have an arbitrary category F in which arbitrary Dirac limits exist, a general category, then the category of functors from n pi c to f commuting with limits, Dirac limits, by those different functor becomes equivalent to the category of functors from c to f, which commute with limits of cardinality at most pi, to the kind of limits that we assume were in C. I mean, this is interesting when we pass to the dual situation, to the opposite categories, when with inverse limits, you see. I mean, of course, the dual statement is true. And then here we would have the data which we have considered in order to study algebraic structures that can be expressed in terms of arbitrary inverse limits. And here we would have algebraic structures that can be expressed in terms of inverse limits involving only indexing categories of cardinal at most pi. And we see that the objects in here that can be obtained as envelopes of objects in here are exactly those that are of the type n lower pi of C, where C is an object in, where C is a small category in here. I take small objects here. Namely, so exactly the categories that are pi accessible. And if we are interested in categories in here that are the envelope of some category, some delta pi for pi big enough, you find exactly the categories that are accessible. And now it's more or less intuitive to see that the categories that we get in delta from algebraic series. After algebraic series, I mean, we could make a constant argument. It would be pretty easy, but as I expressed stepwise by adding at each time with these small sets of data, it can be an algebraic series with respect to delta comes from algebraic series with respect to delta pi for some pi large enough. And therefore, the category that represents it would be the envelope of such a thing. And so passing over now to the opposite categories, that would mean that the category in question of the set-centric realizations of the structure we have in mind here is of the type n pi c for some c having pi Dieck limits. Or it amounts to the same, that it's an accessible category. So really, the point I want to make is that those categories are stable under inverse limits that correspond to algebraic series are exactly those for which R naught is accessible, namely those for which R is co-accessible. Now let me state, well, maybe we stop here. Tomorrow I will say some things about criteria for representability and co-representability on accessible spaces. It's kind of nice. It will ensure that all the functors we are considering between categories extending from algebraic structures definable by inverse limits, that these functors have adjoints always in both directions. Should I tell the story now, or let's leave it for tomorrow? All right. So let me. So there's one theorem which resumes the situation. So theorem that f from e to e prime be a functor where e and e prime are accessible categories. Then first the question of a right adjoint. F has a right adjoint if and only if. Maybe before, let's first state the symbol in terms of representativity of functors. And then this question about right adjoints and left adjoints is just a corollary. Maybe let E be an accessible category. And then first of all, if we have a continuant functor from E to sets, so it's good from E naught to sets, then F is representable if and only if it commutes with arbitrary inverse limits, small of course inverse limits, which just means that it transforms Dieck limits in E, that means inverse limits in E naught, into inverse limits in set. In sets, of course, it's inverse limits we should take. Now we know that if f is representable, then it commutes with inverse limits and transforms direct limits into inverse limits. And the opposite, in fact, is true whenever we have a category E which has arbitrary direct limits and which has a small generating category. You find this. So this is for much more general things than for accessible space. Just it has nothing to do with accessibility. So that's somewhere moved in SGA for 1 paragraph 8, I think 12 or number 12 or so. You see, I think it's fairly well known result. It just comes from the fact that there are direct limits. Well, I'm sorry, accessible, and there exist, we assume, arbitrary direct limits. Yes. Then, because in an accessible space there's a small generating category, it need not even be strictly generating. We know that constraint functors that are representable are just those which have this exact property. What is more interesting is the case of covariant functors. A functor on E two sets, let's say F, covariant is representable if and only if F satisfies two conditions. First, F commutes with arbitrary inverse limits, and second, F is accessible. In fact, what is proved in paragraph 8, I think number 13, where it's the last section on the paragraph on AND objects, is something slightly different. This corollary has not been made explicit, but what has been proved is that that the following conditions are equivalent. That F is, how should we say now? It's a covariant functor. So it's pro-representable. That means it can be, so to say, represented by a pro-object of E, but with a small indexing set, if and only if F is left exact. And accessible, that's what we prove there. Which is also an interesting result. But on the other hand, what does representable mean? It means that it's pro-representable and that it commutes with arbitrary inverse limits. So that's a little lemma that is given in the section 8.12. I mean, it's a very easy argument. If something is already pro-representable and if it commutes with arbitrary inverse limits, when arbitrary inverse limits exist in the category, which is the case here. Yeah, I forgot to say that in an accessible category, I mean in any category which has arbitrary direct limits, and in which there exists a small generating category, we have this criterion for representability, which implies that arbitrary inverse limits exist. Because the condition of representability of a functor here is stable under arbitrary inverse limits. And therefore, an arbitrary inverse limits of representable functor is representable. Alright, so arbitrary inverse limits exist already. And therefore, representability just means pro-representability plus the fact that it commutes with these functors. So in fact the problem is how to get a criterion of pro-representability. And a necessary condition, which is almost sufficient, is that the functor should be left exact, commute with finite inverse limits. Then we can pro-represent it perhaps, but by an inverse system which may not be small, you see, which may have too large a cardinal. And in order now to ensure that the cardinality of this is small, we have to write down that F is accessible. So that's the story. And in terms of adjoints, we see that F has a right adjoint if and only if it commutes with arbitrary direct limits. And second, F has a left adjoint if and only if it satisfies the two conditions of commuting with with arbitrary inverse limits, and it's moreover accessible. It's easy to give functors that commute with arbitrary Dieck limits on an accessible category, and that are not accessible, and therefore that are not representable. There's an example in the notes SGA. You take in the case of groups, for instance, you take first all simple groups. You know that we can find such simple groups for arbitrary high cardinality. Then you take all finite products of such groups and the inverse system they form, you see. And you look at the functor that is represented by this inverse system, co-represented, you see. It's an inverse system which is not really a co-object, at least not a small co-object, you see. Right. Now the functor it co-represents is really a small, its values are small, you see. Because for a given group, the cardinality of those simple groups which can map into it, you see, is bounded because the map is either which can map into it in a non-trivial way, right? And something that is not a unit map is bounded because these simple groups must be subgroups of it. So we have a function, and on the other hand, it's let's see. So it's a covariant functor, isn't it? And why does it commute? Yes. Why does it commute with arbitrary inverse limits? Is this clear? Yes, because you see this filtering system that we have, you see, it's large, it dominates any cardinal, whatever, you see. And therefore, taking this Dieck limit commutes with any type of projective limits, you see. That's all right. So this is a good example of a functor which is kind of pathological, you see. It cannot be described in finite terms, so to say, in small terms. And now if we come back to algebraic series, you see, we have seen that algebraic series, they correspond to categories R, algebraic series with respect to inverse limits. They correspond to series R that are co-accessible, namely doing error reversing. They correspond to categories S that are accessible. R is just a representing category in which the universal structure has its values, whereas S can be interpreted as being the set-centric realizations of the structure. For instance, if you take groups, for instance, S would be the category of all usual groups, and R is the opposite category in which we have the universal group. All right? And on the other hand, you have seen that if you have a category T, so it can be described either through R or through S. A homomorphism of T into T prime, we have seen, can be viewed as corresponding to homomorphism of R, to a functor from R prime into R, that is a delta functor that commutes with arbitrary inverse limits. So if you want to express it as a functor between S prime and S, if you just take the opposite functor, it's a functor from S prime into S that commutes with arbitrary Dieck limits. All right? And this such a functor has a right adjoint. And what is this right adjoint? If you just see what it means, it's just a functor which goes from T-ans to T prime, from T offsets to T prime offsets. It's a natural functor which associates, because of this homomorphism, to every set-theoretic realization of T, the corresponding set-theoretic realization of T prime. Therefore, equivalently, if you represent series by categories down here, you see, you can either give a description which is congruent with respect to the theory, and the arrows go in the reverse way. And here then you get here arbitrary functors from S prime to S that commute with Dieck limits, because they correspond to arbitrary functors here that commute with inverse limits. That these correspond exactly to all morphisms from T to T prime. But you can also give it the alternate description as being as S depending covariantly on T by taking here the adjoint functor which is in fact the most natural thing to do if you don't have all this universal algebra in mind. Well, if you have a functor from t to t, if you have a functor from t to t prime, it just maps t of sets into t prime of sets. If you have a functor which transforms groups into monoids, all right, it transforms usual groups into usual monoids, or such a thing. All right. But what are now the functors from S into S prime that can be viewed as being homomorphisms as corresponding to homomorphisms of series? These are, of course, exactly those which admit a left adjoint. Because, in fact, the left adjoints are the ones that we had to deal with first. And the left and right adjoint determine each other mutually. So what are the functors that have a left adjoint? They're exactly those, if we say here, that commute with arbitrary inverse limits and with no over which are accessible. So we know exactly what they are. So we have on the one hand accessible categories, you see, they express the structures through their central realizations. And on the other hand, homomorphisms between series correspond to homomorphisms to functors between these categories that first of all commute with arbitrary inverse limits. So nothing is said for the time being about how they behave with respect to direct limits. But then we have to add the non-pathological feature, namely that they should be accessible moreover. They should commute with direct limits, provided we take indexing sets I that are pi accessible for, that are dominating pi. So there's one thing more that is being done in the SGA notes, namely, and it's a considerable mess to prove there. I think it must be much simpler than that if one does the things right. It gives a stability theorem about accessibility of categories. It says that some categories constructed in terms of accessible categories are again accessible. So the situation was the following. One had an inverse system of categories Fi over some indexing category I. So it's what is called technically a fiber category F over I, and inverse image functors exist. But viewed as being an inverse system, maybe that's more intuitive. And we assume that the fiber categories Fi are accessible, and that the base change functors Fi goes to Fj are accessible too. And then the conclusion is that the inverse limit in the two category sense, the pseudo-inverse limit or whatever you call it, we have spoken of it a number of times, of the Fi's, which is just the category of Cartesian sections of F over I, is accessible. And in fact also, another byproduct, the set of all sections of the fiber category F over I, not necessarily Cartesian sections, is also accessible. So let's give an example, a particular case of the statement. Assume that the inverse system of the Fi's is constant. In other words, that F is just, that the fiber category is just I times the fixed category E. So this means that all the Fi's are isomorphic to the same E, and these transition morph functors are the identity functors, which certainly are accessible. All right. So we assume now that E is just an accessible category. And then our categories here, the second one is just the category of all functors from I into E. So we get that if E is an accessible category, the category of all functors from I to E, I has to be small, is accessible. And what is this category here? That's the category of all functors from I into E, which transform any arrow of I to an isomorphism. That's a full subcategory. Call it Tomikart if you want. Of I, of those functors from I into E, that transform any arrow into an isomorphism. But of course it can be interpreted as being, home. In fact, this is it would be a corollary of the previous statement, because this would be home of I tilde, where I tilde is the groupoid envelope of I in GE. So in fact, here the relevant statement would be this one. In the general case, these two categories, I don't think you can reduce one to the other. You see the idea of the proof, but it comes out very messy, because I think I didn't understand when I wrote down these things too well what the accessibility was. But the idea is very simple. If pi is a cardinal big enough, then first of all these fi's will be pi accessible. And therefore they can be interpreted in terms of fi lower pi as being n lower pi of these categories. And on the other hand, all of these functors will transform fi lower pi into fj lower pi, what we have said. Therefore, the situation can be entitled, and the functor from fi to fj is deduced from this one by just passing to n objects that are pi dominating. Therefore, the situation can be reconstructed in terms of a small situation. You see, like this here, by replacing the small fibers by n lower pi of these small fibers. And then what certainly should be true, I think a page or two should prove it without the dreadful constructions that I gave. I mean, I gave nearly 20 pages of proof in SGA. It looks really dismaying. But what should come out pretty easily is that when you look at the category of sections of this subcategory of F, whose fibers are just the pi-accessible objects in the FIs. And if you look at the category of sections, or Cartesian sections of F pi over I, that this is, of course, it's a small subcategory, and that this in fact is strictly generating. And in fact, that this is, how should I say, I mean, but in a kind of a canonical sense, a filtering sense, you see. What I want to prove is that, in fact, these subcategories are just the categories of pi-accessible objects in these here. In fact, not only was the proof I gave in SGA very messy and unpleasant and not at all comprehensive, but it didn't tell the true story, I think. The true story would be that for pi big enough, I mean, the pi-accessible objects in here and in there are just the sections of F pi over I. F pi, once again, are not the pi-accessible objects of F, but are those that are pi-accessible in the fibers. So that would be it. I think it should be kind of clear, yes it is clear, that any two Dieck limit, if E are accessible, with arbitrary Dieck limits at least, if you have a Dieck system of EIs, maybe you better assume, to feel safe, I will assume that the functors commute with Dieck limits. That then the two Dieck limits of these EIs is again accessible. I think that's true also if you don't assume the functors to be, I didn't check it, if you don't assume the functors to commute with Dieck limits, but only if the functors are accessible. But in the case when you assume them to commute with Dieck limits, I mean, this is clear in a kind of geometric way, because this corresponds to taking inverse limits of the algebraic series corresponding to the EIs. And this, of course, is an algebraic theory again. Do I say nonsense, or is it true or is it false? Let's see. What is clear geometrically is that there exists a Dieck limit in the category of all categories admitting arbitrary Dieck limits, and that this envelope will be accessible. But is it the same as if I took the Dieck limit? Yes, I think it is. I think it is clear. Because we have seen the thing. Haven't we? Let's see. No, I'm not too sure about it. So let's say it's just a question. I don't make any statement. Is it true that a Dieck limit in the category of all categories of accessible categories is accessible? The indexing category here, I, being small. I would think it is. You see, the one thing that makes me at ease is that I don't feel I'm not sure to have grasped really what an accessible category is, except when there are Dieck limits in it. And when they are not, I'm unhappy. On the other hand, you see, if you take here the Dieck limit of CIs, in the sense of the category cut, of the two-category cut, you see the usual big Dieck limit, capital L. Even if CIs have Dieck limits, and even if the transitional functors commute with these, it's not clear whether there will be Dieck limits in this category. Doesn't seem clear. Doesn't seem to be too clear to me. No, it is not true, you see, because take the sum of two categories which admit Dieck limits. You see, the sum of them will not admit Dieck limits. The sum in the category of categories, you see, is just a disjoint sum. And if you take an object in the one and an object in the other, it can't have a sum. So there's some difficulty, which is tied up to the fact that the last statements, structural statements about accessibility, I'm sure about them more or less only if there are limits. And so of the very basic notion of accessibility, I don't know what the right notion is if you don't assume that there are limits. I guess that the right notion is that these are categories which are two categories of this type. But then, all right, then this would make this statement. This would give a precise sense to the statement without assuming limits. But I'm not too sure. By the way, in this theorem, also when I hear reported about this theorem taking inverse limits of categories in SGA, I didn't make the assumption that these category Fi have arbitrary Dieck limits. You see. Therefore, possibly, I mean, you get all these intricacies in the proof. Perhaps from the fact that you didn't make this assumption, I don't know. Anyhow, I think that the situation is not too clear yet. I think it would deserve, to be cleared up. So I mean, it's a big mess now. These notes, I think, should be kind of cleared up. I think there should be should be able to tell the story, all the story together in 20 pages, including this film that takes 20 pages alone in SGA. All right, so maybe we go on tomorrow down 5.
Resume or something.
Maybe you will see. Why?
get that information, or you'll give it to me after?
So what about the stuff we made yesterday? Any comments or discussion or
Yeah, what was our, can we summarize exactly what the final conclusion was? The algebraic theories, those categories which could be described by means of an algebraic theory
yes.
were precisely those.
Yeah, all right. So the algebraic theories.
And what was the, and let me get straight to the what we defined as the actual definition of our requirement for what was going to be algebraic. Okay.
Yeah, a series is algebraic if we can obtain it by a stepwise construction in which at each step either we add a small number of arrows or a small number of axioms. These axioms being that some arrows are isomorphisms and some pairs of arrows are equal. And we start with a small set of base objects. And we allow ourselves, on the other hand, we allow ourselves to add together a small set of structures that we have already on some base objects to take the conjunction of these. And so whatever we can get in this way by making a transfinite construction, if necessary, we'll call an algebraic structure. And now something which is true, whatever the delta we started with, practically, assuming that problem 1 and 2 has a mathematical solution. And it helps if we take the delta defined by arbitrary inverse limits. It's that algebraic series are representable. So certainly, our series T will be represented by categories R, which will carry the universal representative of the structure. And of course, the correspondence between T and R goes in the two directions, except that it's arrow reversing. Morphisms from T to T prime correspond to functors compatible with the limits, the inverse limits of R prime to R, in the opposite direction. Now the question is, what are the R's that occur? Call them algebraic if you want. Delta algebraic, we would call them then. Delta is the subcategory of cut that corresponds to taking all inverse limits in functors that can reduce them. All right. As we have more or less seen, I didn't give a proof, but I think it comes out kind of rather clearly, self-intuitive, and I'm pretty sure. I mean, it's really true that these are the categories which I would call co-accessible, namely such that the dual categories S are accessible. Now, before speaking of the when we take series that are represented by R's, but not necessarily algebraic R's, so the series may not be necessarily algebraic, then there's some more interest for those R's which admit a small subcategory which is strictly co-generating, which would mean that in S we have a small subcategory which is strictly generating, which would mean in S that every object of S is a direct limit for some suitable diagram of objects of the subcategory. Now, if R is such a category, so it's something more general than just algebraic, then any functor which goes from R to sets and which commutes with arbitrary inverse limits is representable. I mean, dually, this means that the complement functor on S to sets that commutes, that transforms direct limits into inverse limits is representable. That's a well-known theorem. Which means that if you look at the theory represented by R, and if you look at the set-theoretic realizations of this, they make up a category which is equivalent to S, because it consists exactly of the representable functors, and some representable functors are the representable opposite to R, so it's just. Alright. Therefore, we see that in this case, the theory TR, the representative theory, is completely known when we know the category of its set-theoretical realizations. Now, this is true even for non-algebraic theories, for theories that are just representable by R's that have small sets of small co-generating sets. And now, what about morphisms between theories? They correspond to arbitrary functors from R prime to R that commute with arbitrary inverse limits in the opposite direction. Of course, what we're really interested in is not this homomorphism, but it's the functor from T to T prime. And such a functor from T to T prime for U upper star, so functor which goes in the opposite direction here. What we are really interested in is U lower C from TC to T prime C for every C, and for instance we want to know what it is for TRs. What it deduces on structures of type T and T prime in the category of sets. Now TRs and T prime Rs, that's just the opposite categories to R and R prime, that's just S and S prime. So we get a functor from S to S prime, and of course this functor will just be the left adjoint. So we rather put this above the other of this functor for a 2 star. So in fact, homomorphism between categories, just as the categories are between theories, I'm sorry, just as the theories themselves are defined completely when we know its values on sets, also it's true that the functors between these theories are determined when we know its values for sets, because once we know this functor here, we know U upper star, which is just its right adjoint. You see. Now the advantage of taking this arrow rather than this one is that it goes into the same direction as series is, that S depends squarely on T and not frequently like R. But now the question is, what are the functors from S to S prime that correspond to homomorphisms of series? They are of course the functors that admit right adjoints, because they are exactly the left adjoints of functors that commute with inverse limits. But if a functor is a right adjoint, it must necessarily commute to inverse limits. So I mean, it's clear therefore that we get exactly the functors from S to S prime that admit right adjoints. And of course, these functors necessarily must commute with arbitrary direct limits. I'm sorry, here would be inverse limits. I mean, when we are speaking of S and S prime. So this would be here functors that commute with arbitrary inverse limits. But this condition is not quite enough. We must moreover insist that they should be accessible, because between now let's say coming back now to the case when our series are algebraic, then one can give a necessary and sufficient criterion for an U lower star to have such an adjoint. And it is precisely that U lower star not only should commute with arbitrary inverse limits, but also that it should be accessible. So I mean, it's kind of nice in the context of algebraic series, that means of accessible categories S and S prime. What is kind of nice, for instance, is that we can completely characterize the functors from S to S prime, which correspond to morphisms of algebraic series, which I wouldn't be able to do otherwise. So if I have a morphism from S into S prime that just commutes with inverse limits, here, well, it wouldn't correspond to a morphism of series. And I gave you an example. When S is the category of groups and S prime is the category of sets, therefore the structure here is a structure of groups, and this structure is an empty structure on an object. Well, I gave an example of such a functor that commutes with inverse limits, but that isn't accessible. So it doesn't correspond to a morphism of series, at least not in our sense. And it's in no reasonable sense, I think, because really we should have this map, of course, it should be a morphism of series. Now, this error, of course, is pretty clear. Its interpretation is pretty clear in terms of the series. I mean, if you have a homophone of series, it's something, for instance, that associates to every monoid a group, for instance, the enveloping group of a monoid. All right, I mean, it associates to every usual monoid, a set-sorting monoid, a set-sorting group. So this is the meaning of this arrow. What now is the meaning of the arrow that goes in the other way? We can, of course, view it passing to the opposite of it, u upper star naught, as an arrow going from S prime to S. That's something that goes with three structures. You see, it would be something like, quite precisely, which the function in the opposite direction, which associates to every monoid the enveloping group, for instance. I mean, it's the, what should we call it, the free structure with respect to the pair, this free group structure with respect to the pair monoids groups generated by a given monoid. It's just an adjoint, you see, of this here. So in this situation, you see the adjoints of these functions always will exist, if necessarily, these free structures. Of course, the most common case is the one when we have S prime sets or sets to a certain power, where this functor is a functor which associates to every structure of a given type. The underlying sets, set or sets, if there are several objects, and then this here is really what is called the free structure. Perhaps I should say something about the case when this functor here is fully faithful, when S can be identified to a full subcategory of S prime. What does it mean that a functor is fully faithful when the functor admits an adjoint? Here it would be this or this one here, when we reverse the arrows. It just means that the adjoint is a localization functor, is a functor of passage to a category of fractions. That's the general result about the case of adjoint functors. And on the other hand, we have seen in our stepwise construction of the theory, in this particular case, that adding arrows, I mean passing to a localized category, just means that we have added axioms. So here the subseries which correspond to most of the functors, which are full embeddings, are just those which you obtain from a given theory T prime by adding a bunch of more axioms, but without any need to add any more arrows. And in fact, one has a one-to-one correspondence that's pretty easy to check. If a theory T prime is given between a subseries T of T prime, namely functors T goes to T prime, which define here a fully faithful functor, and of course this implies that for every C, TC goes to T prime C will be fully faithful. So these subcategories correspond to all possible quotient categories of R, such that in R there exist inverse limits and this functor commutes with the inverse limits, which means quotient category of R prime, where the set of arrows sigma prime by which we pass to the quotient is stable under inverse limits. So in fact, subcategories just correspond, a subseries, full subseries just correspond to such sets of arrows in R prime. And they're embodied, of course, they're kind of a dual correspondence with subcategories F of S prime that are full subcategories and which virtue, which are stable under inverse limits. But I'm sorry, yes, when I spoke of sub-series here, I didn't care too much whether the series we were speaking of were algebraic or not, just series. Let's say representable series. But All right. So then these would correspond either to such systems of arrows, or here to full subcategories such that are stable under arbitrary inverse limits, and such as the inclusion admits left adjoint. Now, if we are working with algebraic series, you see, then we should insist that this set of arrows, sigma prime, should be generated by a subset of arrows that is small, generated with respect to arbitrary inverse limit operations. Namely, it's the number of axioms we add, you see, should be small. And for this subcategory, if we could express things in terms of this subcategory, we should insist. Now, how should we say it? Is it enough to say so it should be a subcategory stable by inverse limits? That's one point. And I think we have to say the whole story, and S should be accessible. And the inclusion functor should be accessible, I think. We have to add all this, I think. Assume we say only in which case there will be an adjoint on the right, on the left side here. But assume only that there's an adjoint, let's say. Assume that S is stable under inverse limits and that the inclusion has an adjoint. So, which in fact, all right here, which will not imply perhaps by itself that S is stable under inverse limits, because they may not exist in S. All right, now assume this, then because S prime has a small family of generators, S will have a small family of generators, namely the images of the generators here will make generators there. That's all right. And I guess there will be even strict generators. This shouldn't make a difficulty. But is it clear? It's not clear, you see, that these generators in S will be accessible in S, even being accessible in S prime. You see, because commuting with certain types of Dirac limits in S or in S prime is not the same unless we know that these types of Dirac limits are the same. That's what it seems to me, but I didn't really make a counterexample, but it seems to me that one has to add something. It's not clear at all that any subcategory that is stable under inverse limits and that such that the inclusion admits and left adjoint, it's not at all clear that this S will be accessible. Can you make out a counterexample perhaps? Well, let's say, can't these structures which you said, these Boole sets are not be embedded in an S prime, which is accessible? Is Isabel going to come, you think?
Who?
Isabel?
Ismail, I don't know, he might have had to go somewhere. I haven't seen him but very briefly today this morning. I imagine he would be here if he was coming right now.
All right, so we start there. So I'd like to make a few comments we discussed so far and give a few compliments. So we have this two-category data sitting in the cat associated to a pair of sets of diagrams. So these categories admit limits of inverse limits of type t prime and of type t second. And the functors that we are considering between them commute with these types of limits, but there may be some extra exactness properties. And then we define stepwise, first we define what was series relative to delta R. They are just pseudo-functors going from delta to categories. So if T is a series, it associates to every C and delta at TC, but in a two-functorial way. So the series, the delta, series over delta, they make up a two-category, and within this two-category, we have distinguished the two subcategory of algebraic series, or the tal, if you want, by delta, which we have defined inductively by step-by-step constructions. Maybe I was a little inaccurate when stating the last step, which involves the passing to limit, because I more or less assumed that we wouldn't really have to pass to the limit, and now it seems to me there was a little rush in this. The few examples which I had looked up, more than, there didn't seem to need a passage to limit, but in general case one may have to need it. And therefore, the step T would be the following: if we have series T alpha over tau to the I, so the space objects, which form a filtering system, inverse system of series over tau to the I. That would be enough. Any system, in fact, would do. Let's see. Yes. Then we will have these series being algebraic with space, with base data I. Then if we look at the inverse limit in the two-category sense within delta of the T alphas, which lies what tau I is also I want to be an algebraic series. I think this is equivalent to saying that the two-fiber product of an arbitrary number of algebraic series over tau to the I acting as a base set, for each of them is an algebraic series with I as base set. So we definitely want something at least as strong as that. Now, the main problem which we have left kind of undecided, besides the problem number 1 and 2 about the solution of some universal problems, was characterizations of algebraic series as being the representable ones. Let's say that we have within series shortly we have the representable series. Call this representable series. So here this is again a two-fold subcategory, which is equivalent as a two-category to the opposite of the category delta by associating to every object R and delta. The series is two represents. And here the algebraic series were two representable. So they were representable by what one could call categories and delta, objects of delta, which we would call perhaps algebraic objects. So here, this is a situation which we have. The algebraic series can be identified to be opposites, so to say, of objects of delta, which, however, should have a special property which resembles to having a set of small family of generators, and this we would have to make precise. In fact, what we have to assume is, for such an R, I mean, the characteristic property is the following: there should exist an discrete category I and a morphism of this discrete category I into R within cat. In such a way that R can be deduced from I by a transfinite sequence of categories R alpha, which is defined in the following way, step by step. R naught, R alpha, R and delta, and lie over R with functors here with delta functors. And they are constructed in the following way. R naught would be equal to I tilde to the delta envelope of I. If you have an ordinal which is a successor, I alpha plus 1 could be deducible from R alpha by constructions A or B. I'm sorry, B or C, by constructions B or C. I recall that construction B was making a bunch of arrows invertible, or making a bunch of pairs of arrows, or equalizing a bunch of pairs of arrows within delta. We have an object of delta, we have a category, we have a bunch of arrows in this category, and we want to make them invertible university in delta. And the same with pairs of arrows. And for C it was just adding a bunch of arrows. This is a well-defined construction within the category delta. Both these three constructions, the two first in fact are very much related, and the third is for other different type, adding arrows. So remember that when we interpreted things in terms of operations on series, this B consists of adding axioms, and C consists in adding data, namely as new arrows being added. So, and on the other hand, R alpha, if alpha is a limiting ordinal, should be the two-Dirac limit of all R betas for beta smaller than alpha. And of course, that's it. And moreover, we should get that R alpha should be equivalent to R for alpha big enough, but alpha of course being in our universe we're working with big enough. So that's in fact, if we just look at the letter, the description what we defined in algebraic theory based on I, this is what it would correspond to. That's just the interpretation of it. And now we wonder if you have R in delta, and if you have a functor from a discrete category into R, can we give simpler ways of expressing the fact that R is the abutment of such a transfinite system of objects of delta. And really so what I had hoped for was that saying that we have just faithfulness for home underlined R, C in delta to home IC to C to the I, that the mere faithfulness will suffice. I mean, Israel has shown by pretty convincing example that this is not so. Now there remains another intuition, which I hope will be correct, namely that it just means that I in a certain way degenerates R with respect to the operations defined in second. So the main question here in this connection which remains is, if we assume that problem 1 and problem 2 have been solved, so what, let's say this would be problem 3, whether it's true that the existence of such a transfinite construction leading from I to R, if this is equivalent to saying that for every strictly full subcategory R prime in R, which is stable under which is in delta, that would be in which was. But I want also that the inclusion should be a factor in delta. So let's say stable under D limits. This is the same thing as to say that R prime is in delta, that the inclusion factor is in delta. Such that I goes to R factors to R prime, that is containing the essential image of I. We have R prime equals R. Now this just means the following, this condition, that if starting with the full subcategory of R generated by I, we start saturating it with respect to limit operations of type D prime into second, adding to it limits of type D prime into second in order to get a new full subcategory, call it I1 of R, and doing this transiently so that I alpha plus 1 would be what you deduce from I alpha by adding limits of type D to I alpha, and I alpha for alpha and limit ordinal would be just the union of all previous I betas. Then what we say here is pretty trivial, that it's equivalent to saying that this transient construction finally ends up with R. And that would mean that R is generated by D limits, so inverse limits of type D prime, like this at type D second, by the image of I in R. But I haven't proved it in either way. I haven't even proved, I didn't really try hard, I must say. Looked a little bit yesterday. Whether this implies this. I'm pretty much convinced it should come out. The other implication maybe this perhaps is easy to prove. The other implication may be harder. I hope it's true. This would be kind of nice. So this would be really the natural notion of I generating delta, of I generating R in the sense of the operations that we allow ourselves. Of course, this is, I think, the main problem which remains open in this general theory. Of course, we can also ask a question for given R, not caring about I, when is R algebraic? Maybe when does there exist such a functor I goes to R, which has the property stated here, which perhaps I equivalent to the property stated here. Now, this question doesn't really arise, I think, if both D prime and D second are essentially small. If the isomorphism class of diagrams of D prime from a small set and the same for D second. Because in this case, I think the R's in question will just be the small R's. Because in this transfinite construction, granting at least that the universal solutions to our problem 1 and 2 take the enveloping delta category of a category and making arrows invertible or equalizing arrows. That if we start with small things, we wind up with small things, which is hard to doubt, you see. At least in those examples where I can construct these solutions, it is true. If we admit this, then there's this transfinite construction. All the R alphas will be small, and therefore R will be small. Therefore, algebraic objects of data must be small, and we have already seen the converse. Small ones always will work because we take I to be equal to the set of all objects of R. Alright, so this problem of characterizing the R's really arises only if either D prime or D second is not essentially small. If they both have different number of isomorphism classes. A non-small number of isomorphism classes of diagrams. But if we are dealing only with Dirac limits and inverse limits by diagrams whose cardinality is limited, that would be no problem. But if we take diagrams of arbitrarily high cardinal element of the universe, then we will have problems to to characterize the R's that are algebraic. Another remark is the following. When we keep adding arrows like this, you see, I mean, after all, the number of steps in this operation is it's a small number. I want to say it's cardinality. It's cardinality is the element of the universe. So among these passages from alpha to alpha plus 1, they're either just adding axioms or adding new data, and then adding arrows. Now, adding arrows, you see, we do it every time we add a bunch of arrows, which is a small bunch, I mean, which is whose cardinals again small. And we do this a small number of times. And therefore all the arrows which we have ultimately added in the process, you see, will be small. And therefore, if we now look at the corresponding arrows in R, you see, finally, there's a small bunch of arrows that appear. And if we look at the sources and the targets of these, I mean, a good choice would be to look at what happens if we enlarge I to contain also these sub-objects, these objects in R. See, I think it will be still more generating than before. I mean, I think that the larger the set of objects you have in R, the more readily it will be true that I goes to R generates in the sense said here, although I didn't even prove that. It's kind of intuitive, but I didn't prove it, I guess. All right, so what I think is the following, that we can always, if R is algebraic, we can always find an I going to R with I big enough, so that in the corresponding transfinite construction, we have no longer to add any arrows, but only to add axioms. Which would mean that if you look at the full subcategory of R defined by this here, call it I prime, so that in fact we have a function which goes from I prime tilde to R. And let's look at the theory represented by I prime tilde, which transforms C into from underlined with in cat of I prime to C, which is also the more underlined with in delta of I prime tilde into C. See? All right, that TR being viewed as being mapped into Ti prime tilde will, I would think, be fully faithful now. That is, we can view the algebraic theory here as being a sub-theory, you see, full subfunctor, argument-wise for every C, of the algebraic theory defined in this very simple way. This algebraic theory here can be constructed in three steps, from just first taking the discrete set I, that's step A, you see, then adding arrows, that's step C, then writing that some composite terms are equal to some others, that's step B, and these together give us this algebraic theory. So that's a finite number of operations. But then this here, I don't know if a fully faithful subcategory like sub-theory like this, which should be obtained by adding axioms a certain number of times, perhaps constantly many times, if it can be done in a finite number of steps. I mean, in the examples which I've looked at, it can. What may be is that you have still to make this construction, where every time alpha plus 1 is reduced from alpha by construction B. You see, what will happen is that once you add some more axioms, that certain arrows are invertible and that certain other arrows, let's say pairs of arrows, become equal, this will allow us to construct a lot more arrows. You see, by taking inverses, composing, etc. I mean, by using existence terms that use this axiom. So we may be able to construct a lot more arrows. That means that from taking R alpha, you see, and making invertible some arrows and equalizing some others, we get and R alpha plus 1 equals, for instance, R alpha sigma minus 1, something like this. You see? But this functor here can well be not surjective on objects and not surjective neither on the arrows, I mean, for two given objects here. Because we can also, having new arrows, you see, we can construct also new objects by taking limiting operations, taking private products and underlined sums and the like. And therefore this will allow us to write other axioms here, you see, which we couldn't have written there. So what is possible is that we might still have to take a transfer system. We may still have to take a transfer system here. But what will happen is that at every time going from R alpha to R alpha plus 1 is something like a localization process. It corresponds to a morphism for this corresponding series T alpha plus 1 mapped to T alpha, that's it. This being fully faithful, which is kind of a special situation. So there are a few things you see to clear up, which are kind of obscure yet. There's another problem also, which I really have no feeling if one can hope for a satisfactory solution. Let's assume that everything has been, that this really, as we have described it so far, has been nice, has been geared up nicely, so that we have two things that are defined differently and which finally happen to coincide. On the one hand, algebraic series constructed stepwise, and on the other hand, objects that two represent that are just objects of data satisfying some mild extra condition of fineness kind that are kind of small or smallly generated. But when we have a theory, you see, we may try to have intrinsic conditions on T which are not existential, not there exists a transmit sequence such that, or there exists an object that 2 represents it. Which internal properties of T that will ensure that it's algebraic, or that it's 2 representable, let's say. Now let's take for instance 2 representability. Do we have a criterion for a theory T to be 2 representable? Now, there are a number of necessary conditions of 2 representability, which are general conditions in any 2 category. Of course, if we have an ordinary category and we have a functor from these 2 sets, and we wonder if it's representable, I mean, we have some necessary conditions, for instance, the functor being covariant here should commute with arbitrary inverse limits. So that's an important condition. And in the case when this category they're working in admits a small family of cogenerators, this condition, and if it has arbitrary inverse limits, small inverse limits, then this condition is also sufficient for representability. See, that's a well-known theorem of category theory. Now here, one can also write as a first necessary condition that the theory T should commute with 2 inverse limits. Namely, if we have a 2 inverse limit of categories C alpha, call them Ci rather, perhaps, then T of this is the equivalent to the 2 inverse limit of T of Ci by the natural functor between the 2. So that's a pretty strong condition, of course, on a theory. Maybe it's kind of close, you see. If you take the undergone of usual categories, you see functors that have this property, covariant functors that commute with arbitrary inverse limits, assuming that arbitrary inverse limits exist. They are pro-representable by an inverse system. The only trouble which may make it non-representable is that this inverse system may have a cardinality that is not in the universe. You see, but they are very close to representable functor. They are pro-represented by an inverse system of objects. And so here should be something, at least something like this. There's also another condition which is necessary, which is kind of special. Maybe it's a formal consequence of this. It's possible. But let me state it separately. First, this B, if C goes to C prime is a function within delta, is a delta function such that U is faithful or fully faithful, then T of U, which goes from TC to TC prime, is also faithful or fully faithful. So that's pretty evident because Hom underlined delta of RC goes to Hom underlined delta RC prime, you see, which is induced by the corresponding functor from Hom RC to Hom RC prime. I mean, this will be, of course, faithful or fully faithful. Of course, if C goes to C prime is an equivalence, then it's always true whether T is true representable or not, that TC goes to TC prime is an equivalence. So, as I hope to get a characterization at least of two representable functors this way, and then if you want a calculation of the algebraic ones, algebraic series, then we should impose some kind of finiteness condition on the R that 2 represents it, which would be kind of a little bit subtler. So I don't really know. You see in this category delta, there is nothing that there is something that resembles a generator, namely the I tilde, where I is a one-point category. But I don't see anything that resembles cogenerators. So I'm not sure one can paraphrase the criteria of representativity we have in the case of usual categories. One more comment about exactness properties. So, exactness properties for a given pair D equals D prime D second were defined by just taking delta lower D. It's the first step. The category that admits the limits of type D and counters that commute with these. Delta will be defined as being contained in it by these extra conditions. And what we did was to take some categories R and delta D and a bunch of arrows, for instance, sigma, and to take as a exactness property on an arbitrary category in delta D, C, that for every functor, delta D functor from R to C, every functor that commutes with these limits, the image of any object of sigma should be an isomorphism. And also, instead of this, we could have a bunch, sigma prime of pairs of arrows, and we should demand that these should be equalized by any functor that commutes with these types of limits. I think we should allow for both. Now, if you look at the universal construction within delta D, which either makes sigma invertible or which equalizes sigma prime, so we get number from R goes to R prime, then our condition just means that the corresponding functor, a condition on C now, it's the next condition, which goes from Hom delta R prime C to Hom delta, delta D RC by composition, should be an equivalence of categories. So it can be therefore expressed intrinsically in terms of a given functor from an R to an R prime as a maximum of this type. Now, why not take so-called generalized exactness properties? This was, I think, the suggestion of John Duskin, by just giving ourselves some functor R goes to R prime within delta D, and the exactness property will just be that for a given C that this functor here should be an equivalence. And we can, in the same way, take other types of generalized exactness properties by demanding that this functor should be fully faithful or faithful. So this gives us more general ways of describing deltas within delta D's by such types of conditions. Of course, we can iterate the process. Now, what makes me feel that this is although this doesn't correspond to the usual types of usual exactness properties, which are of a more special type, but which convinces me that it's kind of a good condition is that what I have said so far about stability of delta under various operations makes still a good sense if you take these deltas which are defined by these more generalized exactness properties. For instance, that delta is stable under two inverse limits within cut will be true, and a few other things of this type will be true. So it seems kind of a good type of condition. So perhaps the categories obtained in this way, or by iterating, or obtained by iterating such kind of processes transiently, maybe they all admit affirmative solutions to problem 1 and 2, and they admit corresponding theory of algebraic structures. I don't know. I think that ultimately, if one really works these things out, the properties should be, the finite two-state should be intrinsic properties to delta in order to make this field work. So that, for instance, some pretty properties that are pretty simple to check for the categories yet considered so far, which will imply that problem 1 and problem 2 have a solution, and which will imply something about our problem about these transfer sequences that we have just raised, or generation. So, so there's a lot of problems that occur. So some more. Yes, let's give some example perhaps.
Yes.
To this effect. Let's take really the most simplest that comes to mind. Let's take D equals empty. Maybe D prime equals empty. Maybe C equals empty. So delta D then would be just all categories. And in a minute, we will see that problem 1 and problem 2 have a solution. But let's look now at subcategories delta that we can consider in there by exactness properties. Now, if we take the usual exactness properties, I don't see much choices. I see one interesting subcategory by looking at this category here, the category of the one simplex, two objects and just one arrow between them, with not counting the identity morphisms. So that's the category, that would be our category R, and we want that this arrow should become an isomorphism. Now, what is a morphism from R into an arbitrary object of delta D in an arbitrary category? It's just to give an arrow within this category. And the exactness property is that every arrow should be invertible, namely that C are groupoids. Therefore, a first choice here is groupoids. So that's a usual exactness property. But let's take one which wouldn't fit into what we first, at the very first state as exactness property. Let's take this diagram now. And let's equalize these arrows. Let's make an exactness property that these two arrows should become equal through diagrams of this type in the category C. Now, what is a diagram of this type in the category C? It's just two objects, x and y, and the double arrow between them. And this exact property says that two arrows going from one object to another should be equal. That means that the category is ordered. So if we admit this type of exact property, we will get ordered categories. Now this is good. Yes.
We could still have arrows going from one object to the other and also backwards. Even while this condition is satisfied, we could have an arrow from A to B as well as from B to A.
Not in this diagram, but in the category, of course. But this would mean that the two. That would mean that we have a category. But this would mean that the two objects are isomorphic. You see, if you have a category in which there's at most one arrow from x to y, if there's a one from y to x, the composite term is a unique endomorphism of x, which is identity, and the same for y, which if we compose it the other way around. So in such a category, we can have x dominates y and y dominates x only if x is isomorphic to y. So in fact, these are the pre-ordered categories. You see, they correspond really. The category of these categories is in fact isomorphic to the category of pre-ordered sets. And it's 2 equivalent to the category of ordered sets. All right. So we have a delta prime here. You see, and it's kind of nice, this category of. I mean, these are really now the first special type of categories one thinks of. They are groupoids and pre-ordered categories. They are kind of opposite. So, things that are both of them are the discrete groupoids that are just discrete categories. It's a category of those. So that's again a discrete categories. The category of all discrete categories is equivalent to the category is 2 equivalent to what should I say? The 2 category. Yeah. It's 2 equivalent to the category of sets. Because a discrete category. When you take the isomorphism classes of objects, it's just equivalent to discrete. Can be defined by the set. It's equivalent by a equivalence that is determined up to unique isomorphism. All right. So these things generally one wouldn't, with respect to my first definition, I wouldn't have considered as being defined by exactness properties. But it's kind of nice to use them as being defined by generalized exactness properties. Maybe, as we are already looking at these examples, what about problems 1 and 2 for all of these cases?
Yes.
Now, let's first take here all categories. So, first, problem number 1 was to find the enveloping category of a category I. And of course, I tilde here is equal to I. That's actuality. A universal way of mapping I into a delta category, but a delta category is just a category. Take I again. Problem 2, we have a category I and we have a bunch of arrows in I and we want to make them invertible. But this is a well-known construction. That's a category of fractions, I sigma minus 1, which is explained at length, for instance, in Gabriel Ziesmann's book on motorik theory. It's quite an important, quite a useful construction. And of course, also we have as a variant of now as making arrows invertible, but this we know already is deduced from the solution to problem 1 and 2 either. So it was making arrows invertible. So they have solutions. Now what about groupoids? So this is delta D. What about delta? Groupoids. What about problem 1? We want to we have a category I, and we want a universal way of mapping I into a groupoid. Now this is well known that we can do this. It's the so-called fundamental groupoid of a category. The connected components of the groupoid are just the connected component of the category. And the fundamental groups of the various connected components are just what one should call the fundamental group of the category I or of the underlying I would think semi-symmetrical set is true.
Yeah.
All right. So this is a random construction. What about problem number 2? In the group we want to make some errors invertible. All right, they're already invertible.
Isn't, as a matter of fact, in the second case, in problem 1, this is an example of a problem of problem 2 applied to a category where the set sigma is all the errors. If you want to associate the
yes.
category to the group line, and then you
Yes,
just
yeah.
invert all the errors.
That's true, yeah. But what has to prove, of course, that then if you take all errors in the category I, that then the category I sigma minus 1 is a group polynomial. This requires a slight proof, I would think.
Yes, you're right. Yeah.
But anyhow,
Yeah.
this would be pretty trivial. All right. So yeah, that's, I think, it's a nice way to say it. So anyhow, I mean, that's a construction. One can do otherwise. All right. Now, what if you have already a category which is group with C sigma minus 1, it's just C. All right. Now what about delta prime? So we take now ordered categories, and if we have any category I, and we want in a universal way to map it into an ordered category, I tilde, and what we take is to take as underlying set of I tilde equals of I, and what will we take as pre-order, it's the pre-order of domination. We'll say that X dominates Y if there exists at least one error from X into Y, which is a pre-order relation. And then it's pretty clear that there is a functor which from I into I tilde, and it's universal. And this again is a pretty useful functor. I mean, one, sometimes without making it explicit, one uses it quite often in a way. We have certainly used it in some of our courses here. And what about problem 2? So this would mean that we have already a pre-ordered category C, which is essentially a pre-ordered set. And in this pre-ordered set, we have some errors, that is, we have some inequalities x, I contained in yi, and we want to make them into isomorphisms. All right, I guess I haven't really met with this problem before, but it's pretty clear that there exists a universal solution to this within the category of pre-ordered sets.
I think so, yeah. What do we want to do again? We want to make, this is for
We have
pre-ordered sets.
errors, maybe we have inequalities like this, and we want to make them into isomorphism, and we want
So
also that
the
yi should be.
equivalence relation, yeah.
Yeah.
That's all.
So as we are concerned only with categories up to equivalence, we first pass, if we want to corresponding ordered set by passing, to the quotient by the equivalence relation defined by the order, and then so we work with ordered sets throughout only, and then we pass to quotient by the equivalence relation generated by xi equals y, yi. Let's say xi equals yi. We take the equivalence relation generated by this, I mean the smallest equivalence relation, that's it, finest equivalence relation, for which these equivalences hold and which is compatible with the order structure. Like this. And you pass to quotient by this. That's pretty clear. And what about discrete categories? Well, I didn't look. But delta intersects delta prime, so discrete categories. So what about problem 1? How can one, what is the mapping from an arbitrary category to a discrete one? I think one takes a discrete category defined by the set of connected components of I would say. So I tilde would just be pi naught of I. Discrete categories I identify up to equivalence with just sets. So I tilde would be pi naught of I. And what about problem number 2? I have a discrete category. I want to make some errors invertible. Never mind the error invertible. They're just identities. So C sigma minus 1 equals C. So here everything is all right. I didn't try to find many other examples of generalized exactness properties on categories.
May I re-clarify something about it? How did you define problem 2 again? What was problem 2? You have
You have
where was
an object in delta,
Object is in delta,
and you have a subset
in delta, okay.
of the.
Both cases you're just in delta and you just want to invert that back in
Yes.
delta.
Yeah, I want to find the universal way of mapping C into a category D
In B in delta,
within delta,
and delta, no,
the
delta
delta
map.
functor,
Right.
which makes the arrows of sigma
Right.
inverted. Alright, so here, I don't know if you can find many other fancy examples of categories of conditional categories, which are exactness conditions with D was empty. You see, I took the first that came to mind here, but maybe as the most important one. But of course, take any functor between two categories, C goes to C prime, let's say, or let's rather with our conditional cases, R goes to R prime, and then we have as an exactness property that homoline R prime C goes to homoline R C should be an equals of category. Right? I don't know if for such an exactness condition, if problem 1 and problem 2 has a solution, it will be kind of nice if we just look up this case already. Just very kind of explicit. Now I want to say something about existence of limits in categories of the type TC. So let T be a theory which is representable. So T equals TR, R being an object of delta. So TC is just from underline over delta of RC. And so a comment I want to make about the existence of type delta. Let delta be a diagram. Okay. And let's assume we are interested in inverse limits. By dualizing, we will say we'll get the same thing for direct limits. We're interested in inverse limits of type delta in TC, the one that they exist, and how they can be computed. And we make the assumption that A with direct limits of type d seconds, the type of direct limits that are being considered within delta. Delta, if you recall, is associated to a d in our setup. D is d prime d second. So, under these conditions, we have the existence of inverse limits of type delta in TC, and in fact they can be computed component-wise. They are computed when we interpret TC as being a category of functors from R to C. Certain functors, they are computed argument-wise. So the proof is pretty clear. I think that's really that's the only statement I know. I think it kind of contains all other statements I know of existence of limits. Let's look. We know already that in the category home underlined in cat of RC, if a certain type of limit exists in C, type, that's the inverse limits of type delta, the same is true in this category. So in order to prove that it exists, and it's computed component-wise, so all we have to prove is that taking these types of limits doesn't take us out of this subcategory. So we have to prove that if we have functors phi I epsilon opt delta, if you have an inverse system of functors phi I in here, parameterized by delta, that means functors from R to C that commute with limits of type D, then the inverse limit the phi i's computed in here, and they will compute component-wise, let's say phi, again, commutes with limits of type d prime and d second. But it's clear for limits of type d prime for inverse limits, because imposing property of commutation to some type of inverse limits to a functor that's stable under taking inverse limits of an arbitrary type of inverse limits. And it's also true for this here, because we assumed that NC, the direct limits of type D second, commute with inverse limits of type delta. We will write down, which comes out. Moreover, we see as a consequence that if T goes to T prime is a homomorphism of representable series, then Tc goes to T prime C will commute with the inverse limits of type delta C, satisfying still the same conditions here. And the same if C and C prime both satisfy the conditions which we have set with respect to delta. And if we have a functor from C to C prime that commutes with limits of type delta, but if delta itself is in D prime, then any delta function, capital delta functor, will have this property. Then the corresponding functor from Tc to Tc prime will commute with these types of limits, with inverse limits of type delta, small delta. The fact that these limits are computed argument-wise when we interpret T of C as being functors from R to C delta functors can be also expressed by saying the following: for every R object of R, namely for every construction relative to the theory, if I interpret R lower C as being the corresponding functor from Tc to C, this functor commutes with inverse limits of type delta. Now there are cases, you see, when there doesn't exist any type of limits in the TCs. You shouldn't believe that whenever you have a cache of structures corresponding to a cache with C which has many types of limits, that in TC there shouldn't be any type of limit at all. And the conditions I put are in a way kind of stringent. Take, for instance, category of torsors under a fixed group or such a thing. You see that there are no sums, there are no products. There is nothing like this. There is no final object, there is no initial object. There are just only the limits exist which exist trivially. I mean, by a like system which is trivial, which is constant. Essentially constant. That's all. But let's give an example, for instance. Let's assume that D second is empty. So no consideration of Dieck limits at all. So we are looking at algebraic structures that are associated with the existence only of some types of inverse limits. Then this condition here, condition B, becomes empty. And on the other hand, as before, the assumption that limits of type delta exist in C is certainly satisfied if we assume that delta itself belongs to D prime. But never mind whether delta belongs to D prime or not. If in C limits of type delta exist, then in T of C, inverse limits of type delta exist. If C any type of inverse limits exist, or a small indexing set, then in T of C any type of inverse limits exist, which is a more usual thing to happen. Quite often we take large categories C, which have arbitrary inverse limits in this case. In this case, TC is stable under arbitrary inverse limits, and in many cases, the existence of arbitrary inverse limits implies the existence of arbitrary Dieck limits. So in this case, there is tendency that any type of limit exists. So we will come back to this. maybe we should say a word also about change of delta. In a way, when we have an algebraic theory, we mostly, at the very outset, or to the start, we think of it independently of giving any delta. We think of groups of things, of quantities, of such things. And then we try to figure out, hey, but in what deltas, in what kind of categories does a structure make a sense? And of course, there are various choices. For groups, for instance, I mean, the weakest assumption you can think of is that the category is stable under finite products, in order that a functor commuting to these types of limits should transform a group into a group. So there's a first delta, but of course you may be interested mainly in taking groups in categories in which finite inverse limits exist. So that you may have a larger or in which arbitrary inverse limits exist. So you may consider also the theory of groups as corresponding to a larger, to a smaller, more exact properties, so more stringent conditions, so to a smaller bunch of categories. And we would like to see what are the relations between looking theories over delta and looking at theories over delta prime. So it's pretty clear that if you have a theory without accent on it, on delta, just, I mean, a pseudo-functor going from delta to categories, then by restriction, it defines a theory on delta prime. If you know, for instance, as I just said here, when we have described what means a group object in a category which has finite products, then we know a fortiori what it means a group object in a category which has finite inverse limits, and a fortiori still, you know what it means in a category which has arbitrary inverse limits, if you have some bit per second still smaller. All right. So we have here the restriction proof functor, and it's pretty clear that if you have an algebraic theory in here, it defines the restriction algebraic theory there. Because the stepwise construction that you will make on delta, I mean, it restricts to a stepwise construction on delta prime. This is true before having solved any universal problems, anything like this. It's a tautology, almost. So, therefore, algebraic theories over delta go to algebraic theories over delta prime. Here, this is contained in here, and this is contained in there. Now what about representability? I would like to state, now we have to use the solution of universal problems, that if you have a representable theory over delta, its restriction to delta prime is too representable. So let's write it diagrammatically. We want now representable theories, two representable theories, they correspond to delta naught. The objects representing them. It's the opposite of the two category delta. So what we have to do is to find a functor from delta naught to delta prime naught, which should make this diagram commutative, which will make it clear to us that having a representable theory here represented by an R, that TR restricted to delta prime should be equivalent to some TR prime. The R prime is corresponding element in delta prime. So let's try. What is TR prime? Maybe TR restricted to delta prime, call it TR prime. What is it saying for an object C prime of delta prime? That's some underline in delta prime, in delta, because it's a restriction. It's equal to the TR of C prime when I use C prime as being in delta. It's therefore equal to home underline of lower delta of R with values in C prime. Alright? And now the question is, so I have an object R in delta, and I want to map it in all possible ways into a category element of delta prime, and I want now to find it in a universal way. I want to represent this functor for variable c prime, but c prime being variable delta prime. As I want to write this category as being equivalent to hom delta prime of r prime c, where this equivalence is deduced from some functor like this from r to r prime. R is in delta, r prime is in delta prime, and this functor should be a delta functor. So I want to find a universal way of mapping r by delta functor into an object of delta prime. That is, I start with an object in another two category. I want to push it back into delta prime. Now I claim that if problems 1 and 2 have a solution in delta prime, then this new universal problem has a solution. I will call this solution the envelope, the delta prime envelope, unless I call it the delta prime delta envelope. Get the notes. Maybe delta prime envelope of R. Well, it's pretty clear. So the functor we want to represent, the pseudo true functor, is from R, delta, of R C prime. R is fixed in there, C prime varies in delta prime. Now this is a full subcategory. Maybe I write rather on the other part of the blackboard. I don't want to do it. This is a full subcategory of hom underlined in cat of R C prime. And if the problem number 1 has a solution in delta prime, this can be viewed as being hom underlined in delta prime of the delta prime envelope of R. What would we call it now? The tilde is ambiguous because there are two deltas. Call it Lawvere delta prime of R if you want the delta prime envelope of R. This was in C prime. There we take here, we have here the envelope, delta prime envelope of R, which is just a functor from R into a category which is in delta prime, and this functor being universal. But here we have just delta R as being an arbitrary category. We have forgotten for the time being that R is itself in delta, that it has some special properties to it. So the delta prime functors from this into some C prime just correspond to arbitrary functors from R into C prime. But what we are interested in is this full subcategory when we take only the delta functors. That is, we want, this functor here will not be a delta functor yet. It would make a sense, has a sense to say wonder whether it is or not, but it isn't. Both categories here are in delta. And I'm now interested in those functors from rho R to C prime, which not only are delta prime functors, but such as the compositum should be a delta functor. That is, it should commute, this compositum should commute with certain types of limits. Yeah. Okay, what's this? Can I write it or can I not? Yes. I'm sorry, when I suppose that delta contains the delta prime, I will assume at the same time that D is contained in D prime, that we have among the axioms of existence of limits that we have more for delta prime than for delta. That's pretty reasonable. That means that delta functors, these are just the functors that commute with D. That makes a sense if you have two categories that are in delta prime, because D is contained in D prime. Alright, so we are interested in those delta prime functors here, such as the compositum, which is a Yeah, that's a composite term, commutes with limits of type d prime. Now what I do is, as usual, you see, we have these limits of type d prime, of type d. We want from delta rc prime. That's what we are looking for. So we want that they commute with limits of type d. Now I look at the limits of type d and r. This function will not commute with them in general. So the lack of commutation is expressed by the lack of certain arrows in here to be isomorphisms. And the condition which I want to put on this function is just that they transform these arrows into isomorphisms. Alright, therefore, if I now assume that problem number 2 has a solution, maybe making certain arrows invertible, then I will have a solution to the problem up there. Alright, and of course, algebraic theories correspond just to algebraic objects of the category delta, and here 2. And then here nice parallel plane.
Well,
which kind of sums up the situation of change of delta. Of course, you see, we should realize that none of these functors in general is in any sense fully faithful. You see, when we restrict to a delta prime, the morphisms between categories change. We may have more morphisms, for instance, for the series restricted to delta prime than restricted to delta. If you have two series T1 and T2 over delta, it gives rise to two series T prime 1 and T prime 2 over delta prime. And the category hom underline T1, T2 is mapped into hom underline T prime 1, T prime 2. Now this functor need by no means be anything whatever, not faithful, not fully faithful, not essentially surjective, nothing. This is expressed by the fact that the functor which associates on the objects of data, which associates delta R its envelope, you see, this functor is by no means fully faithful, anything like this. It's two functors. Therefore, when we speak about algebraic theories, that even when we had in mind to start with something pretty, what would I say, pretty independent of any choice of any delta, like groups, strings, principal spaces, D algebras, etc. When we want to take these, when we want to turn such series into objects of a category, then we have to choose a delta, and the homomorphisms between series will depend in an essential way on the choice of our delta. Kind of slow. Now my idea was for today that we would look more closely into what happens when p second is equal to empty. If we're working only with one type of limits, inverse limits, let's say. And then the situation seems to be pretty cleared up. And I guess that next time maybe we will say what happens when we work with delta, the two categories of topoi or pseudo-topoi, topoi without generators. Now, there are two kind of things to see in this case. So we assume that d second is empty, so d is just reduced essentially to D prime, we are considering certain types of inverse limits, and we will not put any exactness properties. In fact, the standard exactness properties that one has had to work with so far have been mainly relations between inverse and direct limits. It doesn't seem that one has met with exactness properties corresponding to just a D prime with an empty segment. Now there are two kinds of problems of things one can say about the situation. First, one can construct the solutions to universal problems, problem 1 and problem 2, and one can also solve the problem about characterization of functors from a discrete characteristic into R, which are basic, so to say, which make the I's, which make I into a set of indicating set for base elements for the theory TR. This can be done. And also, on the other hand, in pretty explicit terms, all this, and on the other hand, one can say something about structures of type on the sample to such D's that they are deducible from the same structures as a category of sets, and that the structure of this type on an object of a category in which X is just the same thing as to give it as an object of C hat. You see, so these are two kinds of things that are partly independent. Perhaps it will be kind of refreshing if we start with solving the universal problems instead of saying more general nonsense about the yoga of a structure of type T on an object X being the same thing as a structure of type T on the HOMS, the ZX, which I have developed at length I think in all three courses. So I guess here now we have at least a very precise setup and quite general in which to express it in accurate and both accurate and general terms. Maybe we want to do this because we may get late. Let's try now to concentrate rather on the solution of the universal problems. So we will first deal with a particular case. We will take D prime equals all small diagrams. That means I'm interested in delta equals delta D, all categories, U categories, in which inverse limits of any, all small inverse limits exist, all inverse limits parameterized by a small category. So definitely D prime is not small. And therefore, one might suppose that we are going to wind up with difficulties of cardinals, but it turns out that we don't. And we have to look at our universal problems, and we will see that they have pretty nice solutions. Problem number 1, we have a category C. I'm sorry, it was I all the time. We have a category I. It's just a category, I don't assume anything about the existence of limits in it. And I want to map it into a category which has arbitrary inverse limits. I say arbitrary instead of small because it's kind of customary. In a universal way. So I don't repeat the universal problem. Now, in fact, this problem, of course, is equivalent to the analogous problems with direct limits. And there it's kind of more familiar. It's rather in the disguise of direct limits as it has been stated. So the problem was to map I by a functor into a category C, where arbitrary inverse limits existed and to do this universally. But that's the same thing as to map the opposite category of I, namely G, into the opposite of C, which would be now an arbitrary category in which direct limits exist. And now this problem has a well-known solution because I introduce G hat, so topos defined by J of all contravariant functors from J to sets, from underlined of J naught to sets. Now in this category, of course, there exist arbitrary direct limits. It's a topos. Assume, maybe we assume I to be small. Anyhow, that's small. That will suffice to us. I being small. Alright, that's a topos. Arbitrary direct limits exist. And I have the canonical function from J to J hat, which is a fully phase-free effect, which is the usual identification of objects to the functors they represent. And it's well known that it does a trick, you see, because one way, let's show how any functor from J into category where direct limits exist can be extended to a functor from G hat into D in a way which is determined uniquely up to a unique isomorphism. Every functor f, every object f in J hat can be viewed as being the direct limit of limits of J. In fact, quite canonically so. F is a direct limit over the indexing category J over F. Namely, all objects of J lying over F. Objects of J which together with arrows into F. Once again, I identify J to a full subset of J hat. Of the value of object X of J lying over F. And we have, of course, every object lying over F is mapped onto F, and this works like this. It's not a filtering direct limit, but never mind, it's a direct limit. And that's true in every category. And now, if you have a functor, any functor phi from J into D, where in D the direct limits exist, I will extend phi to phi hat, let's say, from J hat to D, by writing that phi hat of F is a direct limit over the same indexing category J over F of phi of X. And it's a known theorem, and it's pretty easy to prove, but in this way, that this functor which goes from, let's write it, which goes from home underlined JD to home underlined J hat D takes its values in fact in home underlined lower delta. That's a functor we get in this way commutes with arbitrary direct limits. And that this functor is crazy inverse to the restriction functor which goes in the opposite direction. I don't know if it's done in EJ, in SGA, in the seminar on topoy. I'm not sure it's explicitly stated, but it's, well, it should be under the lines with respect, it's not explicitly stated there, with calculation of so-called continuous functors. You see, the proof kind of is in there, but the statement isn't, because it's kind of unnatural conditions, because there one looks at what happens when these are topos, you see. But maybe it's true, I don't think it's worthwhile that I give the proof here. All right. So if you admit this fact, then we are through now. So we have found the universal solution for the dual problem, and therefore the universal problem of this, the universal solution of this problem here has the solution J hat naught, which is I naught hat naught equals, now let's write it, what is I naught hat? It's home underlined of I double naught ounce, that's home underlined of I ounce, sets, I'm sorry. and then we take 0. So what we do is the following. We take the category of all functors from I to sets, and we take the opposite category. Now, we have a natural functor, but it is congruent from I to covariant functors from I to sets, which associates to every I the covariant functor it represents. So it's written as a functor from I naught to home underlined I sets, but he can do it also as being a functor in the opposite direction. I mean, in the for the opposite categories from I to home underlined upper naught. And so we have this canonical functor, and that shield is what we want. So this category is just deduced from this one, in the technical sense we have made here, by just adding arbitrary inverse limits. Alright, so problem 1 has a very concrete solution, it seems to me. It's really written down there, I mean, all functors from I to sets. Reversing the arrows, whatever. There it is. It's kind of typical, I think, this construction. See, I mean, all constructions I know of these problems, they kind of look like this. One has something usually, something that just write it down, comes out. Now what about problem 2? We have already as a category in delta, namely with arbitrary inverse limits. And we have a bunch of arrows, sigma, which we want to make invertible. Here we don't need to bother about equalizing pairs of arrows because this is reduced to the previous case because D prime contains the diagrams for formation of finite products. Of kernels, that's what is relevant here, of kernels. So we want to make sigma invertible. Now, what I claim is that what I say is the following. If you look at C sigma minus 1, the construction is the category of all categories. Just the category of fractions obtained by making these invertibles, not bothering about any kind of limits. Then I claim that this belongs already to delta, is in delta, that the functor which goes from C to this quotient category, to this category of fractions, is a delta functor. And once I have said this, I'm through. Because I claim that in this case, this delta functor here is the solution. Let's see. We should show that the functor of restriction which goes from home underlined within delta of C sigma minus 1, C prime being any object in delta, to home underlined in delta, comma sigma of C prime, where this comma sigma means that we take the delta functors which turn the objects of sigma into isomorphisms. That this is an equivalence of categories. Let's prove this once we admit the previous facts. Well, this here is contained as a full subclass in a home sigma minus C sigma minus 1 C prime. We're taking all functors, and here the same. Here we take all functors from C to C prime, but not caring about commuting with limits, but those which taking, however, those which turn elements of sigma into isomorphisms. And we know already by the very construction of C sigma minus 1 within cut that this here is an equivalence, so restriction. So all we have to show is the following. So to give an object here or to give an object there is the same. So we have to show that in this equivalence these full subcategories correspond to each other. So in other words, we have to show the following. If we have already a functor from this into C prime, then this functor commutes with inverse limits of type delta if and only if the composition does. Now, is this clear from what I have said so far? Of course, if this commutes, then the composition does. So we have to show that if this does, then this does. Maybe it requires an extra proof. All right, we have to give an extra proof then, to prove that if you have a functor like this into some C prime, such that the composition commutes with arbitrary limits, then this functor commutes with arbitrary limits. So we will put this on. And now, so we have 3 statements to prove, and I think they're kind of straightforward. First of all, C sigma minus 1. Oh, I'm sorry, yes, I was overstating a little. I should first have perhaps transformed a little bit my sigma, enlarged it a little bit before this becomes true. So I have to rectify a little bit the statement I gave here. So I have a set of arrows sigma in here. Yeah. And these I want to make invertible through delta functors from C into C prime. All right. Now let's look at all arrows in C, which have the property that every delta functor from C into C prime that turns sigma into isomorphisms turns also these arrows into isomorphisms. That is, let's saturate sigma. So this will now imply that sigma is stable under a certain number of operations. Of course, the universal problem will not have changed when I replace sigma by this enlarged sigma prime. Sigma prime will have the following properties. It will have the property that if it's stable under composition and contains isomorphisms, because of course isomorphisms in any case are transformed into isomorphisms. On the other hand, if 2 arrows are transformed into isomorphisms, then the compositum is also transformed into isomorphisms. So we have this. It's stable under base change. Familiar conditions, these two. Stable under base change. See, let's say, if Vu is in sigma prime, and if then U is in sigma prime, if and only if V is in sigma prime, that if, so if 3 among U, V, and Vu are in sigma prime, then the third also is. That's pretty clear, no? Because of saturation. All right. As a consequence, we have, for instance, that if U is in sigma prime, then delta U is in sigma prime. Because let's see, X goes into Y, let's assume this is in sigma prime, and let's look. That's U. Now this is delta U. If I compose it, yes. So U being in sigma prime, X times X goes to Y is also in sigma prime because of these two here. So these 2 arrows are in sigma prime, and therefore delta U must be in sigma prime. All right. Now these conditions together already imply that we have a left calculus of fractions in the sense of Gabriel. Namely that with respect to sigma prime, namely if we look at the calculus, say sigma prime minus 1, so it's a sigma prime which we should put here. And also sigma prime is here.
Not clear.
Yeah. This implies that if we have such a diagram with arrows that are at sigma prime, then you can complete it by arrows like this here, into a commutative diagram with these here in sigma prime, because we just take the fiber product, and because of 1 and 2, these two arrows being in sigma prime, these two arrows must be in sigma prime. And another axiom for having a calculus of fraction on the left is the following: if you have two arrows like this, and if after composing them with another arrow which is in sigma prime, if they become equal, then we can also find an arrow like this, which is in sigma prime, so that we have equality here. And what we do is we take just the kernel of this set of morphs and we use the things that we have written down here in order to prove that if these two become equal after composing with the limit of sigma prime, then this was already in sigma prime. So that's, I think, the two main properties for a calculus of fraction. I think all isomorphisms should be in sigma prime, and that's, I think, it. And this implies that, I mean, that in any case, the category obtained from any set of arrows by taking these fractions has the same underlying set of objects. So the objects, anyhow, are equal to the objects of C, but we have now to declare what are the homomorphisms in the localized between two objects x and y. And the description is the following when there's a left calculus of fractions. That's the direct limit for all x prime lying over x, but with a projection morphism which is in sigma prime. So x prime element of sigma prime over x, if you want, of form NC of x prime y. So if you look at all possible x primes lying over y, because we have a calculus of fractions, they form an inverse system, filtering inverse system, where this here is the element of sigma prime. And we take the filtering like limit of these, and they compose in an obvious way. I mean, everything is pretty nice, just as nice as in the calculus of fractions of the ring. Then we make elements of the ring invertible. That's the analogy. So what we have to show is that when we make, we have to show that if we make this construction, then this category which we just obtained has the three properties stated. So in order to construct inverse limits, let's first look at finite inverse limits. It's well known that if C has finite inverse limits, then there exist finite inverse limits in here. And the functor going from C to C sigma prime minus 1 is left exact, commutes with these limits. So that's pretty easy to show, but let's not do it. It has something to do with the fact that we have a calculus of fractions. All right, but we want also to have arbitrary inverse limits. That is, that we have still to look at products. But I have forgotten. I have forgotten one condition. I have said here only conditions that come out in finite terms by separating for functors, any functors that transform objects of sigma into isomorphism. I want to look at those functors which commute with inverse limits. So I want also a fourth condition. I'm sorry, this has to be put into the definition of sigma prime. I will augment sigma prime still more than I have done it here by taking these conditions to stabilize it. Sigma prime, how would I say, is stable under infinite finite products. Namely, I want the following, that if we have morphisms from xi into y that are the same y, that are element of sigma prime, and if I look at the product of these xi's over y, that is finite product over y, that then this here goes to y, that the projection of this to y should be also limit of sigma prime. Now certainly if we define, oh I'm sorry, we have already defined sigma prime as all arrows that become isomorphisms and are all morphisms from C to C primes that are delta functors and that are isomorphisms on sigma. So I claim that our sigma prime has this property. All right. Well, it's pretty clear. I mean, so if our functor f computing with arbitrary inverse limits transforms these arrows into isomorphisms, as he commutes with infinite fiber products, it transforms also this arrow into an isomorphism. Therefore, this arrow should be in sigma prime. All right. Now we will construct arbitrary products in here and we will prove that this functor commutes with arbitrary products. So take xi's in this category, but they are just objects of C. Yes. The underlying objects of C sigma prime minus 1 and C are just the same. All right. So I construct first the product of the xi's within C together with the projections of this xi. And all I have to do is to show that this is a product within the category C sigma minus 1 also, C sigma prime minus 1. So I apply the definition.
Algebraic geometry.
Ja, jest tak, you write down as equals because the data finds really fixed is not
Yeah, that's right. Right. No, I'll finish. Do or die. Just regret the fact that the loss line doesn't reach the front. Ask all that, that's a question.
I have been kind of careless in a number of things that I had stated last time. And so some things are just false as I stated them. I think the essential, really essential facts I think are true, but I have to rectify some other things. So what we looked at was the situation when we looked at algebraic structure corresponding to arbitrary inverse limits. So delta was some kind of cut consisting of categories that had arbitrary inverse limits and functors. Arbitrary, that means for small indexing categories. And functors that commute with those. And I solved our two main problems, problem 1 and problem 2. I purportedly I solved them. And in problem 1 I started with a small category C, and I constructed the enveloping category of in delta by taking the category of covariant functors from C to sets and the opposite category, and C is mapped into this by a fully faithful functor. As a matter of fact, by associating to an element of C, it's the functor it represents. And this is all right. I mean, no problem with this, with C being a small category. We have a U category here. Everything is nice. It's a pseudo-universal problem. Then the problem 2 was the following. We started with an object E in delta, and we gave a bunch of arrows in E, which we better assume small if you, I guess, if you want to have a solution of our problem which doesn't go out of this category, which doesn't get into a too large universe. And we wanted to find a universal solution to giving functors from E to categories E prime in delta, which be delta functors, and which transform the elements of sigma into invertible arrows in E prime. And I gave some construction. Well, I mean, which in a certain formal sense was all right. But the category which I constructed, it was in fact obtained by first saturating sigma with respect to a certain number of things. I mean, I explained this, I don't want to recall it. And then just taking the ordinary passage to quotient by the saturated sigma tilde minus 1. The trouble is that the homes that we describe here, when we take the null definition of homes in a category of fractions, they may be just too large, they may be non-small sets, you see. Because when we saturated sigma without, I will just careless about how big it was, you see. The problem is the same, but sigma tilde may no longer be, in fact it will never be a small set, you see, when we have saturated it. It will lie everywhere and even the way, you see, and E is a big category, so a small category. And therefore, when we look at morphisms of an X into a Y, how were they obtained? I had to take, if I remember well, which way was the calculus of fractions? I had to take, yes, the inverse system of objects xi line over x with a morphism from xi into x, which is in sigma tilde, and takes the direct limit of the home xi is y. But the indexing set here may not be small, you see, and there's a problem to know whether or not the direct limit will be a small set. And of course, I mean, it's quite essential. If you have universal problems in delta, I mean, the solution should be in delta. That should be a U category. So homes should be small. So that was one thing where I was. By the way, I had foretold at the very beginning that I would be kind of careless about these problems. But in fact, I mean, they're essential problems for the proofs. You see, if I pretend to give a proof of something, I should really acknowledge that it's just an idea of a proof, but it's not proof, because the real difficulty will lie in proving that we have the U category. But if there's a solution, you see, it must be this one. This is pretty clear. But maybe it's not a solution because it's too large. So that was one point. And another more serious one was that I claimed, yes, that if I have algebraic theory, T, represented therefore by an R object of delta, and with a base set, a basic set I goes to R in discrete category, then I claim that I already directly generated R by inverse limits, that every element of R was an inverse limits of I. That I was strictly cogenerating, as one says also. And I claimed, in fact, that an algebraic theory involving only inverse limits can be constructed in just 3 steps, namely, starting with a discrete set I and the empty structure on base elements indexed by I, and then putting in some arrows in order to make I goes to R fully faithful, putting in some arrows and putting some accent on these arrows, and then putting in some more accents, you see. So in fact I could put the accent all together. But that's just false already with I is reduced to an element. If you have structures on one basis element, let's take for instance the group structure, this would mean that a group structure can be defined in terms of one element and endomorphisms of this element, you see. A group, namely, here these endomorphisms would be the raising to nth power if you look at this situation. But a group structure is known when we know the nth power. It's pretty easy to see. It's not true. The mistake lay in the following argument. I kind of mumbled that that's the notion of strictly generating or strictly cogenerating is transitive. And that's not true. In other words, if you have a category C prime, which is strictly cogenerating in C second, and C is strictly cogenerating in C prime, it is not true that C is strictly cogenerating in C second. For instance, in the case when you take categories of groups, let's say, which is the opposite category to the category R that represents the structure groups. So let's look at the category of groups, say, And here, therefore, as we are taking the opposite category to R, we are interested about generating rather than co-generating. And so here what corresponds to the base object here would be the group Z. And what is true is that if you look at the subcategory of groups which consist of all free groups, Z is strictly generating in it. In fact, every free group is just a direct sum, in the category sense here, of copies of Z. All right. And if you prefer abelian groups, I mean, the same example works also. It's not true that the abelian group structure is determined when we know the multiplication by n, pi by n. All right. So then the free groups would be just the free abelian groups, the free Z modules. All right. So that's true. Z is strictly generating in here, and this is strictly generating in groups. And every group, in fact, is a quotient of a free group, and it's in fact an effective quotient. So it's that just means that groups can be represented by generated relations, if you want. That's what it means essentially. All right, but it's not true that Z is strictly generating in GR. And if it was, this would be equivalent essentially to saying that the group structure is determined by knowing the nth power maps in the group, which is not true. So I just haven't assimilated too well yet this notion. I mean, there are various notions of generating, and they come in so what I really do think now is, although I had no time to get to the bottom of it, that in order to construct an algebraic structure by inverse limits, we may have to take a whole transfinite sequence if we want to follow the step-by-step distribution. We can't manage it all in 2 or 3 steps. We may have to make an arbitrary long transfinite construction. Of course, with still a small construction, as you would say, a small ordinal, involving at the end only a small ordinal number in the universe. So, and also I stated a theorem, let's say the theorem, I will recall the theorem which I stated, which is definitely false again. I stated that if R is an object of delta, then R is algebraic, namely the theory it represents is an algebraic theory, if and only if R admits a small, strictly cogenerating family. So this I stated. It's certainly necessary, although I didn't prove it in the, or the proof I gave was definitely false, but it's true, the statement, but this condition is not sufficient in fact. And I can give you at once an example, a counterexample, although why this counterexample will come out only a little later. If we take the category R equals category of sets, you see. So it's stable under arbitrary inverse limits. It has a strict cogenerator, namely the set with 2 elements. In fact, in every topos there is a small family of which is strictly cogenerating. That's it. And still it can be shown that R doesn't correspond to an algebraic theory. In other words, the opposite category, R's not, you see, cannot be interpreted as the category of set-theoretic realizations of some type of structure. This is not equivalent to T-R's for some algebraic theory T. And you will see why this is so. In fact, we have to put much more stringent conditions on a category than having a small set of strict cogenerators. And I want to speak about this. These are the so-called accessible categories. So I will have to give a little report now on accessible functors. It's in fact a nice story, which is explained in SGA4, is a big seminar on topoi. There's exposé 1, which is little nonsense on categories. And the last paragraph in this exposé 1, paragraph 9, is about accessible functors. And there the story is told somewhat inadequately, because when I wrote it down, I mean it was the first time, the emphasis was not just the right one. And then some definitions are not too pretty. So I think I will want to explain what this real story really is now of these accessible functors. And accessible categories. And it will turn out that algebraic theories corresponding to arbitrary inverse limits, they correspond just to the so-called accessible categories.
Sure, that's not true.
What is not?
On-stop is a complete atomic Boolean algebra. The opposite of the category of sets is equivalent to the category of complete atomic Boolean algebras, which is certainly algebraic in a pretty strong sense.
Let's see. What do you state? What are complete?
That's all up there. I'll look back on the, where's my lattice theorist around here?
What is complete?
These are the things that act sometimes like the power set.
All right. Now, why don't you give the definitions?
Let me see if I can think of the definitions myself.
And we will.
What's the definition of
I'm
complete
really sure
atomic
it won't be an
Boolean algebra?
algebraic. It won't be an algebraic structure, but let's try.
What are we trying to do?
You can define a complete atomic Boolean
So
algebra.
you claim
Yeah.
that R's node, the opposite category to sets, is the set of sets realization of some algebraic structure.
That's right.
Now let's try to.
The underlying functor is going to be exactly the one is the mapping to the power set. The cogenerator inside an OS-op, the generator, projective generator in OS-op is exactly the two-element set in OS. And that's the mapping. That's the mapping.
Let's see. So call this category sigma, if you or S was this one, I think S was opposite to R. And then S now you have the
S satisfies
set with two elements. I call it I2 if you want.
Okay. Right.
And now, so that would be the generator.
That's right.
So from S to E in S is just
that's right.
the set of all subsets of E.
Right.
All right, now what? So that would be the underlying set of the structure.
That's right.
What's S2?
S2 is, that's the dual of the two elements set.
Or call it I2, yes. I2. In S, that's the homomorphism in R's. That's the homomorphism in the category of sets of E into I2, because S and R's are opposite by definition, and that's the set of subsets of E. All right, and now what is the structure you put on it? E?
The structure that's sitting on there is its natural is the natural structure that it has in terms of.
So let's express the structure. It's a set X together with what? Together with a composition law X upper Y.
Yes,
That's it.
yeah.
And this composition law satisfying which conditions?
What the devil is the definition of a complete atomic Boolean algebra?
Oh, there are some finite axioms, you see.
Yeah, it's just everything has got a join. It's exactly like axiomatizing things from a power
so
set.
that X
That's right. Union.
intersects the union of the YI's.
Yeah.
There should be two
The
operations.
two operations, infinite
Alright.
union, infinite intersection.
All right, and that intersection
Yeah.
should be
Yeah,
distributive with respect to unions,
that's right.
and the dual thing. I think it's autodual. I think. Isn't
Yeah,
it?
I think so.
But it's infinite unions here.
Yeah.
But
Only
is it
of
dual
course.
also should be true? But because that's not autodual anymore. But would you assume also the dual thing? Probably not.
Yeah.
Also,
Yeah, wait a minute, let me,
well, that would mean, no, I think this probably shouldn't. Then subsets of a set wouldn't satisfy the dual condition.
Why
I
don't you run
think.
to your office and pull out Hamilton's account?
yeah, let me look up the definition.
Let me pull up this one.
And there exist complements, I think, don't they?
Yeah.
Phi by x, yeah, but then the rule should be true too. So phi by x, there exists x prime such that there exists also a smallest element, so there's a two-sided unit for this here, I think, which is the largest element, and two-sided unit for this, which is the smallest element. So all these are algebraic. I mean, these are axioms that formalize very well. And we assume that for every x exists x prime such that the intersection of x prime is the initial element and x union x prime is the mid element. And that's all, or have you to assume the unicity in it, or is it a consequence of the other axioms? Because we have to be careful also whether this axiom, how this axiom will be stated. I would think that probably can be stated as an axiom of algebraic structure. But so there's the existence of a map from X into itself, you see. Yeah, I mean, we can even make it as an extra data after all. Why not? It's unique all the better. So we put it as an extra data, an extra arrow from X into itself, and X goes to X prime, and this is when it becomes an axiom of this extra data. All right, no problem. And then perhaps other axioms will ensure that in fact this X goes to X prime is unique. I don't know. Maybe we forgot some. But that wouldn't be the whole story. He said something about complete Boolean algebras. For the time being, this is just Boolean algebras, I think, right? With an infinite axiom here.
You said atomic too.
But already, I think already here, this is not an axiom here. I mean, there's an arbitrary set in. It's a bunch of axioms, but we have to be careful. We can have only a finite reserve of indexing sets. I mean, a small reserve of indexing sets. This, in fact, is not one axiom, it's a family of axioms. And if this family is not small, you see, it is not eligible in our context. You see, if we say for every set I, in this large, it's not a small, it's a large set of axioms. Of course, I mean, if you admit large sets of axioms, then I'm quite willing to believe that, then it's, I think, pretty clear that any category with a small cushion set will represent an algebraic theory, but I don't want to do this. I mean, I want only at each step of our construction a small set of axioms, a large set. So this seems to be, of course, it can be written down by a single formula, but there is for every set I, you see. For every indexing set I, and this is, I mean, hides a lot. Then completion would be also, I think, probably complete would mean that the supremum of the arbitrary family exists, you see. The same kind of story in the issue of an arbitrary family. It looks very much like topological spaces, you see. They don't form an algebraic structure, so I don't think that Boolean algebras form an algebraic structure. At least, in fact, I mean, I have a proof that they don't. Because the category of their sets and realizations doesn't satisfy the condition I'm going to state.
Not very nice.
Hold it. That isn't the right term. You don't have to use it. It's stone spaces which are.
Is that what it is?
Yeah. Which are what? Zero-dimensional.
Yeah, and
Is it just zero?
He claims that Jack has the wrong duality. But it's probably important.
It resembles very much, yeah, to the situation with. All right, yeah, for an ordered set, or this infinite distributivity axiom, you see, without restricting the cardinality of the indexing set, it's not an algebraic structure in the sense which Fabian described it.
It's not a bad.
Well, it depends what you want to do. I mean, there are various notions, you see. Each one has its own. I think it's good to kind of frame out something which really can describe in small terms. Of course, using at random, you see the existential and the other quantificator. I mean, you can express everything in finite terms, but that's not what we had in mind, you see. That's what not kind of fineness we had in mind. But then the topological spaces also then make an algebraic structure. After all, one has to stop somewhere. So I was giving certain types of prescriptions which make of a certain standard type, and I was studying these, which I call algebraic structures. And so quite clearly, Boolean algebras are included. I mean, at least a priori, it doesn't seem that this axiom can be expressed, and it seems that we can prove it can't. Let's say also what makes us feel that it can't, you see, even without going through the whole series of algebraic series, you see, would be then you certainly can find for every cardinal, you can find, let's say, a Boolean algebra, or just an ordered set, let's say, in which sums are distributive with respect to intersections for cardinals at most pi, but not for arbitrary mixing sets. That is, you see, whenever you restrict the cardinality, you see we have not yet formulated the full distributivity. I think that's, the situation seems to be pretty clear.
Yeah.
What's Jack doing? He's looking for some big reference book
Yes, I'm Boolean.
to cram you with.
All he wants is a definition of an atomic, complete atomic Boolean
Well,
algebra.
we don't need it anymore, I think.
He doesn't know that.
Yeah.
What is that the other thing? I mean, I've forgotten it from Helmut as well.
I read it on an airplane. It's not the way to do a talk. And, I can't remember. I thought it was so clear. It was read like a comic book. And I can't remember how it was.
Some sort of ultrafilter form. Should be honest.
Go chase them down. Maybe something interesting going on. I mean, God wants me to go. Why is the accent doesn't work?
Well, then do define it by a small set of axioms. But axioms in the sense that I have made explicit, you see. All right, now give us a small set of axioms, please.
Well, this is what I was looking at.
No, but just start. Just those that you remember. There was one we remembered. That's not small here. That's for every set I. And when you don't bound the cardinality of the set I, this means that you have an...
Oh, wait, all right, who's doing this one? Okay.
You can't express it in the way I said, you see.
Yeah.
For a given set I, you see, it makes a sense. It's one axiom. And is it? Is it for a given set? How would we make it as an axiom? Yes, of course. It's in terms of how would we, let's even formulate it for a given set I. How would we formulate the axiom here? In the setup of which I said.
No, it's the same with that. Every element in there has a supremum. Over any index indexed by the element, indexed by the set itself.
Even this, yes, it's
Yeah.
an operation. In fact,
defined by an infinite operation. Yeah, there's no question about that.
the number of iterations in a way is already not small. Because when you want to express the axiom for every family, there exists a supremum, you see. The existence of a supremum, I don't know if you can formulate this in an axiom of an algebraic theory, but even if you could, then we still would have to formulate it for every set I, you see. And there would be the set I again. You see what makes me feel that it, in naive terms, that you can't express this as if in finite terms, is that if you bound the cardinality of I, then you want, it's the right thing.
You're quantifying over sets, the second order.
Yeah.
The second order grid.
I mean, of course, you can express, all algebraic structures, non-algebraic structures, you can express them by finite text, you see, or using a certain number of time quantificated and whatever is allowed in the foundations of mathematics. But that's not what we had in mind. We were given very precise prescriptions of certain types of theories that we were investigating. And Boolean algebra just doesn't fit into it.
Maybe you can define a second order theory after we get finished with the first order ones.
No, it requires infinitary operations. It's not. But it's finite, but it's finitely axiomatized.
No, every arrow you see, of course we can have, a statement we could have, for instance, for a given set I, which may be pretty big, you can have a morphism, a composition law like this, for instance. This is perfectly all right. But we shouldn't have a set of composition laws, you see, in the data that should be non-small, that should be an element of a larger universe only. So this we wouldn't admit, and the same for the axioms. Every time when we're adding axioms, you see, the category of constructions for an intermediate theory, that's a large one. But when we add axioms, we want it to be a small number of axioms. Even within that certain arrows become isomorphisms. We take only a small number of arrows. When you
but the cardinality in the case here for I is always bounded. There's always only a small number of operations. There are no more operations of this sort than there are, the cardinalities of the various subsets. It's bounded by the cardinality of I.
Of which subsets?
Well, in this case, you suppose we want to talk about axiomatizing, a join as an infinite operation. Okay. Yeah.
So we would have only joins for bounded cardinality of the indexing sets. Otherwise, there's a theory. I don't contest that there's a theory of Boolean algebras and the like.
No. The argument about whether or not it's legitimate and it should be called algebraic.
This is a question of taste, you see. But let's say the following: if he wants certain types of results, like representing algebraic theories by universal structures and so, then we better be very careful about the setup. And so I was proposing one. So instead of algebraic theories, call them strictly algebraic theories. If you want to reserve algebraic theories for something larger. But of course, let's say we can, why not look at two setups, but I'm more interested in the first rather, but the second might be just as interesting. By just paraphrasing what I have said so far, but not insisting that at every time the data, the number of data that we give is small.
I'm not requiring this operation for every single set. there's a finite number of, finite number of operations here to get this infinite join. I mean, there's only a set. It's a small set because the i's that I need here need to be no larger than the cardinality of x. But you're going to say that I need that from
Yes, for every x.
For every-
You want to
for
have,
every-
I mean,
for every x.
your axioms shouldn't depend, your set of axioms shouldn't depend on the x, of course. That you're
Right.
putting. The set of axioms should be independent of x, and then you say whether or not the set of axioms applies to x with some data in it. I mean, even the data here, that's the data then giving the infinite join depends on x. You see, I mean, the description of the data, it just doesn't fit. But of course, you see, if you give, you will, I mean, if you allow yourself non-small data, you see, then the categories of constructions, you see, it will kind of go over your head, you see, that it will become like, you see, the category of all functors from ans to ans. I mean, there will no longer be U categories. It will be pretty grim.
It seems like this really isn't a problem, because with any particular Boolean algebra, you can just change the axioms by restricting the cardinality so you could fit it into your scheme.
Of course, yeah.
So it's not really a problem to restrict it.
But in fact, the same argument applies to, and I think this would be...
I agree with you. In this case, there won't be any way. That's true. Anything that would correspond to the theory or the gadget would represent, there would certainly be no small I that would do it. In this case, you'd have to require the smallness of I is clearly out in this case.
Yeah.
Okay, all right. If you accept, if you're, I mean, all I was saying is like,
no small i's there, so why I have a...
no, the I in this thing that would be turning in terms of the representative.
But here you see you have just I reduced to one element. I mean, and you speak about Boolean algebras. But I think it's a good point to make, you see. I mean, every particular one can be subsumed under the theory of pi Boolean algebras, where pi is some given...
No, there's something intermediate though.
Some given kernel.
No, but there's something intermediate between this type of algebraicity and the type of the thing where we would agree that's totally non-algebraic. So there's something. This sits something in somewhere in between this type of notion. It's certainly not as unalgebraic as say topological spaces.
Intuitive.
One has a feeling, yes. Although I
It's
have
not
not...
that. There are a few examples of these. These are what I'm talking about are the ones that are called by the universal algebraists. These things that you can define by means of possibly infinitary operations. You say, well, you can even define
Not
them.
only this, but even a non-small set of infinitary operations. I must say, you see, 20 years ago, I was quite ill at ease when I saw the definitions of properties for example, where I is an arbitrary set, you see.
Yeah. This is certainly
There's
true.
something and then I got used to it. I mean, nobody gave a certain setup. I mean, nobody ever proved it's contradictory. Although I met some chefs who pretend they can prove it is. I'm not sure if they really can prove it. And so,
Where are they? Where?
what's the name of the chap? Arts Dupré is a chap. He's a nice chap, but kind of in some ways a little bit of a crackpot, so at least not relatively speaking. So I'm not sure what she said is true, but anyhow, it goes against some kind of instinct, you see, too. Where there's some small structure of a finite set, you see, and you want to express an axiom by saying for every set. It kind of goes against you. All right. So what should we do now? Should we go on?
Okay.
And forget about this?
It's just again, part of this is deciding on terminology and things, and this is.
Yeah.
There exists.
It's more than mathematics. It's some question of mathematics.
No, it seems to me that you probably get better theorems if we just stick to your original formulation and worry about making it more inclusive with it.
You see, but the same kind of arguments as you made, kind of, applies also to large sets of models for taking limits. For instance, taking all diagrams for taking all small diagrams as taking inverse limits. You see that's in fact it's a point I will have to insist upon is that the categories that correspond to algebraic structures are those which would be the delta pi delta envelopes, you see, of categories corresponding to algebraic structures that can be expressed in terms of inverse limits involving only cardinality at most equal to a given pi. You see, because in fact, when we keep adding data, you see all these data are there's a small number of them, and the limits they involve, finally they will all be moderated by some pi. But these here now in delta pi, you see here, those objects of delta pi which represent algebraic series, they will be small categories. Exactly. In fact, I essentially didn't prove the. Well, in fact, here it's pretty easy. The fact that the enveloping categories, etc. And therefore, in fact, the categories in delta which correspond to algebraic series are obtained in the following way. We take a category in delta pi which is small, and we take its delta envelope by adding arbitrary inverse limits to the pi inverse limits that already exist. And in a way, what I was going to do now was to explain what kind of categories turn out. These are the so-called accessible categories, or co-accessible, I should say. So, if you reverse arrows, then it's likely that we are considering. And in fact, it's rather in the opposite categories that people usually do well, because these are the categories that carry the sensitive structures. You know, it's kind of equivalent. And it's more, in some sense, in some relation, in some sense, it's more intuitive. Well, it depends what one is more intuitive. R, you see, R carries the universal object, and S is a set of structures, of the sets of structures of the given type. So, should I make a little report on this accessibility business? I think it's kind of typical of how the passage goes from a small amount of models for taking limits, let's say, for deltas that are constructed in terms of small number of data to a big data like here. And I think it should be, I think that the general story you see should be of the same type, that you always can reduce to a small set of data, also of models for constructing your limits. Now, I have not completely cleared up the most round way you see this notion of accessibility, and I'm pretty sure of the statements that I'm going to give only when there exist like limits in our categories. But that's not the most natural condition. So let's give the. So we have to give a few definitions. Let pi be a cardinal, and I be an ordered set, or pre-ordered set. We may also have to use the terminology for categories, in fact, in some contexts. But let's take it ordered here. Let's not bother about technicalities. Then I is said to be large over pi. How would you, grand devant pi, how would you say? With respect to pi?
Yes.
That's a little long, but large with respect to pi. If the following condition holds.
You just say pi large.
Pi large, yes. I think that's what is the best thing. Although there's another notion which I would like to call pi grand, but let's say pi large here. But it's larger than pi, you see. Large with respect to pi. So it's a bit larger than pi.
Yeah, I think large.
Pi dominating perhaps is better.
Maybe that's all right.
Pi dominating. that I dominates pi.
That sounds good.
Dominates pi. Yes? If first of all I is filtering, and second, for every family x alpha of elements in I, where the cardinality of the indexing set lambda is at most equal to pi, there exists x in I, x majorating all of the x alphas. In fact, if the cardinal is at least equal to 2, you see, in fact, our cardinals will be infinite. But if the cardinal is at least equal to 2, then it just, this condition already implies that it's filtering. And when the cardinal is fired at least equal to 2, then it's just equivalent to saying that it's filtering. But we're interested, in fact, in infinite cardinals rather. All right? Of course, the larger pi, the stronger is the condition for being pi dominating, or dominating pi. Now, what about, now assume we have two categories, E and E prime, and let F be a functor from E to E prime. Then we will say, maybe we should before this. Yes, I have another definition first to give. So definition 1, definition 2. A category E satisfies condition L pi. That's an existence of limits. If for every direct system xi or x alpha, x alpha, alpha element of I in E with E dominating pi, perhaps we'll write it I dominating pi like this here. I dominating pi. We want that the direct limit of the x alphas exist. So, direct limit with respect, if I dare say large enough, you see, open sets, I mean that converge powerfully enough in a way, which gives a powerful way of convergence. These limits should exist. And we will say that E satisfies condition L. Condition L if there exists a pi, a small pi in the universe that we are working in, such that E satisfies L pi. Alright. Now, what about functors? So let E goes to E prime be a functor, and we assume already that E satisfies L, that satisfies L pi, let's say. Or why assume anything? Let's give a property of the functor. We'll say that F is pi accessible, pi being a cardinal by definition. If first a condition on E satisfies the condition L pi, and second, F commutes with direct limits of type I for every I that is dominating pi. So, on one hand, we want that the direct limits of the type we are considering should exist, and that F should commute with these direct limits. So, it means the yoga is that, at least for certain types of categories, you see the natural functors, I mean the ones that are not pathological, that functors that can be expressed in small terms, so you say. They are exactly those that satisfy to the condition that are pi accessible for some pi. And this we call accessible. F is called to be accessible if there exists pi in the universe, a small cardinal, such that F should be pi accessible. So, I mean, all these definitions are designed for dealing with large categories, of course. Of course, when there exists arbitrary inverse limits of large dominating I you see. Except E is equivalent to the unit category, or is empty. You see, there's small chances that E may be small. And the idea is that for large categories, you see in functors between them, either the functor behaves well with respect to Dirac limits, at least large over pi, or they behave well with respect to inverse limits. If they don't behave well with respect to neither of them, and kind of one has a feeling then that the functor is kind of out of reach. But in order to be finite, you have to go really to the next universe. It's something really too large to be manageable. And now I have to define accessible objects of a category. Let X be an object of E satisfying, well, once again, let's not make any assumption on E.
You want that to be definition 4.
Let's see, perhaps rather definition 4, yes. Then X is called to be pi accessible if and only if the covariant functor it represents Hx, y goes to hom xy, which is a functor covariant I insist from E to sets, satisfies L pi. Is a pi accessible, I'm sorry. Is pi accessible. So this implies that E satisfies L pi. If E has elements that are pi accessible and must satisfy L pi. So we want that hom xy for variable y should commute with filtering Dirac limits that are dominating pi. And we will say that an object is accessible, X is accessible, if there exists pi in the universe such that X is pi accessible. That makes a lot of definitions. They're not quite finished yet, but after a while we'll turn up with some theorems. The idea is that in categories that are not too far out, you see, the objects should be accessible. All objects should be accessible. Now I want to define what are the categories that are not too far out. Alright, so definition 5, I guess. That E be a category. Then E is called pi accessible. All cardinals I'm going to consider are small cardinals. That's not. Yeah. If there exists a subcategory C and E, full subcategory, which is strictly generating, that means that every object of C is a Dirac limit of some diagram belonging to C, which is small, and such that the objects of C are pi accessible. Alright, but the really important notion again is the notion of E being accessible, which means that there exists a pi in the universe such that E is pi accessible. Alright, so these are definitions. The definitions 1 to 4 are those that you will find in SGA. This definition is not the one in SGA, which was not too good one. I said here that we take a small generating category. And the statements didn't come out too nice, in fact. For some kind of marginal results, it was enough. But in order to have the whole story, you see, you better adopt this definition. This is different, stronger from SGA for expose 1. Now let's start with some propositions. Let's look at two categories, E and F. And I guess we assume that E and F both satisfy the condition L pi. Let's state again that we will remain interested in the case of categories that are stable by small direct limits. By the way, when I said here condition L pi, I'm sorry, maybe I large dominating pi and of course I small. I have to make some restriction on the set I, that it shouldn't. So I have to get this E and F satisfying L pi, and I will denote by hom lower pi of EF the full subcategory of hom EF consisting of functors that are pi accessible. And the statements are that for every type of limits, of direct limits, I'm sorry, type of direct limits that are representable in F, of course then we know that the same type of limits are representable in hom underline EF and are computed argument-wise. Alright, well, the first statement is that hom lower pi, that the pi accessible functors are stable by these types of limits. Hom lower pi contained in hom underline is stable by these limits. Now this is a triviality, because being pi accessible is a property of commutation with direct limits. It's stable under any type of direct limits, while these direct limits exist. But now something which is less tautological, that it's stable under inverse limits with the, let J be a category, small of course, such that the cardinality of the set of arrows of J that most equal to pi. I have to make, of course, some restriction. And such that the inverse limits of type J exist in F. Then the set of accessible functors, pi accessible functors, hom lower pi, is stable under these limits. So the inverse limit of pi accessible functors is pi accessible provided we can compute it argument-wise. In fact, we don't even have to assume that in F they always exist, these limits of type J. We have only to assume that they exist for the particular computation we want to carry through. And provided moreover that the cardinal of the set of arrows of J should be modulated by pi. As a consequence, of course, we get something where we drop the pi, namely if we look at the category of accessible, if we look at the inclusion from underlined accessible EF contained in home underlined EF, this will be this full subcategory of accessible functors will be stable under any type of direct limits which can be computed argument-wise, and it will be stable under any type of inverse limits that can be computed argument-wise, provided of course that the indexing sets in both cases are small. So this B here requires some care. It amounts to a property of commutation of filtering direct limits where the indexing set is large with respect to pi with arbitrary inverse limits when the indexing category has a cardinality of arrows at most pi. So it boils down to a theorem in the category of sets. And there one just does it. It's, once one has stated it, it comes out very easily. And so if that's what it gives, let's give some let's apply this to accessible objects. So in terms of accessible functors about which you just have said something, we have defined accessible objects, so let's see the corollary for those. Let E satisfy L pi, and let E pi be the subcategory in E of all pi accessible objects. So strictly full subcategory pi accessible objects. Then what we claim is that E pi is stable under direct limits of type J, provided the cardinality of the set of arrows of J is equal to pi. And therefore, as a corollary, if E satisfies L, then the full subcategory of E formed by accessible objects is stable under arbitrary direct limits. Now this corollary above is needed in terms of what we have said, because if X is a direct limit of some xj's, then the functor home xy for variable y is the inverse limit of the functors home xiy, and as these functors by extension are pi accessible, the inverse limit functor must be pi accessible too, provided the cardinality of the indexing set, of the indexing category, of the set of arrows is at most pi. And we have some nice stability properties. Let's give another corollary. If E is an accessible category, then every object of E is accessible. Because what is the definition of an accessible category? It's a category in which there exists a strictly generating small set, such that all objects of C are accessible. But C being strictly generating, this means that every object in E is obtained as the direct limit of objects in C of a diagram of objects in C. And therefore, being a direct limit of accessible objects, it must be accessible. Now, here I've given a number of stability conditions, but I should give also ways of recognizing that one can find at least one object in the category which is accessible. I should give examples. So, for this there's a theorem, one sufficient condition for getting I have to decipher my own answer. All right. So, it is small and generating by strict universal epimorphisms. So it's something even stricter than strictly generating. To say that C is strictly generating means that an object in E admits a family. We can find an object in E, then we can find a family of objects xi in C, and arrows from xi into x, so that this family should be strictly epimorphic. And there's a term to the effect that this is the same thing as strictly generating. I defined it here. Of course, if x is a direct limit of objects of C, then these arrows which go from the vertices of the cycle limit to x must be strictly epimorphic, but one can prove that the converse holds. But here we want something even stronger. We want that this should be not only strictly epimorphic, but should remain so after any base change. But of course, it's the same thing if you know that in the category we are working with, strict epimorphic families are universally strictly epimorphic, which is true in topoi, for instance. In fact, in topoi, even epimorphic families already, they are strict and they are universal. Therefore, they are strictly universal. All right, so we have this here, which is satisfied in every topos. We assume that in E there are fibered products, exist fibered products. And moreover, yes, and another condition, there exists kernel of double arrows, and I want that this kernel functor for double arrows commutes with, well, sufficiently potent filtering direct limits. I want that this functor should be accessible. UV goes to kerr UV should be an accessible functor. For instance, in most categories someone is working in, the filtering direct limits already, they have filtering direct limits in the large categories one is working with, and these filtering direct limits commute with finite inverse limits. So certainly the kernel will be accessible functor. It will be if not accessible, even too accessible. Where 2 is the kernel of 2, or 3 accessible. All right. So these conditions are certainly satisfied for any topos, for instance. And these imply that E is accessible. So all we have still to prove, as we have already the small strictly generating category, we have only to prove that the elements of C are accessible. In fact, then every element of E will be accessible. So that's really the result. And this, under these conditions, every element of E is accessible. And the proof is given in the reference I gave, 911. SJ4, chapter 1, paragraph 9, proposition 11. So that gives a lot of accessible spaces. Example. Topoi are accessible. But let's give a counterexample. Counterexample. The opposite category to sets is not accessible. Of course, it has arbitrary direct limits because in sets there are arbitrary inverse limits. But what would mean that R naught is accessible would mean that it would, of course, it has also a generator because R has a cogenerator, namely that, for instance, a 2-point set or any set which is not empty or reduced to a point is a cogenerator. But I claim that an object in R is co-accessible if and only if it is reduced to 1 or 0 points. Because to say that it's co-accessible means that the functor y goes to hom yx, transforms inverse limits into direct limits, provided we take inverse limits which are sufficiently potent that dominate some prime pi. But even taking, I mean, it's pretty easy to see that is never true if x is not of cardinality 0 or 1. You can always find inverse systems, you see, where I map from, for instance, this would imply that every product, every map of a product of sets yi, now with a discrete indexing set, goes into X, can be factored through a subproduct with, let's express what it would mean that X is pi co-accessible. And let's give a consequence of this. And let's give an interesting example, let's say, of, we have not given any example of sets that are, of filtering sets that are large with respect to pi. So that would be a good occasion for us. So let I be any set, and let J be the subset of P of I, the subset of the set of all subsets of I, which is formed by those subsets I prime of I, such that the cardinality of I prime is close to equal to pi. Now, these subsets of I mean, they are ordered to inclusion, and they are dominating pi, because if you have a family of subsets of I, which are each of them of cardinality at most pi, and the number of such subsets being at most phi, you see, the indexing set being of cardinality at most pi, taking the union of all these, gives a set which is again of cardinality at most pi. I assume pi to be infinite here. I better. All right. And now, if we take a product, of course, if I has cardinal at most equal to pi, then among these j's there's I. That is that in this case our filtering set has a final element. So the limits with respect to such a thing are not so interesting. But now if I is any set, we know that the product of the yi's, I mean taking products is something that I know, can be obtained by the following way. I take all subsets j of I which are of cardinal at most equal to pi, pi being some fixed cardinal. Call this, for every such subset y prime, call y lower I prime. For every such subset I prime, that call y lower I prime is a partial product. And it's pretty clear that the full product is the filtering inverse limit of these partial products with respect to precisely this filtering set, which is dominating pi. And so if X was pi accessible, that would imply, for instance, that every map of this total product into X factors to one of the yi primes. For instance, if X is a set with 2 elements, therefore if you take if X contains a subset with 2 elements, this would imply, for instance, that every subset of the total product is the inverse image of a subset of one of the partial products. But if the cardinality of I is greater than pi strictly, then it's pretty clear that this is not true. For instance, taking the complement of a point and taking the i's to be all non-empty, you see, and to having all of them having, let's say, all of them having at least 2 elements, the complement of the point. Or the point, let's say, well, it's a subset, so it can be identified to map of this into this 2 point set. It doesn't come from down here, but because the inverse image of a subset here would have certainly a cardinal larger than 1. However, you see, the opposite of R's and the opposite of any topos, in fact, they are categories which have arbitrary Dirac limits and which have generators, because topo you have full generators. But they are not accessible. Now, I get a little mixed up. Here's my sheet.
You just satisfied me in terms of the defining functor that makes us opposite algebraic in the sense that I'm talking about, that I was talking about, is not accessible. You just proved it's not accessible. All the structure on the dual category is carried by the endo functor, the power set of the power set. That's exactly it, and that's clearly not accessible.
Let's see, I don't want to state everything in my sheets here. If you want something with additive categories, for instance, you just, let's take the category R, for instance, of all abelian groups. In fact, all categories yet you can construct with the algebraic structures we have looked so far, you see. They will turn out to be accessible. Whereas up north, for the same reasons, the opposite category is not accessible. Same story. I think it's pretty rare that a category and the opposite are accessible. Maybe you see it's true only for categories that are equivalent to the one-point category. It should be extremely rare. If it's not true for us, for which would it be true then? I mean, or R. So that's a problem. If E and E naught are both accessible, is it true that E is equivalent to the 1 point category? Now I'm going to state a theorem which I guess should be true as soon as the condition L is satisfied for category E. But I'm not too sure. I kind of proved it, I think, when the category admits arbitrary filtering Dirac limits, or not even arbitrary Dirac limits, not only filtering Dirac limits, filtering Dirac limits. So that's for what we want to do in universal algebra right here. That's quite enough, but for other applications it may be kind of silly. So let's get now the main theorem, I think, of the theory of accessibility would be the following. Let E be a category, and so to be safe, we'll assume that there exist small Dirac limits, not only filtering ones, in E, but this is presumably not necessary, and condition L should suffice. And I claim then that we have a certain number of excellent conditions, but in order to appreciate them, perhaps I should first make a very standard construction for getting accessible categories. Because, I mean, we have a model. And so the theorem will state more or less its accessible categories are just those which can be obtained in this way. So let's see be a category, but I will assume it to be small for what we want to do with it. And recall what end of C is. It's a category of end objects of C, namely of diagrams in C which are indexed by filtering ordered sets, and the homomorphisms are defined in such a way that NC, by taking Dirac limits, is contained in C hat, this set of controlling functors from C to R. By associating to every as a full subcategory. By associating to every Dirac system in filtering Dirac system in C, the Dirac limit, but the Dirac limit being taken in C hat. By doing so, we define homomorphisms in here in such a way that we get in this way a functor which is fully faithful, so that the homomorphisms between n objects are just homomorphisms between the corresponding functors they, as we say, n represent. Yes. So that just means, when we look what it means, it is that the homomorphisms of an n object xi and to an n object xj are obtained in the following way. Let's just interpret this. There should be the homomorphisms between the Dirac limits of the xi and the Dirac limit of the xj's, but the Dirac limits being computed in C hat. So if by chance they exist in C, we just forget about the fact that they exist in C. They would of course not be the same in C or in C hat. And therefore, the homomorphisms of this into this, they're just the inverse limit for all i's of homomorphisms of xi into xj into the inverse into the Dirac system of the xj's. That's by the very definition of a Dirac limit of objects in the category C hat. This is a home, if you want, within C hat. This is the home within C hat. And by definition of the by the construction of the Dirac limit of functors, by computing an argument-wise, this home here is a Dirac limit over variable j's of home xi, xj. Therefore, the home in, let's now say, in nc of xi, this values, comma, I would rather put here yj perhaps, otherwise it's kind of confusing the notation. It's not the same. It's not the same Dirac system. And yj is just the inverse limit for all i's of the Dirac limit for all j's of form xi yj. And in fact, this category of n objects, there's a large paragraph in SGA for explicit 1, which is dedicated to the end paragraph 8, the one that just precedes the paragraph on accessibility. So they give rise to the really very convenient formalism. I can't insist too much on it, but many things in mathematics can be expressed in n objects in the most convenient way. And in fact, we are going to kind of make this systematize about this now. Let me give a statement, for instance, which is quite often useful, which gives a characterization of NC in universal terms as being the delta, let's call it the delta envelope of C, where delta is the category, is the sub-2 category of cut consisting of those categories which admit arbitrary filtering Dieck limits, and where the functors are those which compute with filtering Dieck limits. So I say that NC is an envelope of C in this sense, namely, first of all, in NC filtering Dieck limits exist, of course for small indexing sets. So we have in fact a functor from C into a category in which there are filtering Dieck limits. And now moreover I claim that this is universal, namely that for every functor from C into a category E where there are filtering Dieck limits, there exists a factorization up to isomorphism, up to unique isomorphism through NC. And to make it more precise, the statement just means that the functor which goes by restriction from home prime and CE, where home prime, or let's call it home lower delta. This means the category of functors from NC to E that commute with filtering Dieck limits. It's not this delta we have looked at the beginning when we were speaking about inverse limits. Now we are speaking about filtering Dieck limits, which goes from this by restriction to home C, E, plus the equivalence of categories.
With the delta there too.
No, C has no Dieck limits. It's all functors,
right.
all functors from C to E. An arbitrary functor from C to E can be expressed up to isomorphism can be interpreted as being a functor from NC to E that commutes with filtering Dieck limits. So that's one way of expressing NC in terms of C as a solution of universal problem. Of course, C goes to NC associates to every object of C the same object, due to as being a constant Dieck system. Or it's else, in terms of the interpretation of this as subcategory of C hat, it's just a functor represented by C, the covariant functor represented. Complement functors by C.
Didn't you once say you could get aught that way? Didn't you once say you could get aught that way?
Which
Isomorphism.
As n-representable functors? For sometimes, yeah. When you're lucky. Anyhow, if you are n-representable functors, there are a lot more than representable functors in general. And they are very close to representable functors in some respects. Let me give another statement, also without proof. Assume that in C there exist finite Dieck limits. Then it's proved in SGA, and a lot more is proved, that in NC finite Dieck limits exist also, and there's also filtering Dieck limits exist. The two together makes that in NC now arbitrary Dieck limits exist. And then now let's look in delta, let's look at the category, let's now denote by delta prime, let's say, those categories for which arbitrary Dieck limits exist, and functors between them which commute with these arbitrary Dieck limits. And let delta prime naught be the category, the sub-2 category of cut, which consists of categories in which only finite Dieck limits exist, and functors which commute with these. So C is a delta prime naught, and I contend, and the functor which goes from C into NC is a functor from an object, from a category of delta prime naught into a category in delta prime, and I contend that this again is universal, that this NC is a, how would we call it, delta prime envelope of this category C and delta prime naught. In other words, if E is any category in which arbitrary Dieck limits exist, and if I look at the restriction functor, which goes from Hom delta prime NCE, the category of all functors from NC to E commuting with arbitrary Dieck limits, to the Hom underline delta prime naught CE, to the category of functors from C to E that commute with finite Dieck limits. This functor again is an equivalence of categories. So we can also express it in the following way. If we express an arbitrary functor from C into E as being a functor from NC into E that commutes with filtering Dieck limits, then the functor here is right exact if and only if the functor here is right exact, namely commutes with arbitrary Dieck limits. So, according to the situation, this NC category can be expressed as solution of a universal problem in terms of C, and a universal problem think of a type that we have considered, I mean, throughout in our general nonsense considerations on universal algebra. But now I have to work with categories that are subcategories of NC that are slightly more sophisticated, which I will call n lower pi C, where pi is some cardinal. It will be a full subcategory of NC, which contains again C. And this here will be the subcategory of all end objects of C, which can be parameterized by ordered categories which are dominating pi, whose indexing set I dominates pi. So let's just take those, you see, with very strongly converging, strongly with respect to pi, converging ordered sets as indexing sets. And it turns out, you see, that this here is a pi accessible category. Let's see, is this clear or not? Anyhow, it's clear that C is strictly generating. It's a small category that strictly generates, because every element in here is tautologically so. The Dieck limit of a system, of a filtering Dieck limit, in fact even, but never mind, of a Dieck system in C. Namely, it is itself such a Dieck system. This Dieck system as an object of the category NC is in fact the Dieck limit of these Xi's. I mean, that's the way in which I describe the category structure here. By identifying this here to the Dieck limit of the Xi's. All right. So we have to prove that on the other hand that the objects of C are pi accessible. And in other words, we have to show that the functor, well, no, we have to prove, there's a little proof to be given, you see. We have to prove that the functor for fixed x in C, that the functor y goes to pom xy, which goes from end pi C to the category of sets, that this is pi accessible. Now, what we will first note is that if we take a Dieck system, so we have to prove that it commutes with Dieck limits dominating pi within this category. Now let's just check that it works all right. I mean, it's not too hard to reduce to this case. When the Dieck system which we have, let's say y alpha in here, of objects in here, when they in fact belong to C. To have such a Dieck system just means that we have an end object of C, and the assumption which we made on the indexing set, that it's large, that it's dominating pi, just means that this end object not only belongs to here, but it belongs to there. But never mind, what does the commutation with Dieck limits mean? That's essentially the definition of the homes in our category, you see. But we kind of reduce rather easily, and one has to look, and it just comes out. It's almost vertical. Because let's say if you have a Dieck system, large dominating y of y alphas in here, each of the y alphas itself is expressed as a Dieck system large with respect to pi, dominating pi, of object of C. Fitting together all these Dieck systems, you see, we get a double Dieck system of objects of C this time, which you can view as being a single Dieck system, you see. Large, again, large with respect to pi, because, I mean, the components were so. And of course, Dieck limits commute with Dieck limits, so you are reduced to this case. And that's about the way of seeing it. So, we have a very nice way of constructing pi-accessible categories. And moreover, I would like to call this category E for the time being. I would like to show some extra structures in this category, which is kind of nearly intrinsic. Yeah, let's say a few more things. I claim that the category C can be reconstructed from E in an intrinsic way up to equivalence. I claim that C is, what I would like to say is that C is equivalent to the category of pi-accessible elements of E. What I will say is that an element of, that's an easy exercise again, an element of E is pi-accessible if and only if it belongs to, E that belongs to the essential image of C goes to E. It's isomorphic to an element of C. Or more generally, it might not be enough, if it's a direct factor. It's isomorphic to a direct factor of an element of C. So except that we might have to add to C still direct factors of objects of C, E can be I over P can be interpreted as being C. It's pretty easy to see that a direct factor of a pi-accessible object is pi-accessible again. So therefore, if C is a Karounian category, so-called, a category in which every object admits a direct, and for every projected in an object there exists the corresponding direct factor, you see, which can be interpreted either as the existence of certain type of direct limit or of inverse limits. It's always true if final inverse limits exist, if, let's say, if kernels exist, or if co-kernels exist, or filtering direct limits exist, or filtering inverse limits exist. They need only be countable. I mean, that's a very weak condition.
What's the category that isn't?
Well, I mean, take 3 modules over a ring, for instance. You see, a direct factor need not be free anymore. All right. So, in fact, it's easy to see that end C and end pi C doesn't change up to equivalence if C is replaced by its so-called Karoubian envelope when we add direct factors, which is a particular case, of course, of taking delta envelopes. You see, here we want to add certain types of limits that can be either interpreted as direct or inverse limits, just as you prefer. Here we better interpret them as direct limits, anyway. So, if we want, we can assume that C to be Karoubian anyhow. This doesn't change neither end C nor end pi C up to canonical equivalence. And so if we make this restriction, then C is reconstructed from E as being the category of pi-accessible objects. So in other words, at least if C Karoubian, otherwise I lower P would be the Karoubian envelope of C. So we can say that intrinsically E appears as being constructed in terms of the subcategory E pi by taking end lower pi of E pi. That's kind of a canonical way of expressing E pi. And now here we could, if we wanted, replace pi by any larger cardinal. Let's take pi prime and cardinal at least equal to pi. And let's denote by end lower pi comma pi prime of E the full subcategory of n lower pi of E, which consists of those direct systems. I'm sorry, here's C. Of those direct systems xi, I of I, for which not only I dominates pi, but also the cardinality of I that must equal to pi prime. We can here kind of evaluate to see the size of an object of this category E by saying how large filtering sets are needed in order to express it as a direct limit from elements of C. So you have kind of the filtration of E, you see, by subcategories, call this subcategory, let's say, also, if we want to emphasize this notion of filtration for this field upper pi prime of E. So we have a filtration where the filtering set of they are all small cardinals. And the first step of the filtration for pi prime equals pi is just C, we started with. And now what we can prove again is that the pi prime step of the filtration has an intrinsic meaning, namely it consists exactly of the objects of E that are pi prime accessible. So here everything you see is just under our eyes in a very explicit way. The pi prime accessible elements are just those which are in this very explicit category. They form a small category. I mean, at least they are equivalent to a small category again. You see, because all ordered sets of cardinality most equal to pi prime, and the indexing the direct systems they can define and see, you see, they make up something small only. So you have this nice filtration of E by small subcategories, and let's perhaps, which can be also characterized intrinsically as being the subcategories of pi prime accessible elements for variable pi prime. And let's give some nice intrinsic properties of this filtration. That's what is called in the SGA notes a cardinal filtration. So it's we have this filtration by field pi prime larger than some fixed cardinal. And it has three properties. First of all, every field pi prime is small. I should say perhaps essentially small. It is equivalent to a small category. Second, field pi prime is stable under direct limits of type I, where I has, on the one hand, in order to be sure that these direct limits exist, we will assume that I is dominating pi, and moreover, in order to be sure that we don't get out of field pi, we will assume that cardinality of I is most equal to pi prime. All right, and then there's a third condition. Namely, that for every x in field pi second, let's say, where pi second is some cardinal larger than pi prime still, there exists an index and direct system xi with I large respect to pi prime. I now forget about pi and I recall about pi prime. And where cardinality of I is at most equal to pi second, in such a way, such that the direct limit of the xi's is equal to x. So the object of field pi second can be obtained from objects by direct limits or from objects of field pi prime, of the previous step of the filtration, by taking indexing sets that are large over pi prime, that are dominating pi prime, and that are of cardinality at most pi second. Now, whenever we have such a thing in a category which satisfies a condition L pi, let's say, if the filtration begins with pi, assume that E satisfies L pi, and if we have such a filtration, we call this a cardinal filtration. So that's essentially the notion that I have explained in SGA notes, except that here I just did things wrongly, and I had, instead of having the cardinal of I at most equal to pi second, I put a pi second power pi prime, which is kind of ugly, and which gave a certain shift, and it wasn't too nice. I didn't realize that really I hadn't realized that you could always do it with cardinal at most equal to pi second in the case that it really mattered. I just did things not the right way. And so you see that it's pretty, I think it's almost trivial to see that the filtration I have just defined in E when E is equal to n pi of psi is this model of accessible space. That's the filtration I have just described by taking the end pi prime c's over just the same by taking the EP primes, by taking for every p prime the full subcategory of objects that are pi prime accessible, that I have a kernel filtration. This comes from the fact that this EP prime is so very explicitly described as this here. All right. So I have a nice model of accessible spaces and nice filtrations on them, which these kind of filtrations which I emphasize certain properties of this filtration I've constructed there, and they call this a kernel filtration. And now we can give a theorem, a structure theorem about arbitrary accessible categories. So let E be a category, and maybe better assume now that direct limits exist in this category. And what is it? The following conditions are equivalent. Let's fix the cardinal pi frames. Pi fixed, and then afterwards we can take a variable pi. E is pi accessible. B, there exists a small category C and an equivalence E and pi C. And what is here? Yes. Now, which category in a way? Of course, I mean, this story tells it what we should take. So we can state it now intrinsically that E pi, the subcategory of E formed of pi accessible objects, is essentially small, maybe equivalent to a small category, and strictly generating. I mean, every element in E is a direct limit of elements of E pi. It's here, in fact, let's see, we have already seen that if the category is of this type, it is pi accessible. All right? And we have seen that this implies this here, because we have this model situation perfectly well in hand. So what we have to prove is that either A or C implies B. And it's here that I feel more at ease if I assume that direct limits exist in EC. So, of course, let's prove that A, and we will prove together that A implies, how should I say? All right, let's, for instance, prove that A implies B. So the definition of pi accessible was that there existed a small subcategory C and E, which was strictly generating, and such that C was in fact contained in E pi, that the objects of C were pi accessible. That was the definition. Now, as I assume that in E, in fact, finite direct limits would suffice, I think, for what we want to do. Would it? No, maybe not. All right. Now, we know that pi accessible objects are stable and are taking direct limits with cardinality at most pi. With indexing set of cardinality at most pi. We have erased this statement, I mean, this was one of the preliminary statements. And therefore, we may take as a small strictly generating category. Of course, the bigger we take the subcategory, the more generating it will be. So we can add all direct limits of diagrams in C whose cardinality is at most equal to pi. So we can in fact assume that C is stable under such kind of direct limits. See, this wouldn't destroy the smallness of the category. And of course, it will still be strictly generating. So, of course, yeah, it doesn't destroy either. It's the fact that it's contained in E pi. So we may assume C stable under limits, like limits, with indexing set cardinal I of cardinality at most pi. Here I should say that, of course, what is clear also is that A implies C. No, that's not true, that C implies A. So C implies, B implies, yeah, B implies C. C implies A, of course, because IP is essentially small and strictly generating, of course. And there we have the categories we were looking for. So we have this here. So all we have to prove now is to prove that A implies B, and that's it. That's the strongest. That's what we're doing. All right. Now we have to give a doppel story. Let's assume that we have a full subcategory of the category E, where Dirac limits of type dominating pi exist, or assume even that arbitrary Dirac limits exist. Then we have a functor, corresponding functor as we have seen, from end C into E. And therefore we have an induced functor from end pi C into E. This functor will commute with arbitrary, with the Dirac limits that we are considering here. Namely Dirac limits of in fact arbitrary Dirac limits exist here, but we are going to take filtering Dirac limits, I think, that are pi large. Alright, anyhow, we have such a functor. And the question that arises is, when is this functor an equivalence of categories? So we want to prove that when we have taken C as we did here, you see, if it was strictly generating, and if it was stable under Dirac limits of cardinality at most pi, that then this functor here is an equivalence of categories. And first, the fact that it's fully faithful, I mean, it's a very easy argument which shows, I mean, essentially the definition of the homomorphisms in this end category. It's fully faithful, provided the elements of C are pi accessible. If, call this I hat if you want, which you obtain by I hat lower pi if you want. So we say that if C is contained in E lower pi, then I hat lower pi is fully faithful. So that's kind of trivial. So in the case here, we know already that C is contained in E pi. Therefore, we know already that this functor is fully faithful. So the only problem that remains is to prove that this essentially is surjective. So we start with an object X in E, and we want to write it as being the image of an object in here. What we know, however, is that C is strictly generating in E. So we know already that X is a Dirac limit of a diagram X alpha of a Dirac system X alpha in C, which may not be filtering. I don't know yet. It's precisely in order to overcome this difficulty that we have here non-filtering Dirac systems that I assume that in E arbitrary Dirac limits exist. Otherwise, I don't quite know if things will work out so nice. And now what you do is just the trick we explained before. In order to take this Dirac system, we will take it in two steps. X, we first take the Dirac system over subsets I prime of I, which have cardinality at most equal to pi. So I look at all possible subsets I prime of the In fact, I will no longer be an ordered set, it will be a category in fact. So therefore, and it's here I think that we could have, but it doesn't matter. So I take all subcategories I prime of I such that, not necessarily full, such that the cardinality of the set of errors of I prime should be at most equal to pi. And this, of course, makes a filtering set, all these I prime. And this filtering set is dominating pi. I mean, it's an ordered set, the set of all these I primes, and it's dominating pi. And for every I prime, I look at the Dirac limit for I in I prime of xi. So this depends on the choice of I prime, and I take the Dirac limit of all those. And x is just, because we have transitivity, you see, of taking Dirac limits, we can take it just on sub parcels, you see, and then we pass to the limit on bigger and bigger parcels. All right, now this here is in C because we assumed that C was stable under taking Dirac limits with cardinality at most equal to pi. And this here is a filtering Dirac system, which is dominating pi. And therefore, in fact, here we have our element. This, in fact, this Dirac system for double I prime is an element in pi. All right, so really this comes out pretty nicely, provided we work with this extra condition on the existence of limits. Otherwise, I don't really know. I have the impression that the good condition of accessibility really is this one. So if the sum should become false, then we don't assume that there are Dirac limits. I think that the good notion of accessibility would be this one. So perhaps one will have to change the definition I gave. And now, and at the same time we see that when these conditions are satisfied, then there's a canonical way of writing E as being and pi of C. There's a canonical choice of C, namely taking the category of pi accessible objects, the full subcategory of pi accessible objects. And now let's give some corollary about functors now, about amongst those such categories. So as a corollary first, is that if you look at all EP primes, for pi prime at least equal to pi, they form a cardinal filtration. And moreover, for every such pi prime, E can be equivalently expressed as being n lower pi prime of E lower pi prime. This is because we have interpreted E as being n pi c, and so we have just to say what we said about these models. And now let's give another corollary. Let E and F now be two accessible categories, or maybe about accessible categories without fixing pi. So when is a category accessible? E is accessible if and only if there exists a pi and a small c and an equivalence of E with n lower pi c, because accessible means that it's accessible for some pi, and it also means that there exists pi, or for large pi it's also the same, there exists pi such that E pi generates strictly E, and e pi is small. But now what about functors between accessible categories, e and e prime, let's say, let f be an accessible let f be a functor. Now we will express the fact that e and e prime are accessible by picking a pi for which they are pi accessible and writing them as being end pi c and end pi c prime. And let's first express that the functor be pi accessible. So I claim that the following conditions are equivalent to say that f is pi accessible, or to say that there exists a functor from C to C prime. So C I will take to be e pi, of course, and C prime I will take to be e prime pi. The factor of accessible pi accessible elements in E respectively in E prime. So these are small categories. There exists a functor of f from C into C prime such that capital F is equal to n lower pi of small f. It's the natural extension to n objects of the functor which we have between the small categories. So that f is isomorphic to. Well, why is this so? Let's see, is it true? As I stated. No, it's not. It's not true as I stated. Take for instance, the category reduced to 1 point, you see. Then any functor from E into E prime, you see, is pi accessible, but it doesn't map necessarily the point into E pi, you see. No, I have to state it differently. Let me recall how the correct statement goes. No, I can't express in this natural way pi accessibility, I just can express accessibility. So f is accessible, and there exists a pi such that. Yeah, let's say it this way. F to be accessible, or there exists a pi and a functor from E pi to so how do we state our things? Assume that pi naught is assume that pi naught is a cardinal such that both E and E prime are pi naught accessible. Which means that E and E prime both can be expressed as n lower pi naught of some small capital C or some small capital C prime. I fix this pi naught. And then the condition is that there exists a pi at least equal to pi naught, and there exists a functor f which goes from E pi to E prime pi, such that capital F is just reduced from this functor by applying end pi, using the equivalence between E and end pi, n lower pi of E pi, and E prime, and n lower pi prime. EP prime. So the accessible functors are just those which are the canonical extension to n objects of dominating pi prime, pi, for pi large enough, of some functor between small categories. Now, this I think is pretty clear from what we have seen so far. Of course, such a functor which is accessible as an n pi f is clearly pi accessible. In fact, in order that those pi's which can be taken. All right, no, let's say it's one. There, it's clearly pi accessible, such a functor. And this comes from the study of models, and there everything is kind of just, under our eyes. Now, let's prove the converse. Assume that the functor f is accessible. And let's prove that we can find such a pi. So, let's look at e pi naught. Recall that E is just n lower pi naught of E pi naught. Now E pi naught may not be mapped by our functor f into E prime pi naught, E prime pi naught. But E pi naught is a small, its image in E prime is an essentially small subset of E prime. And therefore it's clear that it must be contained in one of the I prime pi's. Recall how I prime pi was constructed. I prime pi was just n pi naught comma pi prime, comma pi, of C prime. If we have within the category n lower pi naught C, if we have a small subset, then this can be expressed in terms of direct systems in C, where all indexing sets have a bounded cardinal. This is clear, isn't it? And therefore, the image of E pi naught in I prime pi must be contained in I prime, must be contained in such an I prime pi. And that's the definition. The pi's for which we have this expression are exactly those for which the image of E p naught is contained in E prime pi. It's exactly the cardinals for which the image of any pi naught accessible element of E is pi accessible in E prime. And now let's show that it works, because then if f maps E p naught into E prime pi, all right, and if f is pi accessible, and such that moreover f is pi accessible. So I take the cardinal pi large enough so that f is pi accessible, and that we have this factorization. And these will be exactly those for which we have this description. Because if f is pi accessible, I want to prove that f maps E pi into E prime pi. How would we get it? No, we have to go, perhaps we have to go still one step further. Maybe we can't do it just that tight. You see, the difficulty is in proving that if f is pi accessible and maps E pi naught into E prime pi, that it maps also E pi into E prime pi. Now this seems to entail a commutation of f with direct limits of cardinality at most pi, but which need not be large with respect to pi. So maybe we have to take a still larger cardinal. So let's take a cardinal pi prime, any cardinal pi prime strictly larger than pi. And now I claim that f maps E pi prime into f pi prime. Now, is this clear? Because any element of E pi prime is a direct limit of objects of E pi naught with an indexing set I who's having cardinality at least equal to pi prime, at most equal to pi prime. That's a description of E pi prime in terms of E pi naught. And now, so x, an element in here, is a direct limit of, how are we going to get it? So it's also, yes, it's also a limit large. We can replace, yes, we can write this limit as being the limit for all sets I prime and subsets I prime and I that have cardinality at most pi. And that are I is here, what is this I? It's large, it's dominating pi, no, that's all we know from the time being. Yeah? Alright. And now, well, as we know that arbitrary Dirac limit exists, I can take any subsets I prime of A of cardinality at most equal.
Well,
In a
does
fully
the opposite,
faithful functor in a way compatible with inverse limits.
I mean, the opposite of the category of sets has that property.
The opposite of category of sets takes this, for instance.
That's Boolean, I mean, that's the complete
Yeah,
atomic
it can be
Boolean.
embedded into some S prime. Let's see. Fully faithful functor from the opposite of sets into such a thing as S prime. So it would be the same as to give it, in fact, an embedding into C hat. Let's say what it means. You see, to give such a thing in S prime. S prime can be embedded itself into some C hat. You see, therefore we may assume that S prime is C hat. And this, to give such an embedding, is just the same thing. Yeah, of course it can. Yeah, of course. Whenever S has a small generating set, you see, S is embedded in C hat. No, that's it. I'm quite kind of confused. Let's take a small generating family, subcategory, full subcategory in S. To say that it's strictly generating also means, oh, that's my oops. It also means that the functor from S to C hat, which associates to every element of S the restriction to C of the contrarian functor it represents, that this functor is fully faithful. Maybe I should tell the little story of strict generators in a little corner, because there are various equivalent conditions. So the story is the following: let E be a category and C be a full subcategory. The question that it's full, in fact, one could generalize it. Why not have just the functor? And I will state some equivalent conditions for this functor. And for every object in X and E, I will denote by C over X the category of all pairs Y, U, where Y is an element in C, and where U is a homomorphism, which I was going to say from Y into X, but Y and X are not in the same category, so I should say from UY into X. But U C as being a subcategory of E, which is the most important case. So in fact, E over X, we know what it is. It's the object of E line over X. Now here we take the object of C line over X, where C is more or less viewed as being a subcategory. All right. And of course, if you have an object X and E, then we can look at the Dirac system. All these Y's you see line over X, the Y's in C, they form a Dirac system in C, and we can look at the Dirac limit, if it exists, of the H of Y's, and this Dirac limit is mapped into X because all of the H of Y's are mapped into X in a compatible way. So in fact, I have a direct system, canonical direct system in C, in such a way that it's imaged by I. I'm sorry, that's I. But it's imaged by I is of this direct system goes into X, and therefore we can ask the question: is this an isomorphism? And let's look at first condition A for every X in E. This is an isomorphism. So that's a nice condition. That means that canonically, every object of E can be written as being the direct limit of a diagram coming from C, essentially. Alright? Now I claim that this condition is equivalent with saying that the canonical functor which goes from E to C hat, which is obtained by first mapping E into E hat, by associating to every object of E the functor it represents, and then taking the inverse image functor which associates to every functor on E its restriction to C, that this functor is fully faithful. So these two conditions are equivalent. And now, if I is fully faithful, so that essentially C is a full subcategory of E, then they are equivalent also to the following. For every X in E, there exists a family of arrows. I, Y alpha goes to X, arrows indexed by some U alpha, so arrows of objects of the subcategory C into X, which is strictly epimorphic. Of course, it's clear that A implies C, you see, because if X is the limit of the IYs, then the IYs mapped to X must make it a strictly epimorphic family. So that A implies C is clear, but in fact the converse holds. It's not hard to see because assume that we have.
And that's strictly in the sense of your usual sense of strictly,
Yeah.
without private products.
No, the private product need not exist.
Yeah. But that's still the same idea.
It's still the same. Yeah. Now assume for the proof, for the simplicity, it's not essential that the private products do exist. When alpha times over X, Y, beta, you see? And then applying the same, assume that C holds. So we have the Y alphas that cover strictly X. And as now use the same assumption for all of the Y alphas times over X, Y, beta. So this can be covered by Y lambdas, alpha, beta. Therefore, we have a direct system now, where we have on the one hand the Y alphas and Y betas, and on the other hand we have the Y lambda alpha betas that are mapped into those Y alphas and Y betas. And we see now that X is the direct limit of these things here. And in fact, it's really proves that it's the direct limit of this direct system. I guess what one can prove that if it is all a direct limit of objects coming from C, then it must be also the direct limit of this particular diagram coming from C, because C is faithfully embedded in E. Otherwise, it wouldn't be equivalent. So A and B are equivalent in all cases, and they imply C in all cases, and they're equivalent to C if I is fully faithful. Now, we can give also, so if the equivalent conditions A and B are satisfied, then we will say that the functor I is strictly generating. And if I is the inclusion of a full subcategory, we will say that the full subcategory is strictly generating. So it just means that any object of X is a direct limit of objects of C. Now, in case when...
No smallness condition or something?
No, for the time being, or why? Oh, I mean, of course, it's more interesting if C is small.
And the family here, the strictly epimorphic family.
But of course, the definition makes a sense without smallness also. I mean,
Okay, but this could be large. The indexing here.
Oh, yeah, it might be large, yeah.
Okay, that's all right. Okay.
So in fact, in this definition, I don't really care so much about, I guess, about universal and smallness. It's just a definition.
I mean, when you
C hat
think
should
of,
be defined.
yeah,
So
when you think of a strictly epimorphic family,
yeah.
you think small.
By the way, if E admits the arbitrary Dieck limits, then to give a functor like this is the same thing as to give a functor from C hat into E which commutes with Dieck limits. Please remember that C hat is the envelope of C within the set of categories admitting arbitrary Dieck limits. And of course, the functor which we have here, call it, what do I know? I or Schrieb or something like this, would be the adjoint, the left adjoint of the functor that we have described here. All right? And then to say that this functor is fully faithful means that this functor is a functor of localization, that E appears as a quotient vector of C hat by a bunch of arrows. So that's still an equivalent way then of stating our definitions. And we could now go on, you see, assuming E to be stable under Dieck limits. Yes. By saying that it's equivalent to say, if E is stable under Dieck limits, then it's equivalent to ask that E should admit a small subcategory which is strictly generating, or to ask that there should exist a functor from C into E with C small which is strictly generating. Of course, if there's such a functor, then we take the full subcategory it generates. Or still to ask that we can find an embedding of E into a category of the type C hat in such a way that this should be a full embedding, in such a way that this embedding admits an adjoint functor on the left. Because of course we see that it's necessary, but also it's sufficient, because if you have such a left adjoint functor, then C which is generating in C hat, its image in E will be generating. Strictly generating. I mean, it's just a definition here, because so it's in a way very much like the situation of topo, except that here we don't insist that this adjoint functor should be left exact. It will be only, if we constitute arbitrary Dieck limits, it will need not be left exact. So that's some kind of weak, very weak, another one of topoid. And now, I gave an example of such categories. So these are the categories that have arbitrary Dieck limits and a small family of strict generators. And the opposite of Ans, for instance, has this property, and the opposite of Ab also. And these categories can be interpreted up to equivalence as being the category of complete, you say, Boolean algebras, or of compact abelian groups.
Complete atomic.
All right. So take S to be one of these squeak categories, and take S prime to be such a C hat, you see. So you have an embedding like this, commuting with arbitrary inverse limits and having a joint, and however S doesn't correspond to a algebraic substructure.
Compact spaces is another one, wouldn't it? Has this same thing.
How do you?
Well, the ultra, we think of it as an operation within the ultra filter, and then something everyone is a unique point to converge to, and let's think of that as an operation.
Does it have a small set of strict generators, compact spaces? It
Yeah,
has.
the closed unit interval.
Uh?
What do you want? Is that the new? What generator?
Strict generator.
Yeah.
What do you take for strict generators? I mean, there's a generator in the non-strict sense. I mean, it's a one-point space, and the corresponding functor to sets would be the underlying set, but it's not strictly generating. I don't think it is. You can write down an arbitrary, can you? Compact space is a No, in fact, it can't possibly, because this would mean that
No,
it's,
it's not that. What do you think? Yeah, well, the stone, let's see. What's the stone check compactification of a discrete space of a one-point space? So that's, it's hard to compact.
right, but however, you see, alright, so that shows that the set has an envelope, but it doesn't show that you have a small family of strict generators. I doubt. Doesn't look so, you see. I guess you have a cogenerator, and there's a, you have something like, yes, a rail line, for instance, or the torus would be a cogenerator, I guess. Here it's the core that works. It has a tendency to work, I guess.
No. I think some of this, I don't think I can prove it, I can't prove it right this minute, but I do think it's true.
It has, but what would be the 1 point set? No, it can't be possibly true, because this would mean that that the functor which goes from compact space to sets is fully faithful. It is not true. So it's not, the point is not strictly generating. But if you take finite sets, won't do it either, you see.
Well, I'll let you know tomorrow. I'll think of it.
But
I think it is.
so this does show that if you insist on working with algebraic structures, really, that then when we speak of substructures, we have to be a little careful. So now we should perhaps decide on what we are going to talk about next, because there are various possibilities. So either we can still go on a little bit and looking at structures defined by inverse limits, but possibly by restricted type of inverse limits, like finite inverse limits, or like by products or such things. And there are a few things to say about the relations between these and what we have said so far. So we could speak about this. We could also speak about, speak about topoi. And we could also come back to the question of the solution to our universal problems we have studied at the very beginning. In fact, I have kind of written down a proof of the existence still for the universal problems in the case when you have only finite small numbers of data, let's say when the parcel of categories d prime and d second that you give you as models for constructing limits is small, and you don't take all inverse limits, for instance, and all finite limits, but only all inverse limits up and about only limited cardinality or such things. So in this context, I've in fact fully written up a proof when you don't put any exactness conditions, and I've almost finished writing up a proof when you admit exactness conditions and of a pretty much more general type even than they considered here. So maybe it's not so interesting finally because it's not slightly technical. I mean, it's kind of cute how it comes out. And then the next thing which would be to do, of course, would be to see how one can, using this fact, how one can pass over to the case when we have no longer small sets of limits that we want to allow by some passing to the limit like we did here. You see, then we are dealing with arbitrary inverse limits by taking categories such as envelopes of categories which admitted inverse limits up to cardinal pi. So I see three different types of things we could try to discuss. So the last one is slightly technical. We will have to do some transfinite constructions, adding and see what kind of things in a well-balanced way.
I'm inclined. I feel sure those exist, but that doesn't worry me. That's exactly as you say. That's.
By the way, one has to be a little careful about the statement. The one I proposed here, I'm pretty sure it was true. The one I told you the other day was false.
So it's too big.
I gave you a statement you see of a delta, and you don't match at all the properties that you put on the categories and the properties that you put on the functors between the categories. And it's pretty easy to see.
Then you've got
that in both ways it doesn't work, you see.
Okay.
If one of them is empty and the other not, or conversely, I mean, you don't have solutions. So you have to adapt them pretty well to each other. That is, you don't have, if you want really existence terms of the type I said, you should never put in your exactness axioms the existence of objects or arrows if you don't have unicities at the same time, let's say. And the existences of, let's say, inverse limits that you assume on your categories, these types of inverse limits that you assume in your categories, they should always be respected by the functors that you take between the categories. Otherwise, I mean, you can define deltas, but you won't have any series of envelopes existing.
But I'd be very much interested in going and either continuing in the frame of the same thing here with more or less gotten the characterization for such as these categories in this form. The direction either in topoi or a combination of topoi or adding both topoi and or adding mixed types of limit.
I could say a few words about, but be pretty short about only inverse limits, but not all inverse limits.
Okay.
And which might be probably certainly the case of finite inverse limits. I think one should have understood.
Okay.
So let's do this. So let's assume that we have now delta d equals, we had introduced, to remember, d equals d prime d second, where this was a set of categories according to which we want to take inverse limits, and this was in order to take like limits. And we had assumed that the second was empty. We still assume this. We don't take any like limits. But we don't assume that d prime contains all categories that are element of the universe. We get ourselves some d prime. So the case when d prime is small will be the more interesting one. All right. And first thing is that problem 1 and problem 2 have a solution. And in fact, I will tell you how you get it. Remember that so-called this, call delta the big one as before, and now we call delta D, the one which corresponds to this term here. And now I want to construct a delta D envelope, and I will do it in terms of the delta envelope. So the delta envelope for what we are now C tilde. Remember that we had a very simple construction. We took the functors from C to sets, and we took the opposite category. And here we have the representative functors. So what you do is just to take the full subcategory of C tilde, generated by C, in terms of the inverse limits of type D prime. So you add to C all inverse limits of type D prime in C tilde. Maybe this will not be stable under these type of limits. All right, you keep adding them, and it's pretty easy to check that it's a solution of the universal problem. So call this, I don't know, this envelope called rho of C. So I won't insist on the proof of this. And the problem number 2 is dealt with in much the same way. When we had to make some errors inverted, if I remember well, to just pass through the quotient category again. That's it. Category of fractions. By first stabilizing the set of errors for the limits that have been allowed. There's one thing which is nice, it is that C is always contained as a full subcategory in its envelope. That's something which is special about the case when we are taking only one type of limits, only inverse limits, not allowing any like limits. All right. Now, another thing that goes with this is that if you look at the category that represents an algebraic theory in delta D, you see, we can take that its delta envelope, so call this R0 if you want. We can take its delta envelope, which is, I recall how you can define it also in terms of structures of series. I mean, having a theory which is defined over all categories where these types of limits exist, are for theories defined over categories on which any type of inverse limits exist. So we have a restriction of this theory to delta. And if we start with one which is algebraic, then we will have an algebraic theory. And the category R that represents it, in fact, is now again very conveniently described by the general theory which we have done before as being T being the theory T of R's, T of sets, I'm sorry. But we have to take the opposite category of this. And what turns out is that R0 is contained as a full subcategory in here. Therefore, to give an algebraic theory, you see, corresponding to a given D, it's not quite enough to give just the category of its representatives in the category of sets. You see, this would give us only the restriction of this 3 to delta. You see, this would give us something less precise. But it is the same thing as to give this together with a full subcategory of this one, or its opposite category, which will be precisely the representative category for our structure. So if this can be called S, then it would be a pair of a category S, which would be the set-centrical representatives, realizations of our theory. So S would be a more or less arbitrary accessible category, together with a subcategory sigma naught of S. But this should not be any arbitrary subcategory. It will have various properties. For instance, sigma naught will be generating an S. If D prime is small, it will turn out that sigma naught, or what denotes in R naught, is small also. So it should have some properties. In fact, the most important property is that S should be the envelope of sigma naught for all direct limits sigma naught having only direct limits of type d prime. In other words, R should be the envelope of R naught for all inverse limits. When we take into account the inverse limits in R naught that exists already of type d prime. So it's not true, you see, that if we have this R naught, if we enlarge it to a larger subcategory, that this will still correspond to a pair coming from a theory in here. But also it will still be true that the larger will still could generate R, let's say, but R will no longer be the envelope of it, exactly. So it's something, well, which is pretty subtle condition, I think. And there are two cases, apparently, in which the exact conditions can be completely made explicit. So one is a case when D prime is a set of all finite diagrams. And the other would be the case when we take all finite products, or all products, let's say. So that's the story you told me. And now let me tell you what the story is when we take algebraic structures that can be defined in terms of finite inverse limits. Because we have kept talking about these in the seminar on topos, that these make a good sense on topos, and because the morphism of topos, the inverse image function, precisely do compute to finite inverse limits, not in general to arbitrary inverse limits. Now, because D prime in this case is small, you see, we have to take only finite diagrams, finite categories. Therefore, the representing categories of algebraic series are exactly those which are small and which are stable under finite inverse limits. So there is no mystery now anymore about how to describe the algebraic series. They just correspond to small categories R naught that are stable, that admit finite inverse limits. So passing over to the opposite category, sigma naught, which sits in S, that correspond to small categories that are stable under finite Dirac limits. But now I have to give the relationship, the direct relationship between R naught and R, or between sigma naught and S. And here it turns out, when it's something very special, really, to the situation where I take here exactly all finite diagrams, that sigma naught can be intrinsically described in terms of S, or R naught in terms of R. What comes out is the following, that sigma naught consists of those elements of S, which I should call, well, 7 accessible perhaps, or 8 accessible. I mean, accessible is the technical finite primes, namely, such that Hom sigma naught is a set of all x's in S, such that y goes to Hom xy commutes with filtering direct limits. Filtering, any filtering direct limits. Now these objects in the category we will call also objects of finite presentation. They turn up a few times in the seminar on topos in the exercises mainly. So I will denote it by S lower FP. So, on the one hand, SFP, the sigma naught, can be reconstructed from S up to equivalence, which I mean is good enough. In a canonical way as being the object of finite presentation in S. And conversely, S can be reconstructed in terms of sigma naught. Well, we know it's the envelope, so we know a priori that it can be expressed in terms of sigma naught. It's the envelope by adding to the finite Dirac limits which exist already, arbitrary Dirac limits. But when there exist finite Dirac limits in a category, adding more Dirac limits is just, I have explained this yesterday, I think, the category N of sigma naught. the inclusion functor which goes from sigma naught into S, because S is arbitrary Dieck limits, extends to a functor which goes from n sigma naught into S. We have such a functor. To say that sigma naught is formed with that the limits of sigma naught are of finite presentation means that this functor is fully faithful, as you will easily see. So we certainly have a fully faithful functor. In order to say that this functor is moreover essentially surjective means that sigma naught is strictly generating. Therefore, sigma naught and S determine each other mutually. So if an algebraic structure definable by inverse limits can be defined by finite inverse limits, it can be described uniquely so. There's just one way of describing it in terms of finite inverse limits. And so presenting category R0 is the dual of the category of finite presentation within the set of realizations. And in fact, finite presentations, in fact, they really correspond to what one always calls finite presentation. Groups of finite presentation, modules of finite presentation, etc. It's just that. It's really easy. It's really the structures of finite presentation. Now, the next question which arises is when all this comes out really, I mean, very readily, I mean, there's nothing deep in all this. You just look, I mean, I have a full also references to SGA, its expose on Dieck systems and such things. Now, the question that remains is, what are the algebraic theories definable in terms of inverse limits that can even be defined in terms of finite inverse limits? And the answer is pretty clear again. These are the categories admitting arbitrary Dieck limits, S. They correspond to such categories, in which, moreover, the subcategory of objects of finite presentation generates S strictly. So there should be enough objects of finite presentation in the category, that's all. Because if these objects generated strictly, that just means that S is n sigma naught, and it's the n lobe. Of course, the objects of finite presentation are always stable under finite Dieck limits. Because filtering Dieck limits commute in this category of sets to arbitrary finite inverse limits. I mean, also because finite presentation is a particular case of accessibility, it's seven accessibility. Or 1,000 accessibilities. So if you have a diagram whose color is at most 1,000.
Excuse me, back to the compact spaces. These are compact separated spaces that I have in mind. Compact separated spaces. Why isn't the 1 point set strictly generated?
Well, it would mean, according to our theorem, that the factor which goes from, let's see, the 1 point category. We have a functor from this to the category eager interest in compact spaces. And let's look at the functor which goes from E to C head. C head is just arms of sets. That's the functor which associates to every topological space on the underlying set. Now this functor is not fully faithful, is it? Well, it's faithful, but not fully faithful.
It's got to be fully faithful.
Yes. For the same reason, you see, once again, in the case of groups or abelian groups, Z is not strictly generating, it's generating.
No, this is okay.
Because once again...
now you just reminded me of what, once I went something and straightened out in my own head, the difference between generating and strictly generating before.
Because
right. Of course, you're right, there's no question about that.
But let me make this example explicit, because I was kind of mumbling only yesterday about this. So let's take, yes, the category of groups here, let's say, or abelian groups if you prefer, and let's see the 1 point category, and let's take the functor which associates to the one object in here, the object Z in here. But let's not take this here, because of course, so of course, this functor cannot be, for the same reason, cannot be strictly generating, because the functor in the opposite direction. What are the homomorphisms of C into a group G? These are the elements of G. And so the functor in the opposite direction is just the functor which associates to a group object the underlying set, which is faithful but not fully faithful. But now take the full subcategory generated by C and E. That means I take just the objects Z and E, but I take into account all endomorphisms of it. The endomorphisms are just multiplication by integers, or rather, if I don't write things additively, if I take not necessarily commutative groups, it's raising things to nth powers. All right. And what is the category C hat in this case, when C is a full subcategory generated by this object in E? That's the category of sets on which the modulo of endomorphism of Z, which is just Z with multiplication on it, you see, raising 2 powers, you see? That's it. When that's the category of sets on which this modulo operates. And what is now the map which goes from E to C hat, where C now is a full subcategory? It's a map which associates to every G, the underlying set, but on which we make operate the modulo of all integers n by associating to every integer n the nth power map on G. And now, to say that Z is strictly generating would mean that this functor going from groups to sets with some types of operators is fully faithful, but it isn't. It's quite easy to see, but if you take Z squared, for instance, already, then there are maps of Z squared into itself that commute with multiplying by n, but which are not group endomorphisms. So here, really one should be very careful about distinguishing generating and strictly generating.
What's just generating the definition, and that's
The one I took was that the functor is faithful.
just faithful here. Right.
No, conservative I took, I think. Well, no,
Okay. Okay.
I don't
So
know.
that's the term. That,
There are
well,
5 or 6
Right.
definitions of generating that coincide if you have certain exactness properties in the category. So most of them are properties of this functor equals to C hat. So you can, the strongest which I considered there was that this functor was fully faithful, that's strictly generating. That's faithful would be generating by epimorphisms. Yes, generating by epimorphisms. This would mean that every object at E can be covered, admits a family of epimorphisms whose sources are in C. That would mean that this functor is faithful. That this functor is conservative means that the homomorphism from x into y is known when we know its action, and when we know how the xi goes to x, what is its compositor. Now, that's what I call, I think, generating when this functor is conservative. It's turned out that this was the one notion of generation that was used the most often in the seminar. And then we have also the fact that this is, what was it? You see that this was conservative for monomorphisms, or that this was conservative for epimorphisms. Maybe that the monomorphism in here, which becomes an isomorphism, was an isomorphism before. This was a topo notion, in fact. This means that if you have a monomorphism in E, and such that every morphism from xi into y can be factored through x, then this monomorphism is an isomorphism as well.
what did you call that?
Generating, I think,
Because that was
four monomorphisms. Not bimonomorphisms, but four monomorphisms.
testing. It would test whether a monomorphism is an isomorphism.
Yeah. There is a whole section SGA for x posing 1, I mean the general nonce of
Wasn't
categories.
that the original part of the original definition of generating or having a generating family of a topos?
In the topos, all these
Yeah,
conditions are equivalent
I saw it in the-
because they are the exactness properties. If you assume that epimorphic families are strictly epimorphic and that and maybe that a morphism can be decomposed in
Yeah,
epimorphism followed by a monomorphism,
Then that's
then everything is, all the conditions, I mean there are 6 conditions I think for generating that are being considered, they are all equivalent. But in this context, it's strict generation here that seems the most important.
Now, let's see, what do we take for the strictly generating subcategory, say, of groups?
In groups, I mean, you take 3 groups, I mean, that's the best one.
Makes the best one, 3 groups,
Yeah.
all 3 groups, that's all.
Of finite, no finite type.
Of finite type, yeah. Okay.
And you take the standard ones, which are generated by the standard set of n elements by n. So this would be Lazar's choice. All right. So this much about the structures that can be defined themselves, the series that can be defined by finite inverse limits. What about morphisms between these series? So these morphisms between t and t prime, they just correspond if t corresponds to s and t prime is to s prime, and if sigma is the set of functors of finite presentation in S and sigma prime the subcategory of object of finite presentation in S prime, we know that functors from morphisms from T to T prime should correspond to functors in the opposite direction from R prime to R that are left exact, that commute with finite inverse limits, or what amounts to the same, to functors from sigma prime into sigma that commute with finite like limits that are right exact. But on the other hand, as S prime and S are the canonical envelopes of sigma prime and sigma, they are n sigma prime and n sigma. These functors are exactly the functors from S prime to S that commute with arbitrary like limits, and that moreover turn objects of finite presentation, map objects of finite presentation into objects of finite presentation. So the category of morphism from T to T prime with respect to this type of categories is a full subcategory of the category of morphism of T to T prime with respect to this. Namely, it's a full subcategory of the category of all functors from S prime to S that commute with arbitrary like limits, consisting of those functors only that transform objects of finite presentations into objects of finite presentation. And I mean, it's just like if you take the enveloping group of a monoid, if the monoid of finite presentation, you expect the group that you have finite presentation. I mean, there's no more to it. Of course, this functor here is not the functor which goes from structures of type set-theoretic structures of T to set-theoretic structure of T prime because of this homomorphism. I mean, it goes in the opposite direction. In fact, what we directly will have, of course, in terms of this, is an arrow like this, which will be a functor that commutes with arbitrary inverse limits and that is accessible. But this functor will have an adjoint, and if you really want that this morphism should be a morphism of algebraic structures of this type here, then moreover, this adjoint functor should transform objects of finite presentation into objects of finite presentation, no more, no less. And now, what about the case when D prime equals finite discrete diagrams categories, if you want, or arbitrary discrete categories, or discrete categories of cardinal at most pi. So we have so if we admit ourselves, let's say, products with some cardinality restriction, possibly. Well, then there's one very special feature that occurs, namely when we make our construction of an algebraic series stepwise, that whatever arrows we add, you see, when we give ourselves more data, more arrows, with axiom on these arrows, which we can then add later, you see, it will never add new objects. Because when whatever arrows we have between objects, you see, we can't, if the only type of limits that we allow ourselves are products, we can't use them in order to construct more limits. We just have only products. We don't have more finite. If we took finite products, for instance, we'd have a lot more. So therefore, in our whole transient construction, you see, the objects that we have originally won't change. Except that if we start with a basic set I, you see, so we have base objects, let's give them name xi, although they will be variable after a while, but they're just letters here. Base object xi parameterized by I. Let's take the simplest case when I is just reduced to 1 point. So I assume we have just one base element. Alright, so we have just 1 point here. So we have to take the envelope of the category of reduced to 1 point with respect to this here. That is, intuitively what we have to do, in terms of one base object, we have to take all products that we allow ourselves to take. So this category would be the category of all xn's. And what are the homomorphisms from xn into xm? Alright, as I declared that xm should be the m's power of x, I have only to declare, so an homomorphism of xn into xm is just a set of m homomorphisms of xn into x, so I have just to say what the homomorphisms of xn into x are. And these, of course, for the time being, we have nothing else but the n projections of xn into x. We don't, in fact, that would correspond to the following. Remember what our general description was of the envelope of a category. We have to take hom of I sets naught. Now I is reduced to just 1 point, so we have to take the category opposite to the category of sets. Alright. When we look at I goes to this associates to the unique element of I, associates in fact the set that has just one element, but viewed as being an object in the category of opposite to the category of sets. And when we look what this element generates by products, let's for instance say finite products, to fix the ideas, well, that amounts to the same that we look what this element generates in sets by finite sums, and that's just all finite sets. So the category which we are working with is the opposite of the category of all finite sets. We could also say that we take the set-centric realizations of our structure, namely sets, that are finite presentation in the category of sets, but that's just the finite sets. And then we take the opposite category of finite sets. Alright, and so that's another way of describing what I did here. So that's the first step, when we describe an algebraic theory as represented by something. So the something here is the category opposite of finite sets. If we allowed ourselves cardinality up to pi, the category would be the category of sets of cardinality at most pi. And if we allowed ourselves arbitrary products, we would take just arbitrary sets here. Is this clear? Alright, and now the next step would be to either add some axiom already on these arrows. There are not too many, so that would be kind of put it together rather hard. Or add some more arrows. Alright? Now when we add some more arrows, as I said, I mean at every step, the objects have not changed. What we will get ultimately is the following thing. We have, let's assume we take only finite products. We have just the fixed set n. We have, which indexes the objects x to the n. And and we have a category whose underlying set of objects is just n. So we have, but moreover, we want that the object indexed by n should be the nth power of the object indexed by 1. And now I should describe what homomorphisms from xn into xm are. And there, because of the restriction I said, there are known when I know the homomorphisms from xn into x. So for every n, I should have a set which I call Hn equals hom of xnx. And then, so there are intuitively functions of n variables, you see, that can be expressed in terms of our structure. And then I should tell myself, we should give ourselves how functions of n variables can be composed. So how we can substitute. Once we have this, then and we should of course have transitivity of composition of n-valued functions. And once we give such a datum, then we reconstruct this category structure. Now such funny data you see, having for every n a set Hn, and between these Hns certain pairings you see, which we call compositions, has been studied 20 or 30 years ago by Lazare. He calls this analyseur in order to study precisely some types of algebraic structures. All right, but here I took the case when we just admit finite products and one base object. So these structures are just classified by analyseurs, by categories. The underlying set is n, and such that the nth object is in a given specified way by giving explicitly the n projections a product of n copies of x.
I might add that's what Lawvere used. It's Lawvere theory.
And so the realizations of the structure in any category which admits finite products are just determined from this particular category to the given category as convoluted with finite products as it should be. And now, in the same way, we allow ourselves more products, and if we give ourselves then just finite products, or if we give ourselves more base objects than just one, if we give ourselves two base objects, then we should allow ourselves objects of the type xn times ym. And more generally, if you have any family of base objects, then the category we start with would be the category of finite sets to the power I. Perhaps it's the opposite category. You see, it's a category stable by finite products generated by I. And now the problem which arises to what are the pairs R0, R, which correspond to algebraic series definable, let's say, in terms of finite products, is somewhat more delicate than before. Or what are the pairs sigma naught goes into S? So certainly the sigma naught should be, R0 should be stable under finite products, let's say, if we take finite products as the basic operations. That means that sigma naught and S should be stable under finite sums. Moreover, sigma naught, I guess, should be strictly generating in S. But these properties are not enough. In fact, there is a characterization due to, no, I always forget, to Lawvere, then is this?
More or less,
yeah. Which characterizes exactly the pairs like this that occur from a category with products by taking the end law. And maybe you tell the story in a few words.
He doesn't characterize them that way. That's the funny thing about it. Not in terms of the generating a subcategory. I'm not sure whether there are several theorems. I have to know whether or not we can.
So if you assume that there's just that sigma naught is reduced to just one object. I'm sorry, that wouldn't be generated.
No, exactly.
Yeah, it's generated.
You can
If
characterize.
there's just one base object. Yes, I see that. what he did in fact was not to characterize the pairs
Not-
sigma
not-
naught S,
no.
but the pairs
The pair
I,
is
comma
I,
S.
comma S.
Yes.
That's-
Where I is where I is a set of base sets.
okay.
So sigma naught would be the category generated by I taking finite sums. So that's it. And the characterization is, if I remember well, that, let's see, well, I mean, you told me the weakest condition possible, but let's see, what I remember is that S should maybe have the usual properties of having arbitrary like limits and inverse limits anyhow. We know at the end it will have them. And on the other hand, now there are two important special properties, I think. That is that equivalence relations are effective.
Right.
And universal, one should add,
No, that's in the corollary.
but they turn out to be universal.
Yeah.
They will be universal, but effective would be enough. And B, that that I is strictly generating, I guess. Something like
No,
that.
it's not strictly.
Oh, it's
You
generating.
just said, you just what you just
I
said.
is generating,
Yeah.
but maybe when we say that it's tests,
Test effective, test
that's
effective.
enough. That implies it that it's generating.
Yeah,
I
that's
think
right.
so.
And then in this case, yes, that's every equivalence relation is effective. We can,
For every morphism X goes into Y in E, yes.
it's an effective.
U is an
epimorphism.
effective epimorphism, if and only if.
I.
For every I in I, hom Ix to hom Iy is surjective.
Yeah, that's true.
So which means that the limits of I, on the one hand, are projective with respect to effective epimorphisms, and second, there are enough of them. I mean, they are kind of.
This implies every object can be expressed as a quotient of copies of.
That's kind of true, because now there's a whole story about these things, which perhaps.
You need a tiny bit more, because this right here, and that's just enough to guarantee.
That's not quite enough. Oh,
Well,
yes,
you-
and then there's a C, yes. In order, well, let's
No,
say
you
that
threw
C-
that in, you threw that in, I'm sorry,
the
you
I-
threw that, you threw that, you
the
threw in
I,
all the
let's say,
limits
our
you
final
need, that's all.
presentation. Yeah.
So if you want to get
limits
that,
exist,
yeah.
and all I's, that I is contained in EPF, for instance.
Yeah.
In fact, something slightly, in other words, weaker should suffice. Maybe if you have an element I that is mapped into a sum of elements I alpha, then it should factor through a finite subsum. Factors through alpha in lambda prime, where lambda prime is finite, of I alphas. Which of course, if the object is of finite presentation, it should have the property. Now apparently one can considerably weaken the limit requirements by assuming that only some
Minuscule.
some very restricted types of limits exist. But I
Finite,
guess sums,
you could eliminate,
sums, I guess, should exist.
well,
Some
all you
infinite-
need is sums of copies of copies of I in this case.
Very nice.
It's quite difficult, it's quite delicate to throw away all of those, all the direct limit considerations.
And it also means, so that's one characterization. Is it in the literature or not finally?
Yeah, that's.
And it also means, if I understood you well, that the functor from S to sets, power I is is base sets, that is given by, well, in terms of this pair IS, by assuming to have an object of X, the set of all hom IXs. One small I goes to capital I, you see. I mean, that's the underlying, that's the functor which assets to every object viewed as being a structure of a certain type, the set of the underlying system of sets. See that this functor should together with its adjoint functor, which we know to exist if the situation comes from a structure, algebraic structure, that this should be a triple pair of adjoint functors, which more or less means that this functor here is faithful, so that resembles the property that I is generating. And moreover, it should commute with effective epimorphisms. It should transform effective epimorphisms in surjections.
And reflect that property.
Well, when you assume it's faithful or conservative, that doesn't do it.
Or if you put it in conservative, you
Yeah, all right.
Deal with this, please.
well, the theorem of the triple ability occurs in a paper of mine. And the original formulation linking it directly with algebraic theories. And that such as with, is in Lawvere's thesis.
It's a funny situation.
So where is that?
Which allows you some symmetry constructions there. And so to give such an algebraic structure is the same thing as to give such a functor from sets to sets with this extra structure, such that, however, pi should commute with filtering diacritics.
Yeah, that's to cutting it back down.
Yes, that reflects this condition here. If we admit arbitrary products, then we can throw out this condition, or rather, if we want really algebraic structure, then we could replace it by insisting that any such homomorphism should factor through a subsum corresponding to an indexing set with bounded cardinality. Bounded cardinality independently of the cardinality of lambda, of course. That just means that we want. That's the arrows that we want to, by which we want to define our structure. Should be a small set. They should be a small set.
And can you link that directly to accessibility? Could we?
Well, I guess it just means that pi is accessible.
Yeah.
That's it.
Yeah.
I guess. If S is accessible, you see, then when we have a pair of adjoint functors joining it, relating to another accessible category like sets, then, I mean, both of these functors must be accessible, so the composite term must be accessible.
Right, okay, and then that's, then that takes care of it then.
Yeah. So maybe either tomorrow or after I leave, perhaps, if there's interest among the people who are around, you could give a little more, go a bit more into this story. I think it was really quite nice. And the relation between this and mathematical algebra with pi.
What about what about, let's see, back at the beginning you had I guess maybe that's the next step, but with the topoi. With topoi, that's the.
So you would like us now to speak about topoi?
I would, but I don't know.
Fine. All right. So, I guess I have said at least about what I know in this relation. And there's, however, one question which I didn't quite. I heard about a theorem of Dürkhoff's which said that if you have a category of algebraic structures definable just by products in our sense here. And call S this category. And if you have any subcategory S prime stable by arbitrary inverse limits, so products, let's say, stable by products, by sub-objects and by quotient objects, that then S prime can be defined by equations, as I would say, namely, I would think that this means by adding axioms, namely axioms that some arrows are equal.
Well, precisely because it's going to be a full subcategory, or one, at least it's going to be, say, a full subcategory. It's going to be a quotient category of S, but it's going to satisfy additional conditions.
Let's see, it's a full subcategory of S. Right?
Yeah, and it'll have enough to join.
Why will it? It's not clear at all.
And not from that description there, but from other considerations. Yes.
But is it true? I mean, I doubt it's true, first of all.
Yeah.
Is it really true?
The thermoburgers, at least I've never seen. It's been sitting in the literature for years and years and years, and there's several proofs of it. It's the counterexample you had in mind wasn't closed.
Well, yes, I guess no,
Yeah.
you're right. In
Yeah.
fact, I think there's an adjoint, at least in the case I think of, there's an adjoint functor.
They
Because
exist.
for every object in S, let's say, we should send it into an object of S prime called Y prime in a universal way. And now, what we will do is to take all possible quotients of X that belong to S prime, and we take the inverse limits of these quotients. Probably should work.
Yeah, it's a tiny bit delicate, but that's certainly the standard way you can view that left adjoint.
All right. So assume we have that joint then we will know that in S prime there are generators. So it corresponds not quite to what we would call an algebraic theory here, but that doesn't.
It corresponds precisely with those algebraic theories that again have that finite product. It's this additional weak condition, but the functor from S, underlying functor in the set,
Yes.
is exactly those subcategories that satisfy this same condition here. That's been picked up. Whereas, for example, a good sort of the standard example of a full subcategory of one that you can, so take for S abelian groups, and take for S torsion.
What?
Take for S abelian groups,
Yes.
and take for S torsion free abelian groups.
But which is S? I'm sorry. Abelian groups.
Abelian groups.
And
the
S prime?
S prime, the full subcategory.
But that's not stable under quotients.
That's right, and that's the standard example of the one that fits, that does not fit into that theorem, and is not definable by.
I see. So the point is that in fact S prime can be defined again by products.
Yes, if it's a Birkhoff, that's the Birkhoff.
Oh, yeah.
Birkhoff is a Birkhoff
That's
system.
kind of evident to check.
It's not difficult to check that it satisfies this condition here if it has that property.
And so.
So you see one, for example, your statement about, so just consider the other way to formulate this effective epimorphism. That just says that U of it is an effective epimorphism, if and only if. So you're saying your quotient there composed, say it's stable on the quotients.
Yeah.
Just take a diagram that you want to be tested as an effective epimorphism.
You want to check now these conditions?
Yeah,
well, I'm willing to believe them, but I
Okay.
try not to understand the sequel. So let's see.
Sorry.
So if S prime, what about the base objects? So there's images by this adjoint of the base objects given S. That's how it goes.
Yes.
All right, fine. So now, all right. Then I guess we must have, this inclusion comes from a function in the opposite direction between the representing function R's and R primes, the analyzers of Lazare, if you want. And because this is full embedding, this I guess will be surjective on arrows. Anyhow, it's bijective on objects. It will be surjective on arrows, that's it. And therefore R prime is deduced from R by equalizing certain arrows. And that's the equations. But we don't know in this setup, I guess, yes. We don't know if you can do with a small set of arrows, of equations. Like the large set of equations.
No, that's. But if you started out with S being, small set of equations, no, I think you do. No, I think
Why?
you do.
As, yeah, I mean, let's drop the final
Without a-
condition. Well, we have it on. Let's assume we have it on ice. Okay. So, why should it be true in S prime?
Again, it would, what should what be true?
This axiom here, let's say, about possibility of factorizing through any morphism of a generator through a finite, not finite, into a sum, through a subsum of finite cardinality for the netting set.
I think so, but you're right, yes.
Of
Yeah,
bounded
that-
cardinality.
That's certainly the case. That's funny, if that, it is conceivable that there's not be. In terms of the phrasing of the Birkhoff theorem, the Birkhoff descriptions, again, by finite, requires the finiteness. So if we're talking about the things that came from that, his only idea, so-called Birkhoff varieties, if I remember correctly, were genuinely required finite products. And then there was, the generalization. But that's, I think that
Oh no, I'm completely confused. In fact,
that's
here
fine.
we have. I mean,
Well, now you're not, but
products.
but the Birkhoff theorem doesn't make any characterizations in this case.
I mean, the cardinality pi that bounds the products being used in order to define composition.
The Birkhoff theorem holds for one base set. Anyway, I mean, it was an original statement, but.
But that's not the point here. The point is
Right.
what kind of products one allows.
Finite. Birkhoff sense.
So
is
then,
finite.
I see. So for S prime, then it will be
But
finite
he was
too.
talking about a subcategory of a category, that had been already defined by a finite product.
And then the subcategory can be also
If it's
defined.
satisfied, if it was,
I see.
stable on the products, so-called subalgebras and.
I see.
and then-
I see. Then if we allow ourselves products up to cardinality pi for S, then the same will hold for S prime, I understand.
If it's a so-called Birkhoff subcategory.
Yeah, S prime being stable under products, subobject and quotient.
That's part of it, and I'm sure that's implicit in Birkhoff theory.
Yeah. Oh, that's kind of nice. But how funny that. What about the case when after all, it doesn't make a sense if you have an arrow in R, you see R is this analyzer.
Yeah,
You want to make an arrow invertible.
all right, that's what you,
Yes, to add an inverse of an arrow.
okay, is that what you're doing? All right, yeah.
Yeah.
Yes,
Now apparently, and but that's not stable under, that something becomes an isomorph, that something is an isomorphism as an axiom, may not be stable by passing to sub-things or quotient things. Yeah. It's funny because, we get in this way subcategories S prime of S that are full subcategories stable under products, but that's it, but not stable under,
Anything
not
else?
stable under sub-objects or quotient objects. That's it.
What if you just look at,
It's kind of funny that you exactly described it by Birkhoff, you see. I'm a little confused though. I don't quite understand it yet. How did you know in Birkhoff's case that the map on the arrows is surjective?
on the represent, which on the represent?
On the representing categories, R goes to R prime. Well, this wasn't clear. It doesn't follow from the fact that this here is fully faithful, as we see by the example when we invert an arrow here.
Nope, but it's,
It's true. or one has to prove.
But you, obviously, you know, there are many more subcategories, full subcategories with even with left adjoints for S,
Yeah.
described this way, than there are these that satisfy the Birkhoff.
No, yes, I understand. So I mean, what Birkhoff's theorem achieves is to single out exactly those subcategories which correspond to axioms that equalize errors.
That's, yeah, I'm sure that really, that's probably the way to think about it that way, yeah. Yeah, things don't get inverted. This is like, you know, this is like abelian groups contained in groups, or monoids contained, viewed as, you know, as being a subcategory of groups, stuff like that. I mean, groups is a subcategory of monoids.
I don't know exactly in this context what are the subcategories S prime and S full subcategories that correspond to same base objects, you see, to algebraic substructures over the same base objects. So they should certainly admit, the inclusion should admit a left adjoint. That's one thing. The new base objects here should be the images of the I here.
Yeah.
And what else? And the composite functor should satisfy these axioms again.
Over sets.
Yeah.
But this,
Sets to the I.
But this curious.
Sets to the I.
Right, okay, but you know, but I don't know. That, this property, you know, is not a,
And it
doesn't impose.
turns out that Birkhoff's condition implies this.
Yes.
That it's a composite functor.
This is triplable.
Yes. It's kind of a subtle, seems some kind of a subtle condition.
Yeah, but only.
Birkhoff's, I mean, this is a very simple one, but I mean, if you want also not only to equalize errors, but also as other axioms to make errors invertible, then well, you just have to say that this composition is triplable. That's what it means. That's what it
Wait, what was your conclusion with that? I didn't, did you repeat that? Just tell me just what your.
I was
in
looking
order-
now, you see,
Right.
I had a theory T
Right.
corresponding to S, a theory corresponding to, let's say, something like finite products. All right? And now I want to characterize all full sub-theories corresponding also definable in terms of finite products. And I guess, yeah, these T prime, as we know already, they would correspond to full subcapital S prime of S, but together with sigma prime and whatever it is. I'm now looking for which are the full subcategories for which
Okay.
it works.
And your conjecture, or your feeling was that it corresponded to what? What was the relation between, what could I do?
That this inclusion should admit first of all, of course,
Right,
a left adjoint.
right.
This will give us the basis sets in S prime.
Okay.
Because we take series over fixed basis sets I, which shouldn't, so the base set shouldn't move, you see.
Mhm.
And then perhaps just to ask that the compositum here should be triplable again. Maybe even that the existence of the joint here is a consequence of that.
That's the consequence of that, yes.
That would be it probably.
But in terms of, you know, what the relationships between the two axiom systems are, between the analyses et al., what we will be doing.
Well, there's a general story that we can get, that we will have to get from R to R prime by adding axioms.
Okay, but adding axioms, yes, and making things isomorphic too.
Adding axioms, then we have just two ways of adding axioms, making two arrows equal,
Or making things
or
isomorphic.
making an arrow invertible.
Okay.
So making two arrows equal, that's Birkhoff's thing. And making,
No, but that's what I was saying, because there's a thing.
but there's another type of axiom that we have, namely making an arrow invertible.
No, that's exactly what I thought you were distinguishing, but what I'm thinking is I'm not clear. Because, for example, a thing that clearly satisfies the Birkhoff thing, if I'm not mistaken, is suppose I put here groups, okay, and consider that as a subcategory of monoids,
Yes.
okay? But I think as we pointed out one day, our description of groups had to do with making a certain Aron isomorphism,
Yes.
2 Arons isomorphism.
Yeah. But you can describe groups in monoids, I think, by equations. I don't think you can. It's the existence of something. I mean, it's of an inverse. It's something like an existence. I don't think that.
Okay. So I'm again trying to get the distinction you're making. Okay, so that doesn't correspond.
And indeed, the groups in monoids, you see, they're not stable undertaking sub-objects because you have submonoids of groups that are not groups. Z plus
Of course,
Z is a
all
monoid,
right.
it's not a group. So that's.
Oh, you're quite right. No, you're quite right.
I think that's a good
Yeah.
illustration of Birkhoff's. I mean, that's established.
Yeah, well,
Without using Birkhoff's, I mean, this makes it pretty clear
yeah.
that groups cannot be described among monoids by just equations, because if it could, it certainly would be stable undertaking sub-objects. Alrighty, now should we go on working sum? Yeah? Speaking about topoi, or do you think? Do you feel like going on? Yeah? Do some? Everybody feel like going on? Do you?
I probably
Yes, so but,
What are you doing tomorrow?
I don't know. Already.
He will take a note.
She will tell you everything. I have no idea what we will do tomorrow. We will see tomorrow. You can speak a lot about topoi.
Well, we've just got an example too. No, it singles out something else. It doesn't, for example, that gives a counterexample to just this statement, this naive statement over here. Because that's obviously right. That all that you're saying is the Birkhoff theorem is. Oh yes, that's true. Although the Birkhoff theorem singles out exactly those subcategories with the left adjoint such as the composite functor is triple. That's exactly what it does, nothing more. It does not say that every single one can be obtained that way.
No, it says something. I think so the situation is described as more restrictive, I think.
Yes.
It's more restrictive than that one. The situation that Birkhoff's theorem describes is more restrictive than only the case when you have the subcategory. S prime and S in such a way that the composite with sense how I is a triple group. It's something more particular than that.
Because this is
if you take that, if you take groups sitting in monoids, this would be
Friends,
true.
that's
However,
true.
it doesn't correspond. Yeah. Maybe you like you like us to finish, don't you? What about I mean, there's no rush neither to finish these.
No, I think your statement was exactly.
We have to hold.
Oh, I would want you to finish, yes, I don't want you to cut it short, okay? I brought a book to read.
What about you?
Oh, no, it's fine.
Right.
No, how do you feel?
You want a little while more?
Yes, no, it just singles out exactly those that can be obtained by adding equations.
First equations,
Just,
yes.
that's,
Equalizing.
yeah, I think now that you remind me of that, I think that's pretty much, that is the way the classical people in universal algebra, I think, describe those things. Imagine?
So, judge it by copying it to mine.
I've forgotten all my universal algebra.
I never knew any.
You seem to have intuited it pretty well.
All right, now let's start a little bit on top way. So we take now the case where delta equals top within a cut. But recall here, so these are categories. Well, I wouldn't say delta equals top because let's say pseudo topoi, because we want to have deltas that are defined by exactness properties. Best in the topos, I suppose, more over the existence of generators.
So what's your actual definition of a pseudotopos, just to be clear?
It's a category which where the axioms A, B, C of Giraud are satisfied.
What's the exact
Maybe,
explanation?
It should have arbitrary indirect limits, maybe, and and at least finite inverse limits. That's it. And there should be A was that there should be more. So that was A. I mean, the existence of some limits.
Mm-hmm.
Then B was that there were direct sums. That these direct sums were disjoint and universal. And C was about the constellations. The constellations should be effective and universally effective. I think that was all.
Okay.
That's really beautiful, in a way, beautiful thing, because it looks so very weak. All right, and this then implies a lot of other things, and especially so if they are generators. But of course, we shouldn't. I mean, the argument category that is going to vary. It's not too reasonable to assume generators. Generators will be in the presenting categories corresponding to theories. But however, we have a main interest, of course, in these, however, that are topoi. Now, the functors that we have will be functors that will commute with arbitrary direct limits and finite inverse limits. Really, these are the basic limits that we are considering. But a functor like this, we will always put an upper star perhaps to the functor and recall that they correspond to morphisms of topoi that go in the opposite direction. After a while, I think, when we make the joint with the, with the John Duskin or universal algebra, it doesn't make a difference. But when we want to have a geometric picture of the situation, we don't recall where the geometric arrows go. All right, and so we are interested in algebraic structures defined in terms of this. So they are just, we have on the one hand general theories that are just something like complement functors going from delta to cut, which associates to every topos or even pseudo-topos a category TE in a functorial way with respect to E whenever we have a morphism from E into F. A functor from E into F, I mean by this, for the time being, that commutes with arbitrary direct limits and finite inverse limits for this functor F star. This should define as a functor from T to TF. I just recall the nonsense definitions. Which would mean, however, the geometric arrow goes F, E and F are topoi from F to E. So we have a corresponding arrow from T to TF, and we have a group in a topos, and if we have a morphism from F to E to this topos, then we have the inverse image of this group. So when we view as topoi as being geometrical objects, then T of E becomes quantified on the topos. And when we say that a series is represented by a topos, so that we have a classifying topos for this series, then this will mean that we have a universal element representative of the structure psi and MTE, and that for every other topos F, an element of TF is essentially the same thing as to give a morphism from F into E by taking the inverse image of the structure. We just make the arrow reversal. But when we have reversed arrows, you see the category HOM underlined EF, or this full subcategory of HOM underlined EF, consisting of those functors that satisfy our ejectors properties, is not the category HOM underlined top of FE, but it's the opposite of it. When we described morphisms between arrows between morphisms of topoi, I mean, it was more reasonable to define them in terms of the Dieck image functor rather than in terms of the inverse image functor. And therefore, when we claim that a type of algebraic structure corresponding to delta can be represented, a type of Syrian type of structure, perhaps not algebraic a priori, when we claim that it can be represented by a topos, I mean. Alright? This means that T of F is by the natural functor equivalent not to HOM underlined top FE, but to the opposite of it. So that's a little technical detail. The functor, of course, is the one which associates to every morphism of topoi from F into E. The inverse image, that's the functor which associates to every morphism of topoi F. The inverse image of the universal structure, F upper star psi. But the correspondence from F to F upper star is consolidated. So therefore, we have here fiber categories over top that we shouldn't call it two representable, but two co-representable, something like this. So let's see, opposite category as a functor of the variable f that we will be able to represent. Right now, this is just to fix some terminologies. Now, let's look at the two main technical problems and see that they have solutions. So problem one is to take the enveloping topos, or the enveloping pseudotopos, which will turn out to be a topos, of course, of a small category. So rho lower delta of C a small category, exists. And let's show how we can construct the solution. It will be very, very simple. So first case, assume that C has finite inverse limits. Or what amounts to the same, C in fact is a representative of a type of algebraic structures that can be described in terms of finite inverse limits. Remember that C is small. So C just corresponds to a type of structure groups or categories. Such a thing that can be described in terms of finite inverse limits. Alright. Then I claim that rho delta C can be taken to be C hat rho delta C is C hat with the canonical functor from C into C hat associated to every object of C. The functor it represents. Of course, C hat is known to be a topos. It satisfies our exactness properties. It's in delta, moreover, it has small generating set, then we see itself. So let's prove it. So let E be a topos. I should say a pseudo-topos, but unfortunately the references will be to topoi. That's kind of unpleasant. But I think it would be easy to get the result you see for pseudo-topoi by going to one universe higher and look at the topos E generates in the higher. I mean, there is always such a thing too. In fact, what I'm going to say, the kind of things I'm going to use, I think, are they shouldn't make any semiotical difficulties. Well, I mean, should be really easy to reduce in the case of topoi. All right. Then we know that that's it. Let me give a little something that I should have stated in the last talk about topoi, which I didn't. That's about, I explained how to a side tree can associate a topos, but I didn't explain the story about morphisms of sides. And so, let me explain it now. So, let's see. Let C be a side, and let E be a topos. Then a functor, or let's say it's the following way, and let C prime be another side. Then a functor from C to C prime is said to be continuous if the inverse image on C by the functor f of any sheaf on C prime is a sheaf on C. That's by definition means that if f is a sheaf on C prime, so f an element of C prime tilde, a pre-sheaf that satisfies certain exactness properties, then f composed with f is a sheaf on C. And now it can be shown that this depends only on the corresponding functor from C into C prime tilde by composing f with the canonical functor from C prime into C prime tilde by associating to every object of C prime the sheaf it represents, or if it is not a sheaf yet, the associated sheaf to this pre-sheaf, so called as epsilon lower C prime. Therefore, it's a condition, in fact, just on a functor from C into a topos. And that this means also, so this here, the first thing was a definition, now the second is something like a little theorem, I mean, it's a proposition. It means also that this compositum functor into C prime tilde, where we have epsilon C prime here, can be factored into a functor through C tilde, here f, or this f tilde, where f tilde commutes with arbitrary like limits. These are the so-called continuous functors. In fact, such an f tilde will be unique up to unique isomorphism. In fact, the functor which goes from the restriction functor to C, or the composition functor with epsilon C, which goes from the category of all functors from C tilde to C prime tilde that commute with arbitrary like limits, to continuous functors from C to C prime tilde is an equivalence of categories. So continuous functors from C into C prime tilde not only don't depend on C prime, but C prime can be replaced by C prime tilde, but they don't depend on C either. They just correspond to functors from C tilde to C prime tilde. that commute with arbitrary like limits. And there's most things that you can define in terms of size, the really important things, that turn out not to depend on the size but only on topos. That's the first step. Now, what are the continuous functors from C to C prime tilde? One can give various characterizations. The nicest one is when C and C prime admit finite inverse limits, and if f commutes with these. Because in this case, f is continuous if and only if it transforms a covering family into a covering family. You must think, you see, as the most standard case, the case when C and Z prime are respectively the size of open subsets of the topological space X and X prime, and this map comes from a map from X prime into X, a continuous map from X prime into X, and then by taking the inverse images of open sets. That's the standard example, where we have commutation with finite inverse limits. In fact, when you don't assume that there are finite inverse limits, the property is the following. It's kind of nice. It should be true that for every X and C, and for every covering sieve of X, or every covering family Xi of X, if you want, but we look at the sieve that it generates. But then we look at C over X, C over R, I'm sorry, we are looking at all objects of C that lie over R. That means objects of C that lie over X that can be factored through Xi, to one of the Xi's. See? All right? And we know, let's write the criterion. Let's first write the necessary condition. We know that the sheaf associated to X, the image of X in C tilde, is a direct limit of all epsilon y's, where y goes through the category C over R. That's in fact a characterization of covering families. These are exactly those for which the sheaf associated to X is a direct limit of the sheaf associated to the y's lying over the sieve defined by the covering. Take all was and y's and y's. All right. Now, if f can be extended to a functor that commutes with direct limits like this, then we must have that f of x is, by the natural arrow, the direct limit of the f of y's. That is the direct limits of C tilde that come from C to C. Well, they should be transformed by f into direct limits in C prime tilde. But here I shouldn't put f, but I should rather put epsilon C prime f. And this condition is necessary and sufficient for the functor to be continuous. So continuous functors between sites, they allow us to define functors commuting with arbitrary direct limits between topoi. And of course, if we start with topoi, any such functor between topoi that commutes with arbitrary direct limits can be obtained in this way, because take two generating subcategories C and C prime in these topoids that are small, and if f doesn't yet map C into C prime, if f tilde does, if the functor that we are given doesn't yet map C into C prime, we place C prime by its union plus its union with the image of C. And so it does it. So continuous functors just correspond to functors between topoi that commute with arbitrary direct limits. And if we have a functor between topoi can be viewed as being sides, and this functor is continuous, of course, it can only it commutes with arbitrary direct limits. So that's the story of continuity for functors. Now, when we have a functor between topoi that commute with arbitrary direct limits, we say, hey, maybe it comes from a morphism of topoi. Well, of course, that's an extra restriction. So we are more especially interested in functors for which f tilde is left exact. Now, in the case when C admits finite inverse limits. Then F tilde will be, if F tilde is a morphism of topoi, as this functor here commutes with finite inverse limits, this will imply that this compositum commutes with finite inverse limits. That will imply that this compositum commutes with finite inverse limits. And if we assume moreover that C prime admits finite inverse limits, and that this functor here is fully faithful, that the topology of C prime is coarser than the canonical topology, then this will be reflected by the fact that F commutes with finite inverse limits already. And the converse, in fact, holds true also. Therefore, if C and C prime both have finite inverse limits, and if the topology of C prime is coarser than the canonical one, so that the functor from C prime to C prime tilde is fully faithful, in this case, a functor from C to C prime defines a continuous functor, defines a morphism between the topoi C tilde and C prime tilde, if and only if this functor is not only continuous but also left exact. Now such a functor, which is not only continuous but which defines also a morphism between the topoi, will be called a morphism of sides. But sometimes we will say that the morphism of sides is from C prime to C, because we want to go into the same direction as the geometric topoi. So for us the important case is the one where C prime is equal to C prime tilde, and we map sides into a topos. So therefore, the functors, that's it, so called here, assume we have a topos E prime here. Now what are the morphisms of the topos E prime into the topos C tilde? I will describe them all in terms of functors on C. These correspond in the opposite direction to functors going from C tilde to E prime that commute with arbitrary direct limits and with finite inverse limits. But according to our general, the first condition just means that we take all functors from C into E prime without any condition. No, I'm sorry, that are continuous, and that's this condition here. But this condition also means, all right, and the second condition, when we assume that C admits finite inverse limits, the second condition just means that the functors that we take commute with finite inverse limits as a left exact. And by the way, once we admit that our functor is left exact, C having finite inverse limits, the continuity condition also expresses itself in a more easy way, namely by just saying that covering families are transformed into covering families. So, to sum up, if we have, the nicest statement we get out here, if we have a side which is stable under finite inverse limits, and if we have a topos E prime, so the morphisms of the topos E prime into the topos C tilde, the category of these morphisms of topoi is equivalent to the category of all functors from C into E prime, which satisfy the following two conditions. They are left exact, and they transform covering families into covering families. So we see that these functors, they have a very simple geometric meaning, which depends only on the topoi considered and not on the particular side by which we have described this topoi. So this, I think, is really the main thing one has to know about description of morphism of topoi in terms functors between topoi, let's say more generally in terms of functors between sides, and more specifically morphism of topoi in terms of morphism between sides. I don't know anything more than what I said here. There are some slight things in the notes. There are something about co-continuous things, etc. But it's not too nice. It's not too important. All right, now let's come back to the situation. What are the morphisms of the topos E into the topos C hat? They correspond. C hat now is just a particular case of C tilde when I take on C which topology? The Gauss's law of the finest one never remembers. The topology, yeah, there are very few for covering families. Covering families are required to have sections, so it's a coarse topology. So coarse topology. I mean, all pre-sheaves are sheaves, and therefore these morphisms of topoi correspond to functors from C into E, which on the one hand should be left exact. Remember that we assume C with finite inverse limits. And second, they should be continuous, but the continuity condition is empty now, because covering families should be transformed into covering families, or like families that have sections are transformed into families that have sections. All right, now I'm through, because what do I want to do, by the way? All right, so oh no, I did it wrong. I want. All right. So I have interpreted for an arbitrary. That's it. For an arbitrary category C, in which finite inverse system limits exist, I have interpreted the category of functors from C into E, which commute with these inverse limits. I have interpreted as a category of morphisms of topoi from E into C hat. Let's write it down. Sex.